Troubleshooting network virtualization is not really a new thing. We've been using various tunneling technologies for quite a while, really, right? IPsec tunnels or MPLS tunnels or GRE tunnels or, on and on and on and on. We've looked at the idea of overlay networks or tunnel-based networks for many years now. So we want to think about the fact that we've actually been troubleshooting a lot of things in the context of overlay networks. So we can take a lot of those skills, many of those skills, and apply them to NSX. Here we've got some of the similarities, right? The endpoints don't know anything about the tunnel. The tunnels are transparent to everybody, right? We look at we've got transparency into the tunnels. We can actually see what's going on with the tunnels on both endpoints, so that we can actually work on them. Where NSX adds to the picture, what NSX adds to the picture is in some ways some simplicity, in some ways some complexity, but it all adds up to be not a terrible experience at all. With NSX, I don't have to actively manage tunnel endpoints. NSX deals with instantiating and destroying VXLAN tunnels as necessary. I don't have to worry about one device or one configuration issue impacting both my control and my management and my data plane, because we've separated those out into separate pieces. So if one of them fails, I don't have to worry about the others failing necessarily as well. So we've got these these pieces separated. We're not manually configuring overlay networks, right? When I create a logical switch, a new overlay network and its infrastructure is automatically put in place. So I just need to make sure that my control plane and my data plane is there. And we can arguably provide better visibility with NSX than with some other overlay solutions, just with the tooling we have in the control plane, in the data plane. But we do need to think about, in the context of troubleshooting NSX, separating the transport, the physical network, the way I get packets from host A to host B, from VTEP A to VTEP B. I need to separate that network communication path with the services that we're troubleshooting. So I need to be able to test my underlay network, my physical network, separately from my overlay networks, from the NSX networks. And we do have tooling in NSX to provide for that. We've got the ping command on the ESXi host that will give me a baseline on my underlay network, right? A baseline from tunnel endpoint to tunnel endpoint. Can we communicate? We can just use ping for that. That gives us some information about the health of our underlay network. Now, outside of that, ultimately you're responsible for your underlay network. We're not going to tell you how to troubleshoot your Cisco network or your Arista network or your Netgear network or whatever you happen to have, right? That's entirely up to you. But we do need to understand that underlay network is there, and it's necessary to get data flowing around the data center. Things we need to worry about with the underlay network, the maximum transmission unit or MTU size. VMware recommends a minimum 1600 bytes MTU for NSX logical switching for our VXLAN implementation. I need to make sure that if there are any firewalls in my underlay traffic flow between VTEPs, that they're allowing the right port for VXLAN traffic. We need to make sure that the NIC teaming policy on my ESXi hosts is correct and not causing problems, right? So in the context of the underlay, there are pieces of that configuration at the ESXi layer that we need to worry about, as well as in the underlay network. Now, as I'm going through my troubleshooting, I'm in NSX, I may need to just cut things out of the picture. What components, what NSX pieces do I need to focus on? Do I need to worry about my NSX manager? Well, am I having management related issues? Am I having login issues? Am I having security related issues? I can't publish firewall rules, for example. That comes into my management plane and might be impacted by the functionality of my NSX manager. Do I have a control plane dependency? If I've got logical switching or distributed logical routing, the answer is almost invariably yes. There is a control plane dependency. So are my NSX controllers healthy and operating properly, and can they communicate with my ESXi hosts? If I've got security-related issues, are they NSX security-related issues? Are they partner tool-related issues? So do I have a partner antivirus solution, or a partner vulnerability assessment solution, or a partner firewall solution? Are they giving me trouble? At that point, not only do I have to look at the NSX control and management and data plane functions that we may be that we're concerned about, but I also have to look at the partner tooling as well to make sure that those pieces are in place. So I need to think about which NSX components are part of my particular puzzle, right? Part of my particular troubleshooting event. Looking at logical switching, what's the faulty service? Is it a logical switch? Is it in the data plane? Is it a faulty control plane issue? Is it a faulty management plane issue? Here we see just kind of a punch list of things I might want to look at in troubleshooting logical switching. We'll go into way more detail elsewhere in the course about troubleshooting logical switching. Again, with logical routing, we'll go into way more detail elsewhere, but here's just kind of a punch list. For logical routing, this is really kind of interesting. Logical routing gets us into, in a lot of ways, validating, is my logical router entity configured where it needs to be configured, and is it configured properly? And once we validate that, logical switching is what we fall back on, right? The logical switching or logical routing, traffic flow rather, we do the logical routing, and then the logical router gets out of the way. So the troubleshooting my logical routing, in a lot of cases, could be much more simple. It's kind of scary to put it that way. Troubleshooting routing may be a little bit more simple than troubleshooting the switching, because I may have a logical routing symptom that is actually a symptom of a logical switching problem. So a lot of things to think about there, right? Lots of pieces in NSX are very much intertwined. So after going through these two segments, we should be able to think about a structured approach to troubleshooting. We should be able to think about symptoms and problems. We should kind of have an idea of separation of service layers in NSX, right? The management plane, the data plane, the control plane. We should also be thinking about how we're applying our troubleshooting methodology to those different pieces. So to really kind of think about Module 2 as a whole, a structured troubleshooting approach enables us to resolve problems quickly and effectively, as opposed to, just scattershot looking at this and looking at that. If I have a methodology, if I have a structured kind of way of looking at a symptom, then I can diffuse that into a problem and then resolve that problem much more quickly. Understanding the basics of VMware virtual infrastructure is going to be a very important thing. Your configuration is a very, very important thing. We talk about this here as a basic requirement for troubleshooting. I think it might be a little bit more than a basic requirement. It's actually a very critical requirement that we're looking at. Management plane, control plane, data plane, all troubleshot separately, but they are all interrelated. So we need to understand that interrelationship, but make sure we approach them as separate components of the infrastructure. We need to understand networking. right? Just to wrap this up, we need to understand networking. We need to understand the networking services that we're working with. And, final bullet point, final key point, documentation is good. Uh, Documentation is good in both the logical and the physical network. That's going to help a lot in the troubleshooting process. So NSX introduced a couple of years ago now the central CLI, or command line interface. The nice thing about the central CLI is that it's centralized. No longer do I have to, while I'm troubleshooting an issue, log into an NSX manager and one or two NSX controllers and an ESXi host or two or three, depending on what I'm troubleshooting. I don't have to worry about having, a dozen different SSH sessions open to a variety of objects in my NSX infrastructure. Now I can get all of my information from one central location, right? The central CLI is housed in the NSX manager. So all I need is authentication access to the NSX manager, where I can then go and collect all the information from all of the other objects. Now, convenience is not the only real benefit to the central CLI. We also have what I would consider a security aspect to this as well, right? As NSX administrators, we are likely networking or security personnel rather than vSphere personnel, and so we go back to kind of the idea of separation of duties, where if I don't need access to the ESXi host, I probably shouldn't have it. And for a great number of things we might do on the ESXi host from an information gathering perspective, or even things like packet capture, many things are actually going to require super user access on that ESXi host. Well, if I'm looking at role-based access control in my infrastructure, my networking folks shouldn't have super user access on my ESXi hosts any more than my vSphere administrators shouldn't have or should have privileged access on my routers and switches, for example. So giving or providing the central CLI, having this central pane of glass, if you will, for the command line to gather all of this information, to leverage the existing relationship between NSX Manager and vCenter to help us get some of this information and do some of these things without having explicit access to the end resources is frankly a very, very good thing. So there's a lot of benefit to the central CLI. Convenience and security may well be considered the two biggest. Central CLI is from a command syntax. The anatomy of a command is fairly straightforward if you really start breaking it down. Up at the top, retrieving information from NSX Manager, show logical switch list or show logical router list or so on, right? Show me an object or show me a list of all of these types of objects, right? These are the things that NSX Manager knows, right? There's nothing more to the command than that, to a point. Getting data about the control plane, right? Instead of logging into the controllers and saying show control cluster logical switch, we can do a show logical router controller, right? So show me the information about the logical router from the perspective of the controller. Well, which controller? Well, I could specify a controller with a controller ID, or I could just say from the master controller. So one controller is going to be the master for a given object, whether it's a logical switch or a logical router. And we can just let NSX figure out which object the master is, or which controller rather the master is for that object. So show me the logical switch. Show me logical switches on the master controller, that matches this VNI, right? Show me this logical switch. So we can look at the central CLI and get information from the control plane about what the control plane sees. So I can look at things now from the management plane perspective as well as from the control plane perspective. But I can also look at the data plane perspective as well. Show logical switch, host, and then the host ID. So show the logical switch information on this specific host for this VNI. So I can also query the data plane configuration and activity of a logical switch or a logical router or whatever as well. Right? So this is the basic structure, the basic anatomy of the central CLI. Now, the show logical switch, show logical router, those are not the only central CLI commands we have. There are a great many of them that we will see throughout the remainder of this course. But what we're trying to show here is the basic syntax of my central CLI commands. Right? They're all going to be show logical router, logical switch, DFW for distributed firewall, edge for edge services gateway, right? Things like that. Show object from what angle, right? From the management plane angle, from the control plane angle, from the data plane angle, and then any of the other arguments that or subcommands that may go with a particular command. And if we look at this chart, we will notice that while the central CLI can do an awful lot, there are some things that the central CLI doesn't have an equivalent for. Many of these things are actually really focused around ESXi host-specific tools and configuration data. So while the central CLI is spectacular, you may still need to work with your vSphere guys to get some information. Lesson 2, an introduction to vRealize Network Insight. By the end of this lesson, we're going to have kind of an idea of what vRealize Network Insight is, what it does, why we might want to use it, high-level architecture of it, and we'll show that, hey, you can actually identify and use vRealize Network, identify issues and use vRealize Network Insight as a troubleshooting tool. So Network Insight. Network Insight is part of our vRealize suite of tools. And the entire purpose of it is, as its name implies, is insight into the network. What are we doing in the network, both physical and virtual, mind you, as well as how do we plan for microsegmentation, things like that. I know previously in this course we've talked about Application Rule Manager. But Network Insight goes quite even further than that. So what are my big features? What are my big 3 features if I had to pick? Security planning, right? Security planning. Who's talking to who? I can look at my entire infrastructure and start making these decisions based on who's talking to who. Visibility is another big one. I can actually see a packet as it goes from a virtual machine to a physical machine through the physical network. Right? You may say, but didn't we just talk about trace flow and talk about how awesome that is for that very thing? Well, yes, but Network Insight, since it can communicate with your physical network gear, not only can we see when the packet goes from host 1 to host 2, we can actually see what happens between host 1 and host 2. So we've got a deep level of visibility here, much more so than the basic deep visibility, I say, that we have with the core NSX tools. And then advanced operations. We've got best practices codified, health checks built in, things like that around NSX. So Network Insight knows NSX. Because it knows NSX, it can tell you when something's wrong with NSX and help you fix it. Network Insight is made up of 2 primary pieces, 2 main components, 2 big moving parts. We have the platform virtual machine. The platform virtual machine is the one that does an awful lot of work. It's the one we see. The platform virtual machine provides the interface to Network Insight. It does the analytics on the data it receives, things like that, right? This is the thing that does all the health checking and the visibility monitoring and all of that kind of stuff. We also have a proxy virtual machine. Sometimes it's also called a collector virtual machine. The proxy VM is another heavy lifter, but it does different heavy lifting. The proxy or collector virtual machine is what you attach to all of your network devices, to vCenter Server, to NSX Manager, to ESXi hosts, all of these different things, so that we have data sources to bring in. So the collector virtual machine brings those data sources in and then feeds that data into the platform virtual machine where all of the analytics is actually done. So microsegmentation, right? Security policy automation for microsegmentation. How fun is this? We can go in and after we configure or discover configure our vCenter pieces, we can go in from Network Insight and discover grouping objects in vCenter, security tags, logical switches, folders, clusters, etc. Right? So we understand vCenter objects. So we can look at things and say what cluster is talking to what cluster, or what host is talking to what host, or what resource pool is talking to what resource pool, and so on. We can go down to what network, what VM, et cetera, et cetera. We can get into, we can actually make recommendations based on those things that we've learned and who is talking to what, right? So we can give you these really, really granular policy recommendations because we're watching all of these things. And then if you really want, we can export that data into a CSV format that you can do with what you will. We can also use Network Insight for various auditing and compliance things, where we can go in and look at firewall policy. Is a firewall compliant with my policy? When did something change? Did something change? If something changed, who changed it, right? Complete audit level information. And I can go back and forth inside my data center about that with my timeline. There's my visibility. Where is the packet going? Through what pieces do we have to pass to get a packet from point A to point B? Now, unlike traceflow that we've already talked about, this is measuring and monitoring real traffic. This is not the visibility that we're showing here that we have in Network Insight is not by any means artificially generated. This is what real traffic is doing. In addition to what we just saw, we can use Network Insight to see what port I'm connected to on a physical switch, right? What virtual NIC maps to this distributed switch, which has these uplinks, which map to these physical switch ports, right? We can actually get that detailed, so I can map out all kinds of levels of detail as far as who's connected to what, where, and why. We mentioned earlier our best practice and health checks and things like that, right? Network Insight knows NSX. So we can leverage this to help make our lives as NSX administrators easier by leveraging this as a set of daily checks that we come in and look at, and hey, do we have a problem with logical routing or with NSX control plane or what have you? We can look at that, right? So here we see highlighted an MTU mismatch. I've got a VM NIC, or rather a VM KNIC, a VM kernel port set to a 1500 or a 1600 byte MTU, which is great. That's what I need for VXLAN. This VM kernel port is likely my VTEP. But Network Insight has detected that the physical NIC on my ESXi host is actually configured for 1500 byte MTU. So there's going to be a problem there if we don't fix it. Right? Here we're looking at a distributed routing problem, right? Distributed logical router routing problem. Networks are not reachable for some router. Well, I can hit the little wrench and screwdriver icon that we've got circled over here, and Network Insight can actually provide you some troubleshooting tips. Where does Network Insight maybe recommend that you go? Right? Now it's kind of kind of easy to think about if we look at the issue below, where the distributed router service virtual machine, or the DLR control VM, is not powered on. But we can still kind of see that Network Insight can provide us some additional value. So we should be able to talk a little bit about Network Insight, what it is, what it does, why it's valuable, the proxy and the collector VMs and what their uses generally are, as well as how we can identify problems with Network Insight. Lesson 3, Introduction to vRealize Log Insight and the vRealize Log Insight Content Pack for NSX. By the end of this lesson, we should be able to kind of talk about what Log Insight is, why it's important, how we might use it in troubleshooting network problems, identifying network problems, how we're going to use it in day-to-day NSX operations. So we come into this and we talk about the importance of log management. Logs exist everywhere, right? They provide us potentially gigs and gigs and gigs of unstructured data every day in our data centers. Some of us may not have a centralized solution to look at them, which means we have to pore over logs locally on my routers and my switches and my storage devices and ESXi hosts and Unix boxes and whatever else we might have hanging around. That's kind of the opposite of efficient. We want to get into log management, right? Every data center should have centralized log management and efficient and effective log management put into place. And one of the ways we might do that is by adding in and centralizing logging first and foremost. We talk about log collectors and analyzers must have certain characteristics, right? We've got to provide a holistic solution. If I can get logs from one thing but not from another thing, that's not going to do me a whole lot of good, is it? We want to make sure that the log management platform understands what the software-defined data center is all about, maybe for correlation or intelligence. We want to have it extensible in some fashion or another as I add new things to my logging, right? My data center is always changing. I may be bringing new vendors in. I may have new gear that comes in during a lifecycle refresh. Maybe I kick one vendor out and bring another vendor in. Who knows what's going to happen in the data center? I need my log management to be able to keep up with that set of unknowns. So we need to think about these things for our log management tooling and platform. Now, VMware offers a platform, a log management platform called vRealize Log Insight. Here we go with more tools out of the vRealize suite of products. vRealize Log Insight provides a level of structure around unstructured data that we don't have otherwise. We show here, if we look here at the dialog, right, we can ingest all kinds of logs, right? We have native syslog support. We have agents that we could install in Linux. We have agents we could install in Windows systems, and so on and so on and so on. So we can ingest logs from a number of different devices and systems, and we can lump them all. They're ultimately lumped all together. We can actually analyze them. Right here we're showing lots of different log messages. And I can search through them and sift through them and do what I can and do what I will. And that's great, right? I can search through things. The structure we talk about adding is in the form of tags and other fields in the syslog message that we can sit and define. And then if we look over on the right-hand side of the slide, under that fields column, we can actually go in and click on things and drill into specific log types or specific logs from specific hosts or what have you. And we can start doing some really cool things. One of the places we create that structure, one of the places we generate that structure is through content packs. So there are content packs provided for lots of different things from lots of different vendors. VMware has generated a number of vRealize Log Insight content packs. but other vendors have developed their own content packs. And what the content packs do for us is they provide, first off, some of that structure, right? They provide those keywords and field extractions from their specific log type messages and whatnot. They provide a series of maybe canned queries or alerts, right? Log Insight does alerting, by the way. They also have dashboards that they introduce into Log Insight that you can go look at for a variety of different things coming from different types of events. One of those content packs is the content pack for NSX, right? NSX has a number of moving parts, right? We've got NSX Manager that generates logs. We have the ESXi hosts on the data plane which generate logs. We have the controller cluster nodes which generate logs. We have the NSX Manager that generates logs, right? On and on and on and on. And so that all sends lots of syslog data. But if we look, right, syslog feeds into Log Insight, we don't have to look at Log Insight as just syslog data. If we look, a big capability of Log Insight is this dashboard capability that we mentioned just a second ago. So we can actually visualize what's going on with our logs instead of just looking through hundreds and thousands of lines of text. So why do we want to use the Log Insight content pack? What are the main use cases? Well, because I want to monitor NSX. I want dashboards relevant specifically to NSX. I want my keywords and my alerts specific to NSX because I'm using NSX in my data center and I'm using Log Insight in my data center. So we can look at data a couple of different ways, right? We've kind of mentioned this. We can look at data as the raw log data, and I can interactively query that data to filter out and find specific things that I'm looking for. That's pretty awesome. And then we have dashboards that we can look at, which are equally but differently awesome in that they give us a level of environmental visualization that we really haven't had if we haven't had any kind of log analytics platform before. So, these dashboards may be just simply number of log messages or number of firewall rule drops or things like that, right? Lots of different stuff we could look at. So we were showing just a dashboard, an overview of the distributed firewall. So, here we can see the top rules that we're hitting. We can see the number of audit events over time. We can see the permit drop chart, so we can kind of look at this to see when we have maybe traffic spikes or when we have activity spikes going on. So there's just a lot of really useful information here that might be a little challenging to get otherwise. I can look at different traffic, right? The traffic dashboards for the distributed firewall, I can go in and look and see my top sources and destinations, right? I don't need an IP fix collector for this. We can see it if we're logging our distributed firewall rules. It's still a good idea to have flow monitoring enabled, though. But we can see a lot of that same kind of information here through the distributed firewall rules dependent on rule logging. Now we can also go in and add another layer to our logging and for Log Insight, for example, or for whatever my log management platform is with my distributed firewall rules by assigning tags. When I assign a tag, this is just a piece of metadata, a string that's injected into the syslog message that is written into the packet log whenever the distributed firewall matches on a firewall rule, which means now I can simply I can simply search for that tag if I'm looking for a particular type of activity. Now at this point, we're going to go into the first lab, right? The first lab is pretty straightforward. It shouldn't take a whole lot of time. We're going to get into the lab environment, right? We're going to access the student desktop system from which you're going to do all of your labs. We're going to go and validate that Log Insight is indeed licensed and the NSX content pack is indeed installed. We're then going to kind of poke around the dashboards a little bit and explore that, and then we're going to do the same thing with the analytics. We're going to walk through some basic interactive analytics that we might look at so that we can see what's going on, right? So now that we're all done with that, we should be able to talk a little bit about Log Insight, why we need it, why we want it, what we can get out of dashboards and analytics, and how we can look at all that. So when we think about the key points, wrapping up Module 3 here. Administrators of an SDDC require a variety of tools to operate and troubleshoot their environment. I think that's a pretty fair statement. What do you think? We've got a lot of tools that we're going to use, and there may be even more that we haven't even mentioned here, that we never even brought up here, right? The toolbox is vast, and there are many things that we can do to add new tools to your toolbox. So we've got to think about that. We need to be able to use the NSX tools, the native NSX tools. That's going to be one of the most effective sets of tools that you have. No matter how many third-party things show up, the native NSX tools provide a significant amount of flexibility and utility because they're going to be in every environment you're in. The non-native tools are spectacular, right? Even if you just look out to the vRealize suite with Log Insight and Network Insight that everybody should have. But even without those, the native NSX tools provide us a significant amount of capability. But Network Insight and Log Insight, both spectacular. They're both very good at what they specifically do, right? With Network Insight very specifically being a flow monitoring and security and visibility tool for the network, and Log Insight being a log management platform, a pretty solid one. When it comes down to it. So that's what Module 3 was all about. Lesson 1, native NSX tools for troubleshooting and operations. By the end of this lesson, we should be able to discuss the operational requirements and available tools provided by VMware and maybe even some tools provided by our partners. We should be able to at least at a basic level, use the native tooling like the central CLI, the NSX dashboard, flow monitoring, trace flow. We should have a basic grasp on those, and we should be able to kind of describe the vRealize suite tools that kind of go with us, specifically vRealize Network Insight and vRealize Log Insight. So as we think about our network and we think about our operational requirements for that network, right? We need to be able to monitor the network. We need to be able to troubleshoot issues in the network. We need to be able to get logs from the network and audit the network, and we need to understand where our traffic is going. We need our flows that are going to give us more information over all kinds of things in our network. So we need to be able to do these basic sets of things, and the tools that we talk about in this lesson are going to meet kind of all of these different needs, but there are a lot of different tools, right? There's no one tool to meet all of these basic requirements. There's no one thing that we're going to get into that's going to do all of this for us. So we kind of break this down, and we show this chart that gives us kind of a breakdown of different tools that we may be looking at, and we may already be using in our infrastructures. So if we look at tooling functions for event data or polling data, right? These are our traditional SNMP type tools that the things that are catching SNMP traps that are being sent by different things in your infrastructure and alerting you when one threshold hits 90% or another threshold hits 80% or whatever it might be. In NSX, we have some SNMP MIBs that we can load into that SNMP collector. And then NSX Manager can send SNMP traps based on a variety of different system events. And then you could also, in a polling kind of fashion, instead of doing an SNMP poll, we could use the NSX API to do some polling to get information about your infrastructure and what's going on in NSX. The vSphere web client gives us some of these kinds of informations. vRealize Operation Manager can give us some of this type of information. We can kind of use these to wrap it all together, even though we're not necessarily looking at what we traditionally might think of as event or SNMP type data. And then we've got partner tools that do some of this kind of stuff, right? EMC Smarts is one example that ingests a lot of this event data and that integrates very nicely actually into NSX and does very, very many things well, maybe for other parts of your infrastructure as well as for NSX. Flow information, application data, application flow records. You're probably using flow collection, NetFlow or IPFix type tools in your infrastructure for a variety of things today. This is not a new idea in the concept of network troubleshooting. So we have both IPFix capabilities out of the box with NSX, as well as a utility called TraceFlow. TraceFlow allows us to watch packets as they go from one virtual machine to another over my logical networks. We can get flow information, packet capture information, both through the vSphere CLI, through vRealize Network Insight as well. Network Insight is keenly suited to various and sundry flow monitoring. And then you may have tools from, say, Riverbed as a partner example that's collecting flow data or is able to collect flow data from NSX and analyze it using all of the secret sauce that Riverbed brings to the market. And then we've got packet capture and log capture as different functions that we may look at. NSX provides, or in your environment rather, you may be looking at individual log files. You may have your own syslog collectors in play of one caliber or another. You may have packet capturing tools or span ports or things like that in use for packet capture. We can use for packet capture the NSX logs. We have packet capture tools at the command line of ESXi that you can initiate packet capture. We've got packet capture through the web UI now in NSX. So we've got a great number of things there that you can look at. We've got port mirroring capabilities on the vSphere distributed switch, on top of which NSX builds. So we can do port mirroring there. We can also leverage vRealize Log Insight for centralized logging and analytics. So we've got a number of native tools in NSX and in the vSphere and vRealize suites that we can leverage for capturing all of this information and analyzing and investigating this information. You may also be using tools from, say, Gigamon or a partner like that for other logging or packet capture, packet monitoring, collection data. So in NSX 6.3, we introduced a dashboard, kind of a quick one-hit view of the health of your NSX infrastructure. The dashboard, we've put a lot of work into the dashboard coming into NSX 6.4. If you've been managing an NSX 6.3 environment for a while, you'll notice right off the bat that the dashboard looks quite a bit different. So it's got the same basic information. We'll talk about some cool stuff in a couple of minutes. So the dashboard is updated well in NSX 6.4 and becomes a new focal point for the overall troubleshooting of and operating an NSX environment. We can go through the dashboard and we can look at any of the different sections, the little widgets as they're now called, in the dashboard, and we can see, traditional green light, yellow light, red light, good, not so good, bad kind of states, for different events. And here we see a couple of examples. If we click on those dots for the different objects, right? The NSX manager is there. There should be a dot for that. You should have 3 dots, one for each NSX controller node under your system overview, things like that. We'll kind of see what's going on there. If we just click on them, we get these little callouts, and they tell us when things are good or when they're bad, and better yet, why they're bad. So we can go in and see, everything from backup failures or backup, whether or not backups are configured, right? Here we show the backup status, and we see that we do have a failed backup, and that's bad, but we do see that it is configured and it is scheduled, and we're at least automatically trying to backup. We'll also show you, for example, that backups are simply not configured in the backup status. We see our controller connectivity and so on. We can go in and we can see our fabric status. When we talk about fabric status, what is the communication channel health for my different objects, in the data path, right? So NSX manager to the firewall agent, the firewall agent to the control plane agent, NSX manager to the control plane agent, identifying whether or not the proxy between the control plane agent and the management plane agent on the host is actually up and running. We can see the control plane agent to the controller node. So do we have any issues there, right? This is my traditional communication channel health. But that's not all we can do with the dashboard in NSX 6.4. In NSX 6.4, I can now create new widgets to pull information to give me additional health data for something that's important to me in my particular environment. So we can configure those right through the vSphere, or not the vSphere APIs, I'm sorry, through the NSX API. There's a whole section in the NSX API guide about working with widgets and how you can configure widgets and how you can manipulate the widgets in the dashboard. So you can now add new data to your own NSX dashboard. So the dashboard is now extensible above and beyond what's available out of the box. So we can create different visualization types. We have aggregate count widgets or grid view widgets or label value widgets where you define labels and values and things like that. We can customize data sources and so on. You can have as many as 10 widgets on your dashboard, right? Up to 10 widgets on the dashboard total. So you may be in a position where you're removing things that are less important and adding new widgets that are more important based on what you kind of need. We also have a system scale dashboard, so now we can actually see whether or not I'm starting to approach the configuration maximums of NSX. Recently, as of NSX 6.3, we began publishing a configuration maximums document, and those configuration maximums have been integrated into the NSX dashboard in the System Scale tab. So I can actually go and look and see how I'm doing compared to the maximum scale limitations of NSX. Most of the time, we should probably be well within tolerances. But when we do exceed those tolerances, or not necessarily exceed those tolerances, but when we reach the prescribed threshold of capacity, right, which, if I recall, is 80% by default, and we can change that, right? You can tune that based on your own comfort level. But once we exceed those comfort levels, those thresholds, then we will actually see NSX system events for those things. those particular threshold crossings, so that we know at that point, hey, it's time to add new capacity for X, Y, or Z, whatever it might be. So just to kind of wrap up the dashboard, it's brand new. It is the centralized view of health of your infrastructure. The scale is a thing now, right? We kind of expose the overall scale, what you've got deployed right now and where the maximums are. And the dashboard is completely customizable at this point. So cool stuff for the dashboard. Flow monitoring in NSX is a function that we can enable that we can then look at some live flow data in NSX Manager, or we can turn around and add on IPFix so that we could then send that flow data out for longer term storage and longer term analytics out to an IPFix collector. So flow monitoring is something that we want to think about enabling in our NSX infrastructures. So once it's enabled, and I can look at my flow monitoring dashboard, and I can see, kind of top talkers. We've got a couple of buttons here for top flows, top destinations, top sources. These will give me sort of my top fives in my environment at any given point in time, right? What's going on kind of right now-ish. Flow monitoring is not quite real time. It ingests data about every 10 minutes, so not quite real time, but close enough. So we can see kind of within the last 10 minutes who the top fives have been. I can go over to the details by service tab as we've got highlighted here, and I can look at who are the busiest services in my environment, SSH, HTTPS, DNS, right, whatever's going on. In this particular screenshot, right, DNS seems to be a pretty hot talker, but there's not a lot going on in this lab, right? 101 kilobytes worth of traffic. So if that's one of my top talkers, I've got a pretty quiet shop right now. To enable flow monitoring, I can go into the flow monitoring section of the Navigator UI in the Networking and Security Web Client. I can go over to the Configuration tab, and then I can enable flow monitoring. It's disabled out of the box on NSX Manager. On an NSX deployment, it's turned off, so I have to go in and manually turn this on. And then I can go in and I can do exclusion filters if I so choose. If I want to minimize the amount of data that flow monitoring is actually collecting, we could go in and do things like tell flow monitoring not to collect layer 2 flows, only to collect layer 3 flows, or something like that. What you may filter out is going to be certainly something that you're going to figure out and define in the context of your own environment. Once we've got all that set up, however, you hit save, flow monitoring is enabled. If you wait 10 to 15 minutes probably, your flow monitoring data will start to populate in the web UI. Now, flow monitoring is great, but it only gives you a finite amount of data, and there's not a lot of analytics going on that data set, right? You saw what we have. We have got our top talkers and top talkers by flow, or by service rather, by source, by destination, right? That's about it. But there's a lot of wealth. There's just a wealth of information that could be mined from that flow data. So you may put in place an IPFix collector that will take flow data and can possibly give you further analytics on it. Could also store much more data, right? The built-in flow monitoring only stores about 2 weeks worth of data, where your external flow collector, well, how much storage does that support, right? How much time does that support storing? Probably more than 2 weeks. So to enable IPFix, it's pretty straightforward. Under flow monitoring, I hit the IPFix button rather than the flow monitoring button. I then add an IPFix collector. I can enable IPFix. I can define the observation domain, which is simply a metadata that identifies this NSX manager instance. I can set that, and once I check the box there that says enable Netflix, that's a slip. Once I check the box that says enable IPFix, then IPFix is enabled. I will hopefully start seeing data in my collector very shortly, right? Again, about 10 minutes or so. This is not real time. Something else I can do is look at flows live. So we can do some live monitoring in NSX Manager through the web interface. So I can go into the flow monitoring UI. I can go to the live flow tab. I can select a virtual NIC that I want to collect data from, and then start the session. We'll start pulling that data every 5 seconds if that's where you set your refresh rate. Right? The refresh rate can be as fast as 5 seconds, or you can set the refresh rate slower. And then you can see flow changes within that refresh interval, giving you very close to a real-time potential flow monitor for a given virtual NIC. So IPFix gives us a lot of flexibility in collecting flows, right? We were just talking about that. We've got a couple of partners that integrate a little bit more closely with NSX than others, and that's okay. Even if they don't integrate an IPFix collector, IPFix is a standard. It's a standard protocol written out and ratified by the IETF, so any IPFix collector should be okay, right? Should be just fine. And we'll forward that flow data to the IPFix collector, where we can then start doing deeper analytics. Now, let's look at a couple of things real quick. When I enable IPFix, NSX Manager is going to reach out to the ESXi hosts and tell them to enable IPFix traffic through the ESXi firewall. So here we just show a couple of different ways to validate that. I can validate that through the vSphere web client or through the ESXi host command line with the ESXCLI network firewall rule set rule list command. I can also look at my IPFix configuration using the vsip ioctl command. Now we'll see vsip ioctl quite a bit more when we start talking about the distributed firewall, but IPFix is a function ultimately of the distributed firewall. So vsip ioctl load IPFix config tells us what our IPFix configuration is, whether or not IPFix is enabled, what I've set for my domain ID, my flow timeout, how many collectors do I have, where are they, and then if I want to validate that flow data is actually being sent to my collector, I can use TCP dump on a TCP dump-UW, more specifically, on an ESXi host to look for traffic with a destination of my IPFix collector and the port of my IPFix collector. So flow monitoring gives us some good flow visibility about what's happening with the distributed firewall. It uses the distributed firewall tooling to give us that flow data. Flow monitoring is required by IPFix. So IPFix is a superset ultimately of our flow monitoring capabilities. We'll use flow monitoring for just small environments or things where I don't need analytics or long-term data storage, and we'll use IPFix for longer-term data storage and business intelligence around our flows. So microsegmentation is a really big use case for NSX in the data center. One of the questions that's always asked is, how do I get there? How do I figure out what rules I need, where I need them, why I need them? Because let's face it, we don't all know all of the various and sundry network connectivity dependencies that are necessarily floating around in our data center. And even if we think we do, and I've been bitten by this before, even if we think we do, we close off one port only to realize that there was something undocumented somewhere, that an application was using, some goofy thing to go talk to, whatever it might need to talk to, that all of a sudden we just blocked off the firewall and broke the application. Hate it when that happens. That's what Application Rule Manager is here to help us with. What we can do with Application Rule Manager is we can start to populate security groups and look at the flows in that security group to see who's talking to what. And then we can go ahead and add to our distributed firewall rules based on what we discovered in Application Rule Manager. So once we've collected the flow data, we get to view all of that information right here. We're showing that as we kind of build out this slide here, right? Now we see flow data. Ta-da! Now we know who's talking to what. And then I can change my view into, say, my processed view, where I've gone and done all my activity or application rule managering. And, I can come in and I can start looking at the actions on my flows, right? So here we've got a flow. We've done a little right click to get the actions menu up, and, I can start building IP sets. I can start creating firewall rule sets and all kind of cool stuff. So here we're looking at under firewall rules. I can go in and create new rules based on flows. So creating a rule based on a flow gives us a dialog, something like this, where I can name the rule. We have the source and the destination that I can edit, because maybe app server 1A can talk to more than just database server 1A. Maybe I have a database server 2A floating around, or maybe I want to change database server 1A into the database servers security group, something like that, right? So I can still edit this stuff as I'm building my rules with Application Rule Manager. Service, where am I applying this rule? What's the action? Am I going to allow? Am I going to block? Am I going to deny? Am I only going to worry about this rule incoming or outgoing, or will I just worry about it on both in and outgoing traffic? Application Rule Manager provides us a significant amount of flexibility in getting started down our microsegmentation path. Endpoint monitoring is a function of NSX that allows you to figure out which flows map to which processes in your guest virtual machines. This has an opportunity to give you a very detailed amount of information about what you have going on in your infrastructure, so that you can dig deeper into understanding what your environment is actually doing. Some things to think about, however, is guest introspection leverages endpoint monitoring leverages the guest introspection framework. Let's make sure I spell that out in the right order. Endpoint monitoring leverages the guest introspection framework, so we need that deployed, right? Which means I need my guest introspection service virtual machines on my clusters prepared for guest introspection. So the service virtual machines will be deployed, the endpoint security multiplexer VIBs will be deployed, and so on, right? So that's all going to be set up and ready for me. And then I need VMware tools installed. The complete installation, or at the very least, the guest introspection driver component needs to be installed in my Windows guests. As of NSX 6.4.0, the endpoint monitoring is only supported on Windows guests. No Linux support at this time. To use to use endpoint monitoring, I need to build a security group and add some virtual machines to this security group. And then I'll start my data collection for endpoint monitoring where I will select that security group that I want to monitor. We'll get a list of the virtual machines that are going to be from which data will be collected, and then I just turn on data collection. Once I'm collecting data, I'll be able to see how many virtual machines are in the security group that I'm collecting data from, how many processes are generated traffic, how many flows are inter security group flows, how many flows are intra security group flows, so how many flows are inside the security group from one security group member to another, or how many flows go from one security group member to something outside. As I start drilling in, I can start looking at individual virtual machines perhaps, and I can start to see, in this particular case, I have two flows coming out of this virtual machine. One is being sourced by PuTTY, so I'm going to assume that's an SSH session, just knowing that PuTTY is an SSH client for Windows. And the other is something from VPX client, so that's a VMware-related connection. So we start to get these very detailed lists of which processes are generating traffic and to where they're generating traffic, which could be potentially a significant benefit to your security planning and your infrastructure. Have you ever wondered where a packet might go as it winds its way in, out, and around your logical network to get from one virtual machine to another? That's what TraceFlow will tell you. What TraceFlow does, right? TraceFlow is a spectacular tool in your NSX troubleshooting toolbox. What it does is it'll inject a packet into a source virtual NIC. That packet will be crafted however you decide to tell it, whether it's just a good old-fashioned ICMP, echo request, or a TCP SYN or a TCP reset or whatever it might be, right? You have lots of control over what's going on here. We inject this packet into the source virtual NIC, and every component along the way reports back to NSX to say, this is where it was, this is what I did with it, right? So we get an output kind of like what we're showing here, where we see, hey, this piece accepted the packet, we processed it, we forwarded it, we accepted it, we processed it, we forwarded it, and on and on and on. This gives us a massive amount of visibility into what my network, at the very least, should be doing. It's a huge thing when troubleshooting, say, firewalling or routing issues. So it's a very, very powerful but very, very simple tool where I can select the source and the destination virtual NIC, and off I go. So, we use TraceFlow. We talk here about, identifying network failures and network verifications. Hey, I've got a routing thing that I'm trying to troubleshoot, or hey, I've got a firewall thing that I'm trying to troubleshoot. All of these are fantastic use cases. If you look closely down here on what's on the screen right now, this actually shows us that TraceFlow ran into a dropped packet. The distributed firewall dropped a packet that was sent from one source to another, and will actually tell you the rule ID, and will show you, if you click on the link ultimately that we provide for the rule ID, we will show you exactly what that firewall rule says. Now, we come into here, and here we have a successful or a delivered packet, and we see here that the traffic is going from one host to another host. We see that we're going, where we're going, when we're going, how we're going, right? So we give you literally step by step where the traffic is and where the traffic's going, and this is what makes it powerful. I have heard for years that NSX is a black box, and you can't see where your traffic is actually going, and to that I present TraceFlow. we really have a very, very powerful visibility tool in Traceflow right here that probably should be leveraged whenever you have a connectivity problem, right? This only takes a couple of seconds to run, and it'll give you a good idea of where your problem might lie. We've been able in ESXi to, through the command line, create packet captures for a long time now. But well, that means I have to be able to get into my ESXi host, and I need to know the packet cap-uw command line syntax, and it's kind of frustrating sometimes. In NSX 6.4, we take some of that frustration away. So now, in the web client, in the networking and security plugin for the vSphere web client, we now have a packet capture management utility, which is really, really nice. What we can do here is we can come in and create a packet capture session and figure out what we need to do, what data we want to collect, or from what we want to collect data. We want to then do all our things and, figure out filters and pre and post filter and what sources or destinations we want to look for and so on and so forth. And then we can manage those packet capture sessions through the web UI and download the PCAP files or what have you as necessary. Right, so let's kind of walk through this. Right, I can go in and hit the add button, create a new packet capture session, and then I go and figure out what host. Right, so I need to know which host I want to capture traffic on, and then I go into adapter and I select whether I'm going to do a physical. Whether I want to capture traffic from a physical adapter, a physical NIC, or a VM kernel adapter, or a virtual machine NIC, or a VNIC. Now here we've selected VNIC, but any way you look at it, once we select an adapter type, there will be additional data to fill out, right? Which physical adapter, which VM kernel port, which virtual NIC. So here we can select the VM NIC, or select the VNIC, and up pops a dialog with a list of all of the virtual machines on this host. Right, so I need to know which host my virtual machine resides on, and then I can start this process. So I select, I have to hit the radio button. Right, this is kind of a strange set of UI circumstances here. I have to select the radio button to get to a virtual machine, and then I select the little right arrow over here to actually slide this over to select which virtual NIC I want to capture traffic from. So in this particular case, this virtual machine has VM01 has quite a few virtual NICs. So we can figure out which VNIC we want to select traffic from. And then we have to choose the filter. Now, when we talk about the filter here, we are not talking about the filtering of the traffic filter. We're talking about the DV filter that we want to collect. So I could use this to select, say, the distributed firewall filter, the distributed firewall. And I could choose whether I'm going to, the next selection down, filter mode, whether I'm going to capture traffic pre or before it enters the filter, or post or after it enters the filter. I can also choose the traffic type. Do I want to capture traffic that's coming in, or do I want to capture traffic that's going out? So into the virtual NIC or out from the virtual NIC. And then under advanced options, I can go in and I can actually define my packet cap UW filters, right? Because that's ultimately what we're doing here in this UI is we're simply setting up a dialog where you go in and you select all of the things that you want to capture, where you want to capture, when you want to capture, why you want to capture, and that's ultimately filling out the packet cap UW command line for you. So once I've got my session created, it can be managed right here through the packet capture UI in the web client. So we see I've got a number of different sessions going right now. Some of them are capturing traffic from physical adapters and some from VM kernel, one virtual NIC. I've got some errors going on. We see all kinds of stuff, right? This is a very busy dashboard all of a sudden. Now that I've got a bunch of different sessions from which I'm capturing traffic. I can hit session status. I can look deep into that. I can see what's going on. Here we've got, stopped sessions. We can click on that and get a pop-up and kind of get some information about that. There is a maximum amount of time each packet capture will run. There's also a maximum size that we will hit for the resultant packet capture file. So, we'll see that, it'll be displayed right up on the top of your packet capture UI. And when we reach that size, PCAP file, or the packet capture has been running for however many minutes, well, that tells us that the packet capture is done. So I can download the file, right? I download the PCAP file and open up in Wireshark or your packet analyzer of choice. Or I can restart the session if maybe I realized that I didn't capture the behavior that I was looking for. Then maybe we restart the session. Whatever may be going on. We've got much easier management here through the web UI now than traditionally we've had simply through the command line. So, packet capture is way better, way easier to deal with in NSX 6.4 because it's now in the UI, right? I don't have to remember, a big long command line. Because we're in the UI, then I can create sessions. We can have multiple sessions, right? I can have an inbound and an outbound session going at the same time, for example, and so on and so forth. So I no longer actually need access to the ESXi hosts. Prior to NSX 6.4, if I wanted to get a comprehensive log bundle set for all of my NSX infrastructure, I would have to go download logs from the NSX manager, the tech support bundle. I would have to go download the tech support bundle from each edge appliance, perhaps. I would have to download vCenter logs. I would have to download ESXi host logs. I would have to go download logs uniquely from each controller, and on and on and on. It was a very time-consuming process. NSX 6.4, well, fixed some of that. It's still a time-consuming process to gather all of the logs to create a big log bundle, but we now have something in the UI here, in the web UI, to actually go and collect all that stuff from one central point. So the bundle collection tool, I can go in and select whether or not I want NSX manager logs, whether I want host logs, controller logs, edge logs. I can go in and select individual pieces. I have all of the control that I might want over which logs in my infrastructure I need to collect for a given scenario, for a given issue that I need logs for. I can choose whether or not I want to include the firewall logs or the guest introspection logs. And I can then turn around and choose whether I'm going to download this log bundle locally or I need to upload it to a remote file server if, say, you're working with VMware support, for example. And once we've got all of that information put together, I can say go, and we'll even give you a status, right? The UI changes to look something like this, where we just get these little circular graphs that will go from 0% to 100% as each component is complete. Again, this is going to take some time, right? Depending on how much you chose to log, this is going to take some time. So be patient, right? Be patient. Once it's done, if you are ready to download it, it'll say, hey, it's ready to download, click here, or you can upload it again to a remote file server, right? So you can upload it to VMware, you can upload it to your local file server just to get it out of the way, whatever it might be. So at this point, we should be able to talk about what the operational requirements of a network are and what tools we have at VMware to meet those different operational requirements, and maybe even touch on some tools by partners. We should be able to use, at least at a basic or a fundamental level, a number of different native tooling to troubleshoot your infrastructure, to deal with what you've got going on in your infrastructure. And then, again, we continue to briefly touch on vRealize, the vRealize suite, specifically vRealize Log Insight, vRealize Network Insight, that we may use in conjunction with our infrastructure. This is the VMware NSX Troubleshooting and Operations 6.4 class. This is Module 4, Troubleshooting and Operating the NSX Infrastructure. We are, according to the modules list, coming into almost halfway through the course. Why is this important? Understanding the infrastructure of NSX really is a, well, it's just a good thing to know. We need to know that the foundation of the house is going to be solid before we put up the walls, right? And that's kind of what we're looking at here. When we talk about the NSX infrastructure, we're talking about things like the NSX manager itself. We're talking about the NSX controllers. We are talking about the bits that are installed on the ESXi host, the VIBs or VMware installation bundles, the kernel modules and the things that make NSX happen. So these are all important things to kind of have an understanding of and understand how they get where they need to be so that we can continue to use them once we start virtualizing our networks. We have 4 lessons in this module. The first is going to be a quick overview of what all is involved in the infrastructure, what the basic deployment process, things like that. Then we're going to go through troubleshooting the management plane. So we're going to focus in a little bit on the NSX manager and some things that might go wrong there. Lesson 3 is all about the control plane and the NSX controller cluster, where we will start focusing in on that layer, that aspect of NSX. And finally, lesson 4 will talk about the data plane, where we'll talk about the host preparation and how to prepare the host and what happens and how to troubleshoot that. Lesson 1, an overview of the NSX infrastructure. What we're going to do in this lesson is kind of just talk through all of the big pieces that are involved that we're going to break down in the subsequent lessons and kind of start seeing how this all comes together. So NSX is broken up into 3 operational planes: the management plane, the control plane, and the data plane. And the management plane is where my desired state is going to reside. The control plane is where my current state, my runtime state, is going to reside. And then the data plane is where my packets and frames are actually processed. That's where all the work is actually done. We can, in the different componentry we're looking at, kind of split this up into the NSX manager exists in the management plane, as does the vCenter server. The controller cluster exists in the control plane, and then the ESXi hosts exist in the data plane. And we can kind of break that down just a little bit further here and show a number of other things that exist in each of these planes and kind of detail that out. We see this diagram relatively frequently in the context of NSX because it showcases all of the things, all of the pieces of the puzzle, as it were. We originally designed NSX to be consumed by a cloud management platform, but we don't need that. It's certainly not required. And then either the cloud management platform or my administrators will consume NSX through, or will communicate with NSX through the management plane, through NSX Manager, through vCenter Server. Also in my management plane is a user world agent that will be installed on each of the ESXi hosts called VSFWD, or the message bus agent. This is how NSX Manager can communicate directly with the ESXi hosts. The control plane, we've already mentioned the controller cluster, but the distributed logical router control virtual machine for my DLR also exists in the context of the control plane, and then we have another user world agent. So we have a control plane user world agent and a management plane user world agent. The control plane user world agent is called NetCPA, or the network control plane agent. This is what communicates between the ESXi host and the controller cluster. We've got our data plane. The data plane is going to consist of the ESXi host, the vSphere distributed switch, the bits, the kernel modules, all the things that we're doing down on the ESXi host to process traffic, as well as the NSX Edge Services Gateway. And here we see a communications breakdown of who's talking to what. The cloud management platform, if one exists, will communicate with vCenter through the vSphere APIs, communicate with NSX Manager through the NSX REST APIs. NSX and vCenter talk to one another using a private set of APIs, and then vCenter talks to the ESXi hosts using its standard management channels. NSX Manager, on the other hand, has some different channels that it uses to communicate with its various components. It will use REST APIs to communicate with the controllers. This is a private set of REST APIs within NSX. It'll use the message bus when it has to communicate with the ESXi hosts. Otherwise, the ESXi hosts will communicate primarily with the controller cluster. So to deploy NSX, we may already be familiar with this. It's a fairly straightforward process. I download and deploy the NSX Manager virtual appliance. The NSX Manager does house all of the other bits we need to install NSX. So it contains the controller virtual appliances, it contains the VIBs, contains the Edge Services Gateway virtual appliance, and so on. So I deploy the NSX Manager virtual appliance, right? One virtual machine. I would deploy through vSphere's deploy OVF wizard. I will register that NSX Manager with vCenter servers so that we have a nice one-to-one relationship going on there. I'll deploy my controller cluster. I will prepare my clusters and configure them for VXLAN and logical switching if I'm going to use that. And then I will deploy my edge gateways and start consuming and configuring my network services, my routing at the Edge Services Gateway, at the distributed logical router, I'll deploy my logical switches, and so on and so on. Naturally, I want to worry about requirements, system requirements in deploying NSX, right? Check the installation guide. There's a whole section in the installation guide about system requirements and planning and preparation. There's also a section for ports that we see here in the slide deck, a sampling thereof. In the installation guide, we can see all of the different ports that are necessary to be opened between clients and the NSX Manager and vCenter server, and all of the different pieces involved. So if we've got firewalls in our infrastructure, we have some solid documentation around what needs to be opened and where. So just to kind of summarize everything, we should be able at this point to describe what's going on with NSX, what are the major moving pieces, how to deploy NSX, how things all kind of communicate together at a high level. So that provides us a pretty solid foundation to move on and talk about troubleshooting those very things. Lesson 2, troubleshooting the management plane and NSX Manager instance. So what are we going to do in this lesson? We're going to talk about the NSX Manager deployment and some problems that may pop up with that. We're going to talk about communications channels in a little more depth and kind of see what's talking to what and where and how. We're going to talk about connectivity problems between NSX Manager and vCenter Server. We'll talk about NSX Manager to ESXi host communication issues, and we'll kind of talk about some logs and system events in NSX Manager that are going to help us identify quite a few potential problems. So we're going to kind of focus here in the management plane, right? That's what this is all about. We're focusing in the management plane. We provide over the matter of this course a number of different flowcharts, basic things that we might want to look at, to help you understand how a troubleshooting process works and where you might want to go to start resolving problems. In this particular example, we have a failure to deploy the NSX Manager. And when it comes down to it, a failure to deploy the NSX Manager is not precisely an NSX problem. It's really kind of a vCenter problem, right? Because we're deploying a virtual appliance. But that makes it no less important for us to think about. So what are some of the things we should probably do if we cannot deploy, for some reason, the NSX Manager? Well, first things first, not actually listed in the flowchart here is, why did it fail? What does vCenter say about the failure? That would be the first place that we really should look. But let's go beyond that and think about some of the other things I might want to do. I need to validate the OVA, the virtual appliance, is actually the right virtual appliance, or it's not corrupted. Something hasn't happened, right? We're downloading the virtual appliance over the internet. We're storing it on some kind of magnetic storage. Both of these things have been known to introduce corruptions into data files over time, right? It could happen. It may not be likely, but it could happen. We can kind of safeguard a little bit against that, or at least validate that things haven't corrupted, simply by checking the MD5 sum. When the My VMware download page for NSX will show you the MD5 sum for the OVA, for the downloadable file. So you just run MD5 sum or whatever equivalent command on your local system against the copy you have downloaded, and you just make sure they match. Right? Pretty simple. Other things we might look at are the release notes of NSX, the version specifically that you're deploying, whether it's 6.4.0 or 6.3.5 or whatever version you might deploy. Look at the specific release notes and make sure that A, we've got the system requirements, and B, more importantly in the release notes, that we actually have, or not have, but are not running into a problem that maybe is a known issue with a known workaround. Required ports, right? Always a good thing. I need to deploy a virtual appliance to get to my vSphere web client over port 443. My vCenter server needs to be able to get to my ESXi hosts, and so on. So validate all of those ports. Make sure that's all available and connected. Right? DNS is a big deal, especially between my ESXi hosts and my vCenter server. We've got to have a solid DNS infrastructure that we can look up long names and short names and reverse lookups, look up by IP address and all that kind of stuff. And then time synchronization. Time synchronization is a huge thing. And if you pay attention over the rest of this course, we are going to continue banging the drum on DNS configuration and time synchronization over and over and over again, because those two things are really critical path components. Now, I've gotten my NSX Manager deployed. I can't get registered for some reason. I have some kind of connectivity problems, maybe to NSX Manager in the first place. Again, the release notes are a good place to look. Ports and firewalls, right? Another good place to look. If I'm having specifically connectivity between vCenter Server and NSX Manager, these are likely both virtual machines. I know NSX Manager is, and more than likely at this point, vCenter Server should be. Migrate the vCenter Server to the host that NSX Manager is on. or migrate NSX Manager to the host that vCenter server's on, right? Take the physical network out of the picture, because I'm gonna take a guess here that both NSX Manager and vCenter server live on the same layer 2 network. They probably both live on your management VLAN, right next door to each other, proverbially. So, take vCenter or take the physical network out of the picture and in your troubleshooting, and put the two, co-locate the two virtual machines. If that still doesn't help things, maybe we want to look at the services on NSX Manager. Maybe my management services aren't running yet for some reason or another. That's naturally going to cause me some communication problems. If all else fails, check the logs, turn off and turn on the services, maybe reboot the NSX Manager. There are a lot of possible things that could be going on here. And while we try to provide a flowchart to give you an idea of where to look, it is certainly not going to be an exhaustive flowchart. We just don't have that much space on the slide. NSX Manager has a certificates UI in its management interface, and we can plug in our own certificates if we want. Right? We can generate a CSR and hand that off to our certificate authority and bring that back and upload it as a PKCS12 store to put our own certificate in. Otherwise, there is a self-signed certificate in NSX Manager that's generated the first deployment, right on the first boot process. We bring this up because we have seen from time to time that cloud management platforms may look like they're working, but there's actually a silent failure happening underneath, right? So my cloud management platform, my user goes in and deploys something, and it includes a bunch of virtual networking that NSX is supposed to make happen, and the cloud management platform comes back and returns to my user, hey, look, this is all good now. Well, NSX Manager may not actually do anything about it because my cloud management platform took the certificate mismatch message as a positive response rather than a negative response. So we've got a couple of fixes for that, right? One, I'd replace my NSX Manager certificate with a certificate and certificate chain that is trusted in my infrastructure, or from my cloud management platform, I can go ahead and accept that certificate and install it into the system and move on. Ensuring proper communication between NSX Manager and vCenter. So there are a number of things that are involved in proper communication. One of those is actually user account. NSX Manager uses a vCenter account to authenticate and register, and then applies an enterprise administrator role to that in NSX to the NSX components. So NSX permissions and vCenter permissions are separate. So the user account, kind of important. Other things we want to think about, here is an example of validating DNS and time on the NSX Manager, right? So my time server and my date time settings, as well as my DNS server settings. So DNS time, DNS time, DNS time. We can't say it enough. I can look at my NSX connectivity status between NSX and vCenter through my Manage vCenter registration link in the NSX Manager UI. And what we obviously want to see is a nice green dot there under status, and it says connected, and a last successful inventory update sometime recently. So hopefully that's what we see. If we need to change that, we hit the edit button, and that brings up this dialog to change the vCenter server. Hopefully I'm not doing that, but potentially change the credentials. So let's look at the background process real quick, and then we'll kind of wrap up a little bit. So NSX Manager, when I go and register NSX with vCenter server, I go ahead and go through the vCenter field. I publish my information. I hit OK. And what that's going to do in NSX Manager is spin up a couple of threads waiting for inventory updates. We are going to then reach out over the network to NSX or to vCenter server rather, and register the com.vmware.vshield manager extension. Then we're going to, through our private APIs, request a vCenter inventory because we need to know at NSX what exists in vCenter. And then we will wait for that inventory to be sent back by vCenter server. Then we'll keep requesting until we have a complete inventory. Now, those two background threads that we kicked off early on in this process are kind of put on hold. They're blocked for the time being until we receive all the updates. Then those threads are going to turn around and start processing what we've received from vCenter. So, DNS and time, critical services. We want to make sure that those are running and solid. Make sure everything in your virtual infrastructure is synchronized against the same time source. That's really the easiest way to deal with that. And then the account that we use to register NSX Manager with vCenter Server needs to have vCenter administrative permissions. So what kind of problems might we run into in connecting NSX Manager to vCenter Server? User accounts. We can't talk about that enough. The user account that I'm using to register with vCenter Server has to have vCenter administrative privileges. So we've got to make sure that's in place. So in my NSX Manager UI, when I go to vCenter registration and I hit edit and I look at the username, I need to go back into vCenter and validate that that user indeed does have the vCenter administrator role assigned to it. DNS and time configuration. We'll bang on that drum until the drum is not there to bang on anymore. A lot of the NSX infrastructure uses DNS to look up names of vCenter servers or ESXi hosts or things of that nature. vCenter server uses DNS to look up an awful lot of things. So my DNS infrastructure is pretty important here. Time is also pretty important as we pass tokens back and forth for authentication and so on. Time is important. Make sure all of your your NSX Manager and your vCenter server and your ESXi hosts and all these things, make sure they're all synchronized to the same time server. I don't care if the time server is correct, so long as everybody is incorrect exactly the same, right? Make sure everybody's time is the same. And then we've got just basic connectivity. I could run into a problem where I have some kind of more fundamental network connectivity problem between vCenter Server and NSX Manager. Maybe I have a problem in my physical network. Somebody unplugged an uplink somewhere, or an ASIC failed on a switch, or who knows, right? Who knows? Just some kind of more fundamental connectivity problem. So how can I start validating some of this connectivity stuff? Well, one of the things we might do is we might SSH into my NSX Manager to do things like ping my vCenter server, for example. So we can do that, and as we're doing that, we need to sit back for a second, to kind of take a brief step back and talk about the fact that the NSX Manager command line interface has both a basic operating mode and a privileged operating mode, sometimes called enable mode. So the basic operating mode, when I log in, when I SSH into my NSX Manager and I log in with my admin user, with the password, whatever password I set during the deployment, well, that punts me into an NSX Manager shell with the little greater than sign prompt, like we're showing in the top example up here. That's basic mode or unprivileged mode. In basic mode, there are some things I can do and naturally some things I can't. To get into enable mode, to get into the privileged mode, I type the word enable, right? Why it's called enable mode. I'll have hopefully a different password set for privileged mode. That password would have been set during the NSX Manager deployment. And once I'm in enable mode, I'll see my my prompt replaced, no longer a little greater than symbol, but now a hashtag or a pound sign. And then I can do things like show running configuration. The show running config command shows me the configuration of the NSX manager, kind of like we have on screen here. And this gives us an idea of what we've got going on in my NSX manager configuration. I can make sure that my DNS server is configured properly, that my management interface IP address is configured properly, right? This is just one more validation. All of this stuff I can see right through the NSX manager user interface, but maybe I'm more comfortable looking at things through a command line. Now I can look at the routing table. Right? This might be useful on my NSX manager if I'm trying to get to a vCenter on a vCenter server on a different subnet, right? So if my NSX manager is on 10.1.10 and my vCenter server is on 10.1.11 and they're both /24 networks, I have to have a router in between them to get from one to the other. I can validate that I know who my gateway router is with the show IP route command. Or maybe I need to have a static route to get to that other network, whatever craziness that might be. More than likely, my vCenter server and my NSX manager are going to be on the same network. They'll be in the same VLAN, the same subnet, proverbially, figuratively right next door to each other. So I can use show ARP on the NSX manager to make sure that I am indeed resolving the IP address that I know for my vCenter server to a valid MAC address. And then I can take that MAC address and go back and validate that that is indeed the vCenter server MAC address. I can also look in the log file, show log, right? Show log. Show log is how we look at the log files in NSX Manager. And then there are a couple of different logs we could look at. In this particular case, we want to look at the manager log. So show log manager. And then if we look at the last part of that command, show log manager follow. Follow tells me to display the log and then update the screen as new log entries are written to the log. So here we see a log message, cannot connect to HTTPS, right? vc-l-01a-corp.local. Connection was refused. All right, now I've got something going on. Is there a firewall between me and vCenter that that is actively rejecting connections on port 443? Are my web services on vCenter server not running yet? What's going on, right? Now I have something I can go investigate. We could get to a point where maybe I want to do packet capture. Maybe I want to capture all of the packets that are coming out of my NSX Manager to make sure that traffic is getting to NSX Manager and maybe even coming back from NSX, or getting to vCenter server and coming back from vCenter server. I can use the debug packet command for that, right? And what debug packet is going to do, that's the packet capture command in NSX Manager on the Edge Services Gateway on the Logical Router Control virtual machine. And I can debug packet. I can send the packet debug either to a capture or a PCAP file that I can then copy off and look at it and say Wireshark or something, or I can show the packet debug to display where it shows up kind of like what we see on screen here. I define the interface, right, with the keyword interface. The interface name on the NSX Manager is management MGMT. And then here we're filtering out everything that is not port 443 or port 80 traffic. Right, so that's all we're looking for is 443 and 80. TCP4, or well, not TCP, anything on port 443, anything on port 80. That's all we're looking for. And this will give us what we need. And if we see traffic on this, we know that vCenter and NSX Manager can talk to one another or can communicate with one another. We already kind of mentioned the log files. We're going to mention them again. I can look at the log files, but what if I need to collect all the log files? From the NSX Manager UI, I can come in here and hit this download tech support log button. And that's going to collect a tech support log bundle in NSX Manager that I can then download to my local computer through my web browser. We can also use the support bundle tool in the vSphere web client. But if I'm still having trouble getting NSX Manager and vCenter to talk to one another, this is not going to be an option. But if everything is connected, then this is actually a pretty good option because I'm not limited just to my NSX Manager logs. I can also pull logs from my hosts or my controller nodes or my edge services gateways or so on. Now, what am I going to look for in the logs? Why am I going to look for logs? What am I going to get into? Well, here we're kind of showing heart beating, right? NSX Manager and the ESXi hosts heartbeat back and forth so that they can maintain some level of synchronization. And we can see in my NSX Manager log as well as in my host logging when that synchronization breaks. So the heartbeats all have a sequence number to them. And we're going to log, hey, we received a heartbeat with this sequence number. We received a heartbeat with that sequence number, and on and on and on. But we're also keeping track separately of what the sequence number should be. If we receive a heartbeat that has a sequence number that doesn't match, we're going to let you know. This will be all over your log messages, both on the ESXi host and on NSX Manager. And what's going to happen when we receive something that's out of sync, that's a wrong sequence number, is the host will then, I'm starting in the wrong spot. NSX Manager will tell the affected host, hey, you need to request a synchronization. And then the host will in turn request a full synchronization from NSX Manager. NSX Manager will send everything again back down to the ESXi host. We'll kind of remark the sequencing and we'll start over from there, right? I don't anticipate that this should happen terribly often, but heartbeats tend to be lower priority, so it could very well happen. NSX Manager, if you're looking in the Web UI and the Networking and Security plugin, if you go to Events, you can go see all of the different events that are logged in NSX Manager. If we go to the System Events tab, we can see all of those. And these are going to be things like, as we're showing here, firewall rules applied, backup of NSX Manager failed. We can get into, we'll see all kinds of other things here. If my message bus fails, we'll get a messaging infrastructure down on host message that shows up in my system events and on and on and on. So this is where we want to go for our events, what's going on in NSX Manager. This is where we will find those. I can back up and restore NSX Manager. This is not a terrible idea. I'm going to back up NSX Manager to an FTP or an SFTP destination. Your choice as an administrator. I can turn on a schedule. I can schedule daily, weekly, or monthly, and that'll automatically back up whenever I tell it to. And I can choose exclusions for the backups. We can see the backup history. I can then also do an ad hoc backup. Maybe I'm going to do a backup before I upgrade NSX Manager, for example. Now, this is going to bring us into not one, not two, but 3 consecutive labs. The first lab, Lab 2, we're going to review the NSX configuration. We'll go around, we'll look around the central CLI, validate my vCenter server and NSX Manager registration, make sure all of my licensing is valid, do some basic checks on the NSX management plane. Lab 3, troubleshooting scenario. This is where we will start running the break scripts. And if you look through the lab manual, there is on the desktop of your, on your lab desktop, there's a NSX troubleshooting menu.ps1 shortcut. Right-click on that and select Run with PowerShell. To run the break script, this is Lab 3. You will type the number 3 and press Enter. It'll fire off the script and off you go. You'll wait a couple of minutes. It'll say, hey, I'm ready to go. In Task 2, we will walk you through validating the symptom. Right? Task 3 is where you go in and you fix the problem. And then Task 4, you validate that the problem is fixed. Now, something I will recommend fairly strongly in these troubleshooting scenario labs is whether or not you actively fixed the problem, whether the symptom is gone and you think you've got it, run the repair script at the end, right? So the last thing you do as you're wrapping up task number 4 is just run the repair script. That way that resets, completely resets the brake so that it's not going to potentially rear its head later on. So this is always a good idea, especially in cases where maybe there's a symptom that could have multiple problems, or a problem that has multiple ways of fixing it. So at the end of each troubleshooting scenario, I do strongly recommend that you run the repair script that goes with it. And you do that in the same troubleshooting menu that you ran the brake script. In this case, instead of just typing 3 to run the script, type R3 to run the repair script. And then off you go, right? Once you're done with that, you can move on to Lab 4, which is a very similar type of scenario, or a situation, not scenario necessarily, where, again, we're going to run a brake script. We will run the Lab 4 brake script this time. And then Task 2 will verify that that particular brake has actually occurred. You'll troubleshoot and fix the problem. You'll verify that you've fixed it, right? We'll walk through in Task 4, just like the other troubleshooting labs. And then you probably ought to run the repair script here just to make sure. Reviewing the learner objectives. What did we get through here? Once we got through all of this and got through the labs, we looked at NSX Manager, deployment problems. We talked about communication between NSX Manager and vCenter Server. We talked about connectivity problems and so on, right? So we've covered a good number of things here. Lesson 3, troubleshooting the control plane and the NSX controller cluster. So what are we going to do here? We're going to get into the controller cluster. We're going to talk about how the controllers communicate with one another and how you deploy the controllers and how you validate operational states and things like that. We're going to talk about some common controller deployment, both during deployment and post-deployment issues that we may run into. We're going to get into communication channel health and talk about the controller log files a little bit. So a lot of ground to cover here. So here we have our management control data plane diagram again. We're highlighting the control plane because that's where we're focusing in this lesson. The controller cluster, what does it do? Why do we have it? We talk about the control cluster typically in storing the runtime state of the software-defined network. But what are some of its characteristics? Well, let's just go down the list we have here. The control plane is almost entirely housed in the controller cluster. So the controller cluster is kind of what makes up a significant majority of the control plane. It's provided by a 3-node cluster of controllers. So I have to deploy 3 controller nodes. We need 3 for majority. We need 3 for high availability. Frankly, we need 3 to be in a supported configuration. So that's something to think about. But not any one load or not any one controller is necessarily going to be overloaded compared to the others because we do distribute the workload across the 3 nodes. Each controller will be responsible for one or more logical switch, what we call slices or shards sometimes. We'll see that the 2 terms kind of thrown about a little bit. So the controller nodes are responsible for some of my logical switches and some of my logical routers, right? Each given node. All 3 of the nodes combined, the controller cluster is responsible for all of them. It learns the topology, the layer 2 and layer 3 topology, the controller cluster. When we talk about a controller being responsible for a logical switch slice or a logical switch shard, part of what that means is for that logical switch, a given controller will maintain a VTEP table, or a table that just lists all of the VXLAN tunnel endpoints involved in that logical switch, an ARP table, and a MAC address table, right? The MAC table just maintains a list of all of the MAC addresses of the virtual machines attached to that logical switch, and the ARP table contains the MAC to IP mapping of all of those virtual machines. Now, the ARP table provides for a really cool capability in the control plane. If we look down the list, we mentioned reducing ARP flooding through ARP suppression. Well, we can do that ARP suppression because we maintain that ARP table. So the ARP table gives us a central place to intercept and make ARP queries instead of flooding the ARP query across the entire logical switch. That's done through a piece of software installed with the rest of the data plane components called the switch security module. So that's installed in line with the between the virtual NIC and the logical switch. When an ARP request is sent from the virtual machine, the switch security module will pick that up and will query the controller node. Will query the ARP table on the controller node to say, "Hey, can you make this ARP mapping for me?" And if that's the case, then the controller will respond to that switch security module, and the switch security module will then respond to the guest operating system, the virtual machine itself. So we don't have to flood an ARP request, right? The ARP request still happens. It's simply a unicast through my control plane rather than a broadcast across my logical switch. Makes a big difference in some environments, but how much of a difference it'll make will naturally depend on how many virtual machines are on a given logical switch segment and how much ARP traffic they generate. But it's a really, really cool feature. The distributed logical router also, or the controller cluster, a given controller node, when it's managing a slice for a distributed logical router, will maintain a LIF, or a logical interface table, which just documents out what logical interfaces are attached to that logical router. It'll maintain a LIF table. It'll also maintain a routing table for that distributed logical router that will then be propagated to all of the ESXi hosts. And then having that central control plane, that virtual appliance-based control plane, minimizes, or not minimizes, but reduces, or not even reduces. There I go, minimizing and reducing something that we're removing altogether. Removes altogether the need for multicast potentially in my VXLAN transport, right? So very, very brief recap. VXLAN is documented and standardized in RFC 7348, and it documents VXLAN, which we use for our logical switching, documents that out as a multicast flood and learn control plane, which means VXLAN requires multicast in my physical network. The RFC also allows for a centralized control plane as we've deployed. And what we did in implementing that centralized control plane is included things like the VTEP table. So we have at the central control plane a list of all of the all of the VXLAN tunnel endpoints involved in a given logical switch, so that we don't have to multicast. That's used in both our unicast and hybrid replication modes, which we'll go over elsewhere in this course. So we don't need necessarily multicast for our physical transport any longer. We may, depending on how we've got things set up, right? There are lots of options going on there. But the control plane, the key here is the control plane is the piece of the puzzle. The controller cluster takes away that VXLAN requirement in some deployments. So again, elsewhere in this course, when we start diving into logical switching and VXLAN a little more deeply, we'll talk more about that. So how do we deploy a controller cluster, right? What goes on? How do we go in and do this? Well, deploying a controller cluster through the NSX Manager UI, through the networking and security plugin in the vSphere web client, piece of cake, right? It really is. I click on an Add Controller button, and I get a quick window to fill out some information, and I hit go, right? So we deploy a controller, right? We fill out that dialog, give it a controller name and what cluster I want to deploy the controller to, and some other identifying information. And NSX Manager talks to vCenter Server to actually deploy a virtual appliance, right? Again, we're using OVF, the Open Virtualization Format, to do that. And as part of that, we're also sending vCenter an OVF client configuration payload along with the virtual appliance files, and we're deploying that and configuring the IP address. We're configuring pre-shared keys for IPsec, for controller-to-controller connectivity. We're configuring passwords. We're configuring public and private keys and controller IDs and all kinds of things, right? We're taking all of this information and packing it in and configuring it in the controller node. Once that's all done, then the NSX Manager starts trying to communicate with the controller over a private set of APIs, right? We start calling APIs against the controller. So this is actually the commonplace, just to go on a brief tangent, this is the common place where controller deployments will fail because maybe I've got an IP address misconfiguration or something like that. I mistyped an IP range in my IP pool, or I mistyped a gateway or something like that, right? Oftentimes, this is where we'll see a failure. There is, on step 4 here, this will take about 20 minutes to time out if there is a connectivity problem, at which point the controller will simply be powered off and removed, and I'll have to go fix whatever the problem was and try again. So anyway, let's continue talking about this as though it's going to be successful. So we're going to make these API calls. Once the controller is up and running, these API calls will be successful. Should only take a couple of minutes. And off we'll go, right? Once the cluster is created through these API calls, then we need to go back through the networking and security UI and deploy 2 more clusters. And that's done serially, right? I have to do them one at a time. So I'll deploy controller 2, and then I'll deploy controller 3. And when I deploy each controller, what's going to happen? We're going to go through the user deploys controller workflow. The NSX Manager will work with vCenter to deploy the virtual appliance. We'll send the configuration information with all of the same stuff outlined in step 3, and off we go, right? The NSX Manager will communicate with the other 2 controllers to join the controller cluster, and once the 3rd controller is deployed and the cluster has been joined, then we're done, right? Then we're done. So everything's pretty good there. Now, we can watch all of this. In the NSX Manager log, we can actually watch and track the progress of our controller deployment, right? We can do a show log manager, probably a show log manager follow if I'm trying to track the entire process. And we'll see things pop up about to create a controller, deploying virtual machine, and then the controller name, controller deployed successfully, powering on virtual machine, successfully powered on, right? Again and again and again, right? These messages that are highlighted in yellow. Now, something I will note that is that you're not going to see all of this in a nice, compact log output like we're showing here on the screen, right? If you look at the log output, you'll notice that it's truncated. We've got sections kind of broken up by a series of hyphens in the screen that kind of shows other spots where we've truncated output. So just be aware, there's lots of stuff going on in the NSX Manager log. These are just some of the keys you might look for to be able to track your controller deployment process. So once we've got the controllers deployed, through the networking and security UI, if we go to installation and upgrade, and then the management tab that's shown, we can see our controller nodes, right? We can look at this here. I've got controllers 1, 2, and 3, and they're deployed. We can see the IP address in the controller node column. We can also see the controller ID. So controller-1, controller-2, controller-3, and the name, that's just the name we assigned the controller. The actual controller ID is listed along with the IP address, right? We show you which NSX Manager they're registered with. Status, hopefully the status column is green check marks across the board and everybody's connected. And then I should see two of these little green squares in the column following that. What this is telling me is my peer connectivity status. So controller 3 has two green dots. That means it can communicate. It's got a solid communication channel with controller 1 and controller 2. Right? Controller 2, two dots. Controllers 1 and 3 are successfully connected, and so on. Right? So this just shows me that everybody's connected, everybody's happy, everybody's in good shape. From the NSX controller command line, right, I can SSH into an NSX controller. From the command line, I can use the show control cluster status command to see what the status is. And here we've got some things highlighted on the screen. Join status, right? Join complete, that's a good thing. Connected to cluster majority, that's a good thing. We have a cluster ID and a node UUID. In this particular case, if we look at the cluster ID and the node UUID, they're identical. What does that mean? That simply means I'm looking at the first controller that was deployed, right? That's all it means. The NSX controller cluster ID will be taken from the first node's UUID. And then down near the bottom, active cluster members, we see I've got 3 active cluster members, which is a very good thing, right? I need 3 controllers. I can use show control cluster history to see exactly what it says. I can see a history of what has been going on in the controller cluster for this particular node. So we can see when it joined, when it connected to the majority, et cetera, et cetera. So this is a good command just to have in your pocket if you're curious about what might have been going on with the controller cluster for a while. So just to kind of wrap this all up, we talked about the controller cluster deployment process, and we talked about how to validate the controller deployment right through both the UI and the CLI. So what can go wrong during an NSX controller node deployment? Quite a number of things, actually. I could run into cases of I don't have enough disk space in the data store. I'm trying to deploy these to, or my IP pool could be misconfigured, right? Maybe when I was configuring out my IP pool, I had a typo in my gateway, or a typo in the IP pool address that could trigger a duplicate IP address or something something terrible to track down like that. I could have a corrupted controller virtual appliance file. Not likely, but I could. Not going to rule it out. Some kind of IP connectivity problem otherwise, right? Maybe everything is configured properly, but maybe my NSX manager and my controller nodes are on separate subnets. I could have everything configured right, but if I'm blocking, say, TCP port 443, our API calls are going to fail, and it's going to look like I have no connectivity. So maybe there's something else going on. Could be a DNS or an NTP problem, right? I'm sure you've heard us talk about DNS and NTP and their importance for NSX before. We're going to talk about it here again, right? So those are problems we might run into in actually deploying NSX controller nodes. While I don't know what your experiences have been, my experiences have been that more often than not, we've got a misconfiguration in an IP pool. That's just the easiest human element to to make a mistake on, right? So you keep that in mind though. There are a lot of things that could potentially go wrong. What about after we've deployed? Well, things could go wrong after we've deployed the NSX controllers as well. How about my controllers going offline for some reason? How about my controllers going away, right? Could have a data store failure that wipes out all of my controllers. I could just have an ESXi host fail that has a controller node on it that takes that controller node down. We might run into disk latency problems, right? These 3 controller nodes are clustered together, and disk latency is actually a thing to worry about because they do share information. They do go back and forth with their information. So it's sort of important that disk latency is reasonable in the environment, so that the controller nodes themselves don't get out of sync. So there are a number of things that could go wrong after the fact. Now, insufficient disk space. I'm trying to deploy a controller node to a data store that doesn't have enough disk space. It's a fairly obvious failure. Once we see it, we get errors in vCenter server. We get errors in the NSX manager log when we're trying to track the deployment thereof, and they all very explicitly say insufficient space on data store, whatever data store you're deploying to. Chances are this is just going to happen because you inadvertently chose the wrong data store, but maybe there's just a storage problem. Maybe you're just that tight on storage in your environment. That could happen. Who knows? Intercontroller connectivity. Right, my controllers, those green dots that we were talking about, that we show in the status of the controllers that we're showing up here in the right-hand corner, the upper right-hand corner of the slide. Well, how do we validate what we're showing there? Well, from an NSX controller, I can type the command show control cluster network IPsec tunnels. That's it. Show me the IPsec tunnels. The controller nodes build IPsec tunnels between them for secured communications. If there's something wrong with one of those tunnels, that green dot will turn red. In this particular case, we have a controller powered off. I can't establish an IPsec tunnel to a device that's not there, so we are naturally going to show problems here, and we can see that in the show control cluster network IPsec tunnels command by simply looking through the output and seeing, hey, we only have a single IPsec tunnel established in the controller cluster, right? So we can validate that. If I have a controller failure, what happens? If I have a controller failure, what happens? Well, a single controller node, I'm simply in a jeopardy state, right? This is my HA kicking in. One controller fails, the logical switch and logical router slices and shards are redistributed to the surviving two controller nodes in the cluster, and everything continues to work. I obviously want to bring that dead controller node back to life as quickly as possible. Maybe this was caused by an ESXi host failure, and all I have to do is wait for vSphere HA to kick in, or maybe there was something catastrophic about this particular failure, and I have to deploy a new controller. Either way, I really want to get another controller brought back to life. If my controller is still in existence, I can reboot the controller either by logging in, SSHing into the controller and running the restart controller command. I can also reboot by simply right-clicking on the controller in my vSphere client or vSphere web client and restart controller. Restart controller does for us just a services restart. Right? That just restarts the services in the controller. So one controller failure out of 3, not a big deal, right? Not a big deal. I still want to resolve the issue, and I want to come back to three controller nodes in my cluster, but it's not the end of the world. 2 controller node failures, well, still not the end of the world. This is not a catastrophic failure of your NSX infrastructure. However, this will take the control plane offline. Once I lose 2 of my 3 controller nodes, my cluster majority goes away. When my cluster majority goes away, the control plane kicks itself into a read-only mode. However, the surviving controller node also disconnects all of the other connections and starts refusing reconnection attempts. So the 2 controller losses effectively takes down my controller plane, or my control plane, not my controller plane, my control plane. So what do we need to do? Well, I need to bring those 2 controllers back online. If it was simply 2 hosts failing or a host failing that had 2 of my controllers co-located, then I can simply restart those controllers and bring my cluster back to life. If it's not that simple, then let's go ahead and delete all the controllers and redeploy them. someplace that is going to stay up. That's really the good answer there. Once my control plane has failed, so once 2 of my 3 controller nodes have failed, this is a point where I probably want to scramble to action to return the controller cluster to service. It's just really a thing. Now, if my control plane has failed, if my control plane is no longer existent, my data plane does still process based on its last known information, right? Everything still runs based on what we knew. So this is not a catastrophic failure as far as my software-defined network is concerned. But if we localize that discussion to the control plane, then yes, I've just had a catastrophic control plane failure. I need to fix that. But my virtual machines are still going to cruise right along, right? They're still going to pass traffic. They're still going to get where they need to go. Everything's still going to be okay. If I do have to destroy all of my controllers and rebuild them, once my controller cluster has been rebuilt in my management UI under installation and upgrade in my networking and security plugin, I want to select my NSX manager and select under actions update controller state, just to force a resynchronization of the NSX manager and the NSX controller cluster so that we can continue on with a solid and freshly synchronized control plane. Right? This is not a bad idea at all. Now, we mentioned a little while ago that disk latency could be a problem. We can actually select a controller node in my networking and security UI and select the fetch disk alerts option under actions, and we'll get a list of disk latency. Disk latency being high or low is going to vary relative to your particular environment. But once we start seeing high double-digit latency or, heaven forbid, triple-digit latency numbers, I probably want to think about something. Right? We will see alerts in the dashboard if NSX Manager thinks the disk latency is getting a little too high. How do we fix that? We need to clear contention for my controller nodes. Our quick and easy recommendation is simply put a dedicated LUN in place for your controller cluster. So, what did we talk about? We talked about controller failures, right? 1 controller, 2 controllers. A 3 controller failure would have a very similar effect to a 2 controller failure. So we didn't actually detail that. And then we talked about finding disk latency issues. So a couple of really cool things about the controller. Now you kind of know some of the common problems. Things should be good from here. So the control plane in NSX can fail. How do we deal with that? Well, we have a feature that was actually introduced in NSX 6.3 called CDO mode, or Controller Disconnected Operation Mode. And as we see here on the slide, this kind of sets up a what we term here in the command line a control VNI. This is sort of a hidden logical switch that we force everybody to join. So CDO mode, what its ultimate goal is to reduce application downtime. So when my control plane fails, when my control plane goes offline, we can get into a situation where maybe virtual machines will lose connectivity because they're moving to a host whose VTEP has not joined that logical switch or that VNI yet for one reason or another. So CDO mode kind of protects us against that by moving sort of a backup, if you will. That's not quite a precise term, but kind of moves a backup of that VTEP list for all of the VTEPs in my NSX domain into down onto the ESXi hosts that we can use. So we can enable CDO mode. One of the big enhancements in NSX 6.4 is this is now enabled at the management plane layer. So we enable CDO mode on not on a controller, but on the NSX manager. And off we go, right? Then we get to see the little checkbox that says CDO mode has been enabled. So what happens, right? Let's talk about this control plane failure and where I might have trouble or where I might run into trouble without CDO mode, and then we can see why CDO mode is sort of important. So here I have a case of 3 ESXi hosts in a cluster. I have web server 1 and web server 2 on host 1 and 2 respectively. All 3 hosts are configured for VNI 10,000. My controller cluster is talking to all 3, or is able to talk to all 3 hosts. But when we look at our VTEP table on, say, host 1, right? When we look at the local VTEP table on host 1, it only shows us one VTEP. It only shows us the VTEP for host 2. Now, why is that? Well, that's because host 3 does not have any virtual machine running on VNI 10,000. So so host 3 has not joined VNI 10,000 yet, right? So it's not in the VTEP list. It's not actively participating at this point. It's not a big deal. It doesn't have any virtual machines. I'm not worried about it, right? But here we've got a case where I have a control plane failure. That control plane failure is localized to host 1, right? So somebody logged in and stopped NetCPA. Here we show that NetCPA crashed. Maybe that could happen too. But the control plane on host 1 has failed. So we look at the VTEP table on host 1. VTEP table on host 1 only shows host 2. And it's going to continue to show host 2 because we're not, even if the control plane is down, we're not flushing out all of that information. We're maintaining the last known information, for better or for worse. Host 2, well, let's skip host 2 for a minute. Let's jump over to host 3. Host 3, while the control plane on host 1 has failed, we've instantiated a new virtual machine, web server 3, and we've put that on host 3. Now, host 3 joined VNI 10,000. No problem. Host 3's control plane is still up. So when I look at the control plane, or if I look at the VTEP table rather on host 2, then host 2 will show the VTEPs for host 1 and host 3. Host 2 is also still connected to the control plane. So VM2 is able to talk to VM3 because we can do some ARP suppression, we can do some broadcast, we know where the other VTEP is, everything's great. But web server 1 doesn't know where web server 3 is. Host 1 doesn't know how to get to host 3 or to web server 3 because web server 1 doesn't know that there's a new VTEP as part of the VNIs. So host 1 won't communicate with host 3 over VNI 10,000 at this point, right? This is sort of a problem, isn't it? Now I have virtual machines that can't talk to one another because of a simple control plane failure, which is where CDO mode comes in, right? What CDO mode does is it creates this control VNI, this kind of hidden logical switch that, and we force, when we enable CDO mode, we force all of the ESXi hosts that particular NSX manager knows about. We force all of them to join this control VNI, this hidden logical switch, so that we have this global VTEP table, essentially, that we can use in the case of a failure. Now, we're not going to use this until we absolutely have to, but it's there when we need it. So when host 1 loses its control plane, CDO mode is there so that when we try to get from VM1 to VM3, while we can't do any ARP suppression, we can still flood to a VTEP that we didn't know was previously a member of this logical switch, right? Because we'll flood to everybody in the control VNI. So we can actually look, we can actually see this. So let's look at some VTEP tables when CDO mode is enabled. Here we're on ESXi01, host 1. Right, my control plane has failed. Right, my control plane has failed. So we look and we see a VTEP, a single VTEP in the VTEP table. And that's the VTEP for host 2 that we already knew about. We don't know anything about host 3. We don't know anything about virtual machine 3. But if we look at the CDO VTEP table, then we can see, hey, look, there's 2 VTEPs in there, right? Host 2 and host 3 are part of the CDO VTEP table, which means now when we try to ping, the ARP can be flooded across the to all of the VTEPs. VM3 can then, web server 3, 172.16.10.13 can respond to that, and then VM1 can talk to VM3. Everybody is ultimately happy, right? Functionally, things work just fine. So we can actually see some of this, and if we set the VDL2 kernel module to a trace logging level, we can actually see when we are replicating to the global VTEP list. Right? It's not logged anywhere normally, but if I change the logging level to trace, which from the host command line is log level 10, using the netvdl2 command, then we will actually see in the VM kernel log that we are able to replicate to the global VTEPs, right? Again, non-default logging level. And when we're done, turn the logging level back, right? If you're done looking at this, turn the logging level back. So, quick wrap up. We talked about what CDO mode is, what it does. We talked about some use cases and some behaviors and different scenarios in which CDO mode is useful. So you can make your choice there, whether or not you want to turn on CDO in your infrastructure. What happens when netCPA fails? When the control plane process, the control plane agent on an ESXi host, what happens when that fails? Hopefully nothing. And when I say hopefully nothing, I mean hopefully nothing that's observable. There has been a lot of work put into the netCPA agent, the control plane agent on the ESXi hosts to mitigate any potential impact from that failing, or mitigate it failing at all in the first place, actually. So there are a number of things going on here. One, there's a watchdog mechanism that's in place, right? So if the netCPA service is running, there's a watchdog paying attention to it. If the watchdog sees the service fail, the watchdog's going to restart it, right? Total outage time, let's call it a second, right? I haven't timed it, but it's not long at all. So probably not observable, right? Probably less than a second, probably not observable. The control plane is going to keep on going. Everybody's going to be happy. It's just going to keep cruising. We've also plugged into the control plane agent a heart beating mechanism. And what this heart beating mechanism is, it's a heartbeat between the netCPA process and the host system itself, the ESXi host itself, that allows us to tell if the netCPA process has just kind of hung, right? We talk about it here about, we can detect a deadlock situation. If the process has simply hung, we can see that. We can identify that. And if we get into that situation, right, where we stop receiving heartbeats, what's going to happen? Well, yeah, my control plane may be offline for a little tiny bit longer, but we're going to generate a core dump and then restart netCPA. Right? We'll have that core dump just in case you need it, just in case you open up a case with support. And they say, well, give us the core dump so we can see if we can debug why it hung up in the first place. We will see that backtivity located in a syslog message on the ESXi host, right? But this is a host-specific logging. Now, when it comes down to it, even if these things are happening, again, we're not going to notice, right? The control plane is very resilient. The control plane will If it fails on an ESXi host, again, we're not going to flush anything, any of the information on the host. We're going to know what we had just a second ago before NetCPA crashed. Chances are it hasn't changed in the next couple of seconds while we're fixing NetCPA up. We'll automatically restart, we'll automatically resync, we'll automatically go back to work, and you shouldn't notice a thing. But you could, you could get into a situation where maybe NetCPA is just dramatically broken and it's constantly restarting, and then I have to certainly evaluate what's going on there. If you want to see what we show in the logs, in var log syslog.log, right, on the ESXi host, that is the log file that we will watch, or not watch, but that's the log file we will watch to see the NetCPA watchdog stuff. And you can see that there are some NetCPA messages in here. There are some watchdog NetCPA messages in here. So you can actually see in this particular example, right? Monitor looped last 1,700 times. The last 100 loops checked 100 times, right? Everything's chugging right along. Everything is perfectly happy. Everything is great. Nothing terrible is going on, right? I like to see repeats like that because that tells me that my heartbeats are going and my NetCPA process is working. My watchdog looping is going. It's all happy. But then we see an error message. Watchdog NetCPA. NetCPA exited after 162,000 and some odd seconds. That's a problem, right? NetCPA exited. It stopped. It was killed. It crashed. Whatever reason, it's no longer running. And then we see, immediately after it logs that, executing NetCPA. Right? We're starting it back up, so we can actually see when the watchdog does what it does in syslog.log. Now, the controller cluster has to communicate with NetCPA. It does that over a TCP connection using TCP port 1234. That channel is securely managed. It's SSL encrypted. But what else do we see here? We see a bunch of other stuff, right? So NSX Manager talks to the controller cluster. That's over a set of REST APIs. That's TCP 443. NSX Manager communicates with VSFWD, the message bus agent, the management plane agent on the ESXi host. We have an SSL encrypted message bus connection. That's TCP 5671. NetCPA is bootstrapped by and heartbeats to NSX Manager, but NetCPA can't communicate directly with NSX Manager. So we proxy that connection by way of the message bus agent. So there's a TCP connection inside your host between NetCPA and VSFWD, and that TCP connection for the proxy is TCP 15002. Right? So this gives you a nice overview, a diagram of what's talking to what, and what ports and protocols they're using to communicate. This is actually a really, really nice diagram. The NSX controller has a number of log files, a lot of log files, right? You can log into the controller and type show log and hit the question mark, and holy cow, you're going to get a list of logs. Some key logs to think about: CloudNet Java VNet controller, CloudNet Java Zookeeper, CloudNet CPP log, CloudNet NVP controller log. These are just different logs for different components and applications inside the controller node that contain a lot of useful information. If you look at the NSX troubleshooting guide in the documentation, right? If you go to docs.vmware.com and find the NSX documentation, one of the books in that documentation set is the troubleshooting guide. The troubleshooting guide will talk about some very useful logs that you might look at. The Zookeeper log, for example, will show you things like disk latency alerts, because that's where the latency is actually a very critical piece. So these are some log files that you may want to keep an eye on. You can configure the controller nodes to push data to syslog, and then all of this data would be in your syslog collector as well. So let's take this into a couple of labs Two labs, 5 and 6. In lab 5 is a pretty short lab. We're going to verify that the control plane works, right? Quick, short, sweet. We're going to log in, we're going to poke around the control plane a little bit and see what we see. Everything should be working, I hope. In lab 6, we're going to go through another troubleshooting scenario. So again, we're gonna right-click on the troubleshooting menu script on the desktop and run that with PowerShell. We're going to press the number 6 to run lab 6, to run the script for lab 6. Task 2, you'll go through and verify that the system is indeed broken. Now, this troubleshooting lab kind of deviates a little bit from the previous troubleshooting labs in that we have a third task. That third task is to use log insight to actually identify the problem. So we're breaking the system, we're validating that the system is broken, and then you've got a task here in the middle that will lead you in log insight specifically to the problem, right? But the idea here is that we want you to start thinking about leveraging vRealize Log Insight as a tool to manage your log messages and see the value of how do we identify things that are broken when they're in the logs. So we're going to lead you right to the problem. So task 4, where it says troubleshoot and fix the problem, task 3 sort of spells it out for us, right? What is the problem? And that should be, it should give you a pretty good idea of how to fix the problem. Task 5, let's just verify. Let's make sure it's fixed. And then once it's all said and done, again, run the repair script just to get in that habit here. So open up the troubleshooting menu script again and type R6 and hit enter, and you should be in good shape. So what have we gone through here? We've talked about the controller deployment. We have looked at the operational status of the controller. We have dug deep into that. We've looked at communication between the controllers. We've talked about common problems in deploying the controllers, both before and or not before, during and after deployment. We've talked about log files. We've talked about communication channels, right? Gone through a lot of stuff here. Lesson 4, troubleshooting host preparation. So what are we going to do here? Here we are going to dive into preparing the data plane of NSX. We're going to talk about the VIB, the bits that we're installing on the ESXi host. We're going to talk about how we get those bits installed on all of the different ESXi hosts, which means we're going to talk about a thing called EAM, or the ESX Agent Manager. So we're going to get into that. That's a vCenter component that we rely on pretty heavily in NSX. We're going to talk about from the ESXi host problems connecting and working with the management plane and problems working and talking with the control plane. So we're going to see some things kind of go back and forth there a little bit. We're going to talk about logs and the UI and how to use some of those things to troubleshoot these problems. So there's our management control data plane diagram, and notice here we are down at the bottom of the list. We are in the data plane. We have made it through the management plane and the control plane, and now we're off to the data plane. So before I prepare my cluster, before I get my hosts ready to go, I naturally am going to need NSX and vCenter to be working nicely together, right? At this point in the process, I should have NSX Manager deployed and registered with vCenter. I should probably have my controller nodes deployed. At this point, making sure that my host is registered is likely a moot point, but it's a good double check, right? This tells me that things are in good shape and relatively healthy. So host preparation is all about installing VIBs, or VMware Installation Bundles. A VIB is simply our package format, right? If you're familiar with other operating systems, they all have some kind of package management format that they use. Whether it's a .msi in Windows, or a .deb, or a .rpm, or something like that on a Linux system. They've all got their own different package management system. That's kind of what a vSphere VIB is. So we've got these different, this VIB that we install that contains all kinds of different things, and that's all installed through a function of vCenter server called EAM, or the ESX Agent Manager. And what EAM does is EAM creates basically a profile, right? What we call an agency in the EAM context. It creates a profile around a cluster object in vCenter, right? So it works at the cluster level of granularity, and we apply this agency to a cluster so that we can then check all of the ESXi hosts in that cluster to see if they match some baseline set of configuration, right? In the case of NSX, is the NSX VIB installed, and is it up to date? So we'll validate that, and if any of the ESXi hosts are not in compliance with that, EAM will ensure that the VIB gets pushed to the host and installed so that that host is then in compliance. So what does this process look like? Well, I go in and I prepare my cluster, right? So I go into the NSX Manager UI, I go to Installation and Upgrade, I go to Host Preparation, and I find a cluster that I need to install NSX on, and I hit the Install link. NSX Manager then is going to reach out to vCenter Server over its private API set and say, hey, I need you to create this agency. I need to get this agency created. This is the stuff that needs to be in the agency, and let's go do the things. vCenter Server at that point will then reach back to NSX Manager and download the VIB and cache it locally, right? That VIB name is ESX-NSXV. So we'll cache that VIB locally, and then EAM will start doing its thing, right? EAM picks up and starts working now. So EAM will scan all of the hosts in the cluster using the vCenter Patch Manager function, right? vCenter Patch Manager is not Update Manager, although it will integrate with Update Manager if you're using Update Manager. Patch Manager is still kind of a separate component. And it's going to go out and scan all of the ESXi hosts in the cluster. When it finds hosts that need what we call enhancements, right, things that don't meet the agency description, then EAM is going to tell the host, hey, you need to go download this VIB, right? You need these things so that you look like everybody else. So what's going to happen there is ESXi is going to use the ESX update framework in the local ESXi host to reach out to vCenter, right? Because we're going to point to the cached VIB at vCenter. It's going to download the VIB from vCenter and install it using the ESX update mechanism in ESXi. Right? Once that's all done, then the scan will happen again, and we'll say, oh, look, you're just fine. Great. Have a nice day. Now, just because we have installed the VIBs doesn't mean we're done. Right? There's more that's going on here. So these VIBs, or this VIB rather, includes the management plane agent, VSFWD. But VSFWD doesn't know where NSX Manager is at this point. We need to get that information from NSX Manager to the ESXi host. So NSX Manager sends to vCenter Server a set of advanced configuration options, right? ESX config, advanced config options. And sends three of them, right? The RMQ IP address, RMQ username, RMQ password. This is a temporary username and password used as we're bootstrapping the message bus agent, so we're not going to use these long term. So we're going to send those to vCenter Server. vCenter Server will then send those down to the ESXi hosts that were just prepared. The ESXi host, VSFWD on the ESXi host, looks at those variables, sees those variables, and says, oh, let me go log into the message bus at this IP address. When it does, NSX Manager will then say, oh, welcome aboard. Here's your specific credentials and any other message bus related information you might need right now, right? The certificates and et cetera. So we'll log in. Once we log in the first time, NSX Manager will start directly communicating with the message bus agent on the ESXi host, and vCenter's now out of that picture. But we've still got the control plane agent, NetCPA, to bootstrap. So how does that happen? NetCPA can't communicate directly with vCenter server. It can only communicate directly with the controller cluster. But the controller cluster doesn't exist as far as NetCPA is concerned at this point, because NetCPA has just been installed, right? It has no configuration at all. So NetCPA is going to reach out over the TCP 15002 proxy. It's going to reach out to VSFWD, and it's going to ask very nicely, hey, can you get some information from NSX Manager for me? And VSFWD says, sure, great, no problem. No problem at all. So VSFWD reaches out over the message bus and says, hey, Mr. NSX Manager, can you give me the configuration for NetCPA on this host? So that triggers a bunch of stuff, right? NSX Manager is going to reach out and push certificates and SSL thumbprints and things to the controller cluster. It's going to then return things like those SSL thumbprints and certificates and other configuration data. How many controllers do I have? What are their IP addresses? On and on. Back down to the ESXi host over the message bus. VSFWD will then pass that information over to NetCPA, where NetCPA will take that information and it will build a number of configuration files, right? It'll build the key files. It'll build the XML file that contains its configuration, right? The config by VSM.xml file. It'll configure all these, build all these things. And once we've got those built, it's going to, NetCPA is going to look at that config by VSM.xml file, and it should see 3 controller nodes listed, and it's going to pick one of those 3 controller nodes at random, right? You've got a 1 in 3 chance of picking the same controller that NetCPA does, and it's going to make a TCP 1234 connection, a control plane connection to that that controller node, where it's going to check the thumbprint and do some mutual certificate authentication to say, hey, I'm a control plane agent and I need to talk to the control plane. And then once that's done, NetCPA starts requesting updates from that controller and spawning connections to the other 2 controllers to ask them for updates and caching control plane information locally at that point. So here you can see it's been quite a journey to get from hosts not prepared to hosts prepared, bootstrapped, and attached to the control and management planes, right? There's a lot of stuff that goes on in this process, right? A whole lot of stuff that goes on in this process. Now, how can we watch some of this stuff happen? How can we see some of the logging of some of this stuff? Well, in eam.log, which on the vCenter appliance is located in var log VMware VPX eam.log, right? That's the ESX agent manager log. We can actually see the agency creation. Here we're highlighting, right? Creating agency eam.agency.config info, and this kind of kicks off where NSX Manager is creating the agency for us. We can go in and follow the logs as we are scanning and adding host system. We need to scan this, adding agency to this cluster resource, right? Vib scan for install. Let's go look. Do I have the ESX NSX vib installed on the hypervisors? What else going on there? Here we see some other stuff. Installing vibs on host. There's a vib ID with some information. Completed with result, install result, success result, done. Right? There's a lot of excess text in there, but we've highlighted the key messages we might want to look at. So just to kind of wrap this all up, right? We've talked about the host preparation process, and my, what a process that is. A lot of stuff going on there. And then we talked about how to kind of track that through the various log files. I can look at it through the host log, through the EAM log, a lot of different places. So ESX Agent Manager can fail, right? It happens. It's software. Software sometimes crashes. People shut down services. Who knows what's going on? So what happens? What do we do when EAM is down? Well, when EAM is down, NSX just can't know whether or not its clusters are prepared. So we get things like what we're showing here. The cluster is not ready. Well, it's not necessarily that it's not ready. It's just we don't know that it's not ready. If we click here for more info, right, we see the little link off to the side of not ready. We can click on that. That should bring up a callout box that may show that something has gone wrong. Something else we might see, and something that might be a little more obvious than just looking at not ready on my cluster list here under host preparation, is the fact that we have this EAM status here in kind of the header of the window, if you will. And that says, hey, EAM status, is it up or down? I want to see this green and up. But if it's down, we'll tell you about it. And it says to resolve, click here. Right? What that's going to do is that's going to take us into the correct vSphere web client UI location, where we can then find ESX Agent Manager, and then I can right-click on the actions on that and simply start, or whatever I need to do, probably just start the service. If EAM is up, this should be green. I should be happy. Under vCenter Server, if I go to Administration, and then VMware or vCenter Solutions, and go to the vCenter or vSphere ESX Agent Manager from there, and then select Manage, I should be able to see my agencies and see that everything is good, right? Green is good. We've got a status of green, normal, everything's happy, right? That's what we want to look at. And we're going to see one agency per cluster, per compute cluster. So here I've got VCNS 160 SA Management, VMware Network Fabric. So there's a cluster for my management. Cluster is prepared, as is my compute cluster, right? As evidenced by the second agency. Troubleshooting agencies, if NSX Manager shows that, or my host preparation UI shows that I can install the VIBs, then what we're getting into is a case of, if I've already installed, we're in a case of a deployment unit is not there. It's been deleted somehow. And this is actually really a case in a fresh cluster as well, right? There's no deployment unit there. So when we click that install link to prepare the clusters, in NSX Manager we create the deployment unit. In EAM we create the agency. Now we should be able to just resolve, right? And that kind of forces us to go back and forth and have NSX Manager and vCenter Server talk about their agencies and deployment units, so that they can kind of match things back up, right? Because we've got to map the deployment unit to the agency itself. Now, what if I need to manually install the NSX VIBs? This is a common thing if I'm using, say, vSphere Auto Deploy to deploy hosts into my clusters. Being able to download the VIBs and slipstream them into my image, or simply being able to download the VIB and it slips and manually install it onto an ESXi host. This is just something nice to be able to accomplish. So what I need to do is I need to figure out where this particular version of NSX Manager is storing those VIBs, because the path location of the VIBs is a little bit dynamic. In that it's going to change from version to version. Not that it's just going to change depending on the day, right? It's dynamic by version. And so what we're showing here is the output of the nwfabric.properties file in the /bin/vdn directory off of the root of the web UI of NSX Manager. So I can look at this by just pointing a web browser to HTTPS, my web browser ID, or my IP address rather, of my NSX manager /bin/vdn/nwfabric.properties. And I'll have to authenticate, right? We don't just give everybody access to this. You have to have your NSX credentials, a login screen will pop up. And then it'll just display this. And what you'll do is you'll go through this file and you'll look for the version of vSphere, the version of ESXi you want to install the VIBs on, and that'll give you the path to download the vxlan.zip file, the path location of the vxlan.zip file. So you can take that path, right? Notice it's /bin/vdn/vibs-something. You can take the path to that zip file and just replace the path in your browser and just do an HTTPS download of the vxlan.zip file that you can then copy to your ESXi host and with ESX CLI software VIB install, manually install that VIB. Once we've got it installed, we can validate that the VIB has been installed. ESX CLI software VIB get, right, tells the ESXi host to get the VIB, --vib name ESX NSXV tells us that we are looking for the specific ESX-NSXV VIB, and it gives us all of the content about that VIB, right? What version of the VIB, what does it contain, etc., right? What things are there. Now, when looking for the VIBs, when we get an error message about VIB inaccessibility, right? VIB inaccessibility. We got two different places where the VIB could be inaccessible, right? We could have a VIB accessibility issue between vCenter and NSX Manager, where vCenter server can't download the VIB to cache it. It also have a VIB inaccessibility between the ESXi host and vCenter server when we're preparing, right? Because the ESXi host will pull the VIB from ESXi. So what are some of the causes? Well, DNS. When we download the VIBs, we are downloading using the DNS name. If DNS doesn't know how to resolve that DNS name or resolves to a bad IP address, then we're going to have a problem. Could be stale VIBs, in that when we talk about stale VIBs, we're really talking about I didn't get things uninstalled properly, so they're kind of still there. And we could just have a bad inventory from vCenter. So here we show some errors that hey, the agent VIB is not installed. I can look at the esxupdate.log in /var/log on the ESXi host in question. And here we're showing some, just a metadata download error at this point. But, this is going to be a bigger problem. Name or service not known. Right? It can't resolve the vCenter server host name. Now, this could be a DNS problem. Once in a while, even if the vCenter server does resolve properly, if the IP address on vCenter has been changed, sometimes we run into a case where maybe we need to set the managed IP address of vCenter. So this is a setting in vCenter server that we may have to go and manipulate. By default, it's blank. We simply use DNS resolution internally, but sometimes I have to set that I'll just set that to match whatever we're resolving to, and everything should be good. EAM can't access VIBs from NSX Manager. This could be a firewall problem. This could be a DNS problem, right? vCenter server can't resolve the host name for NSX Manager. So that's something that we could be running into there. So we talked about EAM, what it is, what it does, what happens, how do we restart it, right? Some of the different failure scenarios we might see. We talked about how to manually install the VIBs on an ESXi host. What is a boot bank and why does it even matter? A boot bank can be thought of as sort of the boot firmware for your ESXi host. It's a partition that is created by the ESXi installer, a fixed size 250 meg partition. It may vary a little bit from ESXi version to ESXi version, so just remember that. But it's not something I can change. It's a fixed size partition that contains all of the bits, all of the VIBs that are installed on the host. So my hypervisor, NSX stuff, the VM kernel, third-party things that are installed, that get installed over time, all my drivers, all kinds of stuff gets installed here. Now, generally speaking, the base 250 megs is plenty of space. Right? Generally speaking, that's fine. Especially as if you're using, say, vSphere Image Builder to create your own ESXi images. We've got a secondary and an alternate boot bank that as we make changes, we'll create an alternate just so we have a backup, someplace that I can boot from if something goes terribly, terribly wrong. But we need to understand what it is and why it's there, right? This is from what I boot my ESXi host. So when I power on the host and I watch the ESXi host and it says booting ESXi and you get the list of all of the things that are booting, that's all coming from the boot bank. Now, we may see a scenario like this, where I'm looking through my log files and I can't get my host prepared for NSX because I see error messages like this. The pending transaction requires X, however the maximum supported size is less than X. This error says not enough space in the boot bank. That's all it says. Not enough space in the boot bank. Why is there not enough space in the boot bank? Well, it's simple. I've installed too many things on my ESXi host. Now, maybe you haven't installed anything on your ESXi host. You just came, this is how it deployed out of the box. Something that we do run into from time to time is with vendor-specific ESXi images, right? So ESXi can be packaged up into distributions, right? We've got our image builder tool that allows you as a user or a big computer vendor, a big server vendor to create their own ESXi image, right? And when my hardware vendor gives me that image, it typically is the base ESXi distribution plus the stuff that the vendor has added, right? So it's what we deploy if you download ESXi from VMware.com, plus drivers specific to a given vendor's hardware, maybe hardware management tools specific to a given vendor's hardware, things like that. So it's vendor-specific stuff to make ESXi work on their particular hardware. Maybe it's got NICs that we don't supply drivers for out of the box because the NIC came out after the last big version of ESXi did, or whatever it might be. So this happens. It's not a big deal. It's just a thing to think about. We may run into this from time to time, and again, it's typically with those OEM ESXi images. It's not a big deal. Not a big deal. We can remove things that we're not using. Now, how do we figure out what's even installed? Well, I can use the command ESXCLI software vib list on the ESXi host to figure out what VIBs are installed. Now, just the list of VIBs doesn't tell me whether or not I can remove them. I probably want to look at other information, and some other information we might want to look at is, say, network drivers. Right? In our servers, we tend to have one or maybe two types of network devices. Right? We're not gonna add things typically that go outside of that realm. So network drivers are often a relatively safe bet as far as things we can remove. Storage drivers are another case of things that we might safely be able to remove if I know which one I'm using or which drivers I may be using in my server, right? So, for example, here I've got a list of NICs, right? ESX CFG-NICs-L for list out all the NICs. Well, here I'm using NVMXNet3 device drivers, right? So all I have is VMXNet3 devices. This is a virtual machine. I could probably take out all the physical NIC drivers. But other systems, your physical systems, maybe you're using ELXnet NICs, or you're using Intel NICs using the IBGN driver, or whatever else you might be using, whichever Broadcom NICs you might be using, right? You're probably using a bunch of NICs from one vendor, and they're probably all using one driver. Well, at that point, you probably can get away with removing the other drivers, which are all consuming space in the boot bank, right? I can see which kernel modules are loaded. This is going to help me understand which things I absolutely don't want to remove. I can see which kernel modules are loaded on the ESXi host by looking at the ESX CFG-info output. But you probably don't want to do that without filtering that output a little bit. Otherwise, the text is going to scroll and scroll and scroll. It's going to go for a while. So we use the grep command, right? We pipe the output of ESX config-info to the grep command. And that's going to filter for a string. The string we're looking for is shown in quotes, equals, plus, module with a capital M, space, colon, end quote, right? So all the stuff between the quotes we're going to look for. We want to look for that because if we look at the output of the screen, look at that name, right? The ESX config-info provides a nice kind of a treed output, a hierarchically treed output, but there's a lot of stuff that's being produced at that point. So we want to filter that out. But the module line, if we were to follow that over, that doesn't give us the module name. It's actually the next line in the output that gives us the name of the module. But if we just searched for the string name, we'd get a bit more than we bargained for. So what we do is add the command argument to the grep command -A1. And what the capital A does is it tells us to search for this string, and when we find the string, right, grep finds the string and prints the string, but it says -A, append one line, right? So we get the module line, and then we follow that, we append to the output the next line. So show me the line with the match +1. That's all that grep command is doing. So we can look for that, and then maybe we can pipe that output to a paginator like less or more to give me something I can look at instead of dumping everything out to the screen at once. And here we can see the kernel modules that are active on the ESXi host, right? These are the VIBs that are active on this ESXi host. Don't want to delete those. If I try to delete something that is in use, well, we get an error message, right? Can't remove this file, device or resource busy. This is a bad place to be because we're in a questionably safe place. I want to reboot my ESXi host as soon as possible after I run into this error message, just to put my host back on a steady state. However, device drivers that are not in use, or VIBs that are not in use, I can remove, again using ESX CLI software VIB remove and then -n in the name of the VIB. We get error, not error, but status messages like VIBs removed, here's what was removed, right? This is good, but if you look at the message, the update completed successfully, but the system needs to be rebooted for the changes to be effective, right? We still want to remove VIBs, or not remove VIBs. We still want to reboot the ESXi host when we're done removing the VIBs. Now, when it comes to fixing NSX or trying to resolve boot bank related issues or things like that, we also needed to uninstall the NSX VIBs so that we could go through and get a clean baseline, right? Or even after my VIBs were upgraded, we needed to reboot for that all to take effect. Well, it's not quite as structured or critical as before. At this point, I am going to say, though, just as a personal recommendation, when you're mucking around with VIBs, clean things up, do what you need to do, reboot, and then try again, whatever you're trying to do, even if it's bouncing or even if it's repairing the VIBs on an ESXi host, right? but rebooting a host is not necessary if I'm, say, upgrading the VIBs on ESXi, right? That's a new thing in NSX 6.3 and 6.4. We can now dynamically unload and reload and replace the VIBs and the kernel modules and things like that without rebooting, right? It's perfectly safe, perfectly reliable, works just fine. So, we talked about a boot bank. We talked about what a boot bank is, why a boot bank is there, and we talked about fixing problems when the boot bank is full. Once we get all the hosts prepared and get everything rocking and rolling, we need to think about, or at least understand, how NSX Manager and my ESXi host kind of stay in sync. And that's done through a heartbeat back and forth, right? And the heartbeat is pretty simple. The heartbeat comes from the host. It reaches out to NSX Manager. It says, hey, this is me. I'm here. This is the heartbeat sequence that I'm on. And NSX Manager comes back and says, oh, great, that's awesome, right? And back and forth and back and forth. The heartbeat process is something that we should see. We may not actually see. It just going to happen, right? It's just going to cruise right along and it's going to do its thing. Once in a while, if I run into a sequence number mismatch, then we'll move on to 2, right? Hey, you need a full synchronization, right? Full sync notification. You need a full synchronization. You, this particular ESXi host, you need that synchronization. And then the host is going to say, oh, we're apparently off. So yes, let me send you a sync request, right? Tell me everything. Where are we? What have I lost? What have I missed? Where are we now? Let's just start back over, clean slate, and drive from there. And then NSX Manager will then send us that full synchronization. It'll do its thing. We'll sync back up. We'll have a new sequence number that we'll start with, and back and forth we'll go again, right? We'll continue to send the heartbeat. The heartbeat contains a sequence number and the connection status. So can all my agents talk to one another and talk to the things they need to talk to, and so on. Messaging does occur between the firewall agent and the RabbitMQ. So here's just looking at another picture, another diagram of this, right? So I've got one message bus channel with my heartbeat, another for my heartbeat response, and then we've got normal messages. And when we talk about normal messages here, what we're talking about is distributed firewall updates and distributed firewall statistics and just all kinds of stuff like that, right? Those are other things that are outside of the scope of the heartbeat. What else do we have going on, right? So we have, if we look at the communication channel health statistics that NSX can provide us, we have one that says, can the message bus agent talk to NSX, right? NSX Manager. So that's what the first half of this slide was looking at. The next statistic that we look at is, can the control plane agent communicate with NSX Manager? And ultimately what that's going to tell us is the proxy between the control plane agent and the firewall agent, or VSFWD, is that proxy healthy? Because if that proxy is healthy, then we can get messages in our heartbeat payload to the NSX Manager from the control plane agent. We've got a third heartbeat, or a third communication channel health that says, can my control plane agent get to my controller cluster? Well, the information for that, NSX Manager isn't going to see unless we tell it. So that's part of the payload that's proxied from the control plane agent to VSFWD. Right? VSFWD will then take that payload from NSX Manager that says, yes, the proxy is working, and yes, I can communicate with my controllers, and that becomes part of the heartbeat that we just saw. Now, if my message bus fails, if my message bus goes offline, we'll start seeing messages like this. Messaging infrastructure is down on host, right? This particular host ID 20, right? Host with the managed object ID or managed object reference ID of 20 is not communicating with the message bus. Now this could be a message bus failure, but if I'm only seeing this on one host, it's probably a message bus agent failure. Now if I see this on a number of hosts, right, all of the hosts in my environment all of a sudden pop up with this message, then we may have a message bus related failure at NSX Manager. So I want to look there. So it depends on where I'm going to look for where I'm going to, or what has actually failed as far as how I'm going to resolve this, right? I'm either going to troubleshoot VSFWD on a single ESXi host, or I'm going to troubleshoot the message bus on NSX Manager centrally. But I want to think about that once I start seeing things like messaging infrastructure down on host. This is really a critical event. So what happens to my channel health troubleshooting when my message bus is down? Well, if my message bus is down, then my heart beating doesn't work. If my heart beating doesn't work, my communication channel health cannot be reported. So we will report, NSX Manager will report for this host that VSFWD to NSX Manager is down, that NetCPA to NSX Manager is down, and that the controllers to or the network control plane agent, NetCPA, to the controller cluster is down. Now, we can be really confident with the first two, right? If my message bus has failed because my message bus agent has failed, then we can't talk to the message bus, so we can't talk to NSX Manager. And if the message bus agent has failed on the host, then NetCPA's proxy to VSFWD has also failed, right? We've got a critical component that's no longer there. At that point, all we can do is assume that since NetCPA can't tell us anything, that's in bad shape, right? So we make a worst case scenario decision here sometimes, right? We may see this as unknown, and we may also see down as well. Now, if my message bus is down on a host, I want to look at the status, right? Etsy initd vshield stateful firewall status is the command line that I run on the ESXi host that's been impacted to see what the status of VSFWD is. Hopefully I see it running. If it's running, then the watchdog maybe has caught it and been able to pick it back up, and we're back in business, and that could be good. Otherwise, I need to look and see what's going on. I can look and see what the RabbitMQ configuration, the message bus configuration is with the ESX CFG-advanced config, or ADV CFG config, or ADV CFG command. ESX CFG-ADV CFG-L list. That lists all the advanced configuration variables. We want to trim that down. We pipe that output to the grep command. We grep for RMQ. Case sensitivity is a thing. That should be a capital R. That'll give us all the variables. There should be 16 of them, right? That's not going to give you what the variables are, but it'll tell you it'll tell you the variables, but not the contents of the variables, right? To look at the actual contents of the variables, the value of the variables themselves, we use ESX CFG-ADV CFG again. Instead of -L, we use -G for get, and then we get a specific variable. So the example shown on screen, the RabbitMQ or RMQ IP address. Where's my NSX Manager? ESX config advanced config -get user vars /RMQ IP address. And that should return an IP address. Hopefully that's the same IP address as my NSX Manager. Probably want to validate that. I can validate that I'm connecting to the NSX Manager. Here, we've got a good output that we're showing you, ESX CLI network IP connection list, the longest netstat command you will ever type. So when we look at ESX CLI network IP connection list, we want to trim that output down to just look for port 5671. TCP 5671 is where the message bus runs, right? That's the TCP port that the message bus uses. So I should see connections, established connections to TCP 5671. More than one, most likely. I don't know how many you're going to see, but there should be at least one of them there. So I can see from the logs whether or not my message bus is successfully connected. Here we showed in green for good and red for bad. We've highlighted positive and negative here. So var log vsfwd.log is where we're going to look for that. So here we show, host ID, host 20, peer exchange. blah, 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 right? Receive a registered client with topic heartbeat, right? So there's my heartbeat client topic. So now we can go back and forth on the message bus with the heart beating. That's good. That's a successful connection to the message bus. Compare that to the bad. SSL connect, underlying syscall error, bad file descriptor, failed to connect. Oh, that's terrible. Can't connect, that's no good. So, we can also look in our logs, var log vsfwd.log on the ESXi host to see whether or not my message bus is doing okay. I can also validate that the message bus is working by looking at the config by vsm.xml file in the etc VMware netcpa directory. And what this tells us, right? What this tells us is the message bus worked and the proxy between NSX or between netcpa and VSFWD worked because we get this information from NSX Manager. Right? netcpa gets the information to build this file from NSX Manager, so that should give us everything, right? What we've got highlighted here, port connection ID 0, port 1234, server 172.20.10.40, that's a controller node, right? That's a controller node that we've gotten this information from. We've got information about our distributed logical router, but the fact that we have this file, the fact that we have this file populated with information about things like controllers, this tells me that the message bus proxy is working, or was at least at one point recently. Now, what happens when the control plane agent fails? Right? What happens to my communication channel health when the control plane fails? When netcpa goes away for some reason or another? Well, we're still going to show the channel health for VSFWD to NSX Manager. We're going to show that as good because it should still be good, right? We haven't noticed that VSFWD is down. We will show that the proxy has failed from netcpa to NSX Manager, and we'll show that the controller connectivity is either unknown or down. Because we don't know, right? We don't have netcpa reporting that to us because netcpa has failed. We can look at netcpa, right? I can look to see that my config.xml file exists. That's the first example here on the screen. I'm just doing a list, ls, in the etc VMware netcpa directory. I can look at the netcpa status. The netcpa service status. Is that running? Is it not? Right? If it's not running, then I definitely have a problem. If it is running, I could still have a problem. Hopefully not. I can look at the netcpa log. That the netcpa log is var log netcpa.log. And here we see, I've got global lux. I've got messages from controllers. This looks okay to me. So this does not show us an error condition. What else can we look at? I can see in my netcpa log, received controller information, right? For added this controller, added that controller, added that controller. I've got successful connections to my controllers. So if I'm curious as to whether or not I'm successfully linking up with my different controllers, this is another place I can look where I see these added connection to this IP address. Config by VSM.xml, what all is in here? Well, we saw some of the stuff that was in here. We saw a small list of controllers and then a distributed logical switch list. But what else is in here? Well, when it's populated, when it looks good, we actually should see 3 connections or 3 connection IDs, right? Here we're showing 1, 2, and 3. And we see the IP address, right? Server, whatever, port 1234. SSL enabled is good, right? There's our thumbprint. We have secure communications capabilities from NSX, or from the ESXi host rather, to each of these 3 NSX controller nodes. These IP addresses here should match up with what we've actively got connections to, right? We can validate that with the SXCLI network IP connection list and search for 1234, grep for 1234, the TCP port for our control plane. Now, we've talked about the connection status health or the channel health. We've talked about the different things that impact that. What if we see discrepancies? What if we see some discrepancies? For example, we see VSFWD is down, but my control plane agent is up, and I can communicate with my controllers. Well, that could happen. Or something like example 2, right? Firewall agent is up, controller is down, controller is unknown, even though I know that everything is good. If I've just restarted services or reset things or I'm just coming out of a problem, it's okay, right? These things are actually expected. Just give it a second and all the reporting will kind of calm back down and we'll get the right output. So we talked about the communication channel health. We talked about NetCPA's role in that communication channel health. We talked about VSFWD's impact on the communication channel health, and we talked about how to look at those things in the logs and all kinds of good stuff there, right? So these are the services, the two user world agents that are kind of what we have just focused on here a bit. So we can restart the control plane or message bus agent from the ESXi host with the command line, but what if we're not logged in? What if we don't have access to the ESXi host, right? That could be a thing. How can I do that? How can I restart these services? Well, one way is going in through the networking and security plugin in the vSphere web client, going to installation and upgrade, going to host preparation, and next to a cluster or next to a host, even if I want to localize it to an individual host, I can expand out the cluster and hit the little gear next to a host, right? If we hover over the edge of any of those columns, we'll get this little gear icon. And I have this force sync services action, right? Force sync services, what this is going to do is then pop up a little dialog box. It'll say, what do you want to synchronize? Your options are routing, VXLAN, and firewall, right? Firewall will restart the VSFWD service. Routing or switching will restart for you the NetCPA agent, right? It's part of the force synchronization process. We'll restart the agents and kind of set things back up from there. Let's look at some other maintenance items that we may get into, right? Log files. What logs are interesting in context of my host or my control plane or my, on and on and on. Right? What other log files might be a little bit interesting? Well, the VM kernel log on the ESXi host, right? var log VM kernel log. This is going to contain information about, if we run into problems with kernel modules, right? The actual core functions. So the VDL2 kernel module, the VDRB kernel module, and the vSIP kernel module, the different things that we're running, those will log to the VM kernel log. The control plane, NetCPA, will log to netcpa.log, right? So the user world agent logs to a separate log. VSFWD, that's where my message bus agent lives. That'll log to the VSFWD log. On my edge, on my control virtual, or on my distributed logical router control virtual machine, just like on my NSX manager, I can do a show log. And then I can always export tech support logs from my individual edges, or we can go through the packet capture, or not the packet capture. I'm in the wrong place in my head. I can go through the support bundle UI that's new in NSX 6.4 and gather the logs for all of the relevant components that I need. What other interesting files are we going to run into? Well, there's config by vsm.xml that's located in etc VMware NetCPA. That's going to give me the configuration information that the NSX manager gave me about my controllers. So that's going to exist. I'm going to have one of those on each of the ESXi hosts. We have our netcpa.xml file. The netcpa.xml file in user lib VMware netcpa etc is the localized settings file. Right? It's not going to contain the actual information about where netcpa is connecting, but it's going to give us some behavioral information. We'll primarily look at it for things like changing the logging level of netcpa as we may need to do from time to time. We've got our certificate files in etc VMware SSL. So those are my control plane certificates. And so we've got all these things that are going to be built up by communication with NSX Manager. In VSFWD log, we're going to see connection attempts to the message bus. We're going to see basic message bus activity. We'll naturally see more message bus activity if we crank up the logging level. By default, that is informational. And if we want to look for things related to the NetCPA to VSFWD proxy, we'll have to turn the logging level up to verbose and look for the keyword VNet, right? We can look for stuff in the NetCPA log. Here we're showing VSFWD client. VSFWD client is going to be the proxy message in the NetCPA log, right? So we'll see that. But again, we have to turn the NetCPA logging level up to verbose from its default information. We can also see things like there's an error message here on the screen that says got mismatched VSM sequence numbers. So this is my heartbeat sequence number. Now that's bad. Received full sync notification message. Hey, you need to ask for a full synchronization, right? Other things we might see in the NetCPA log file, cannot connect to server, handshake failed, async callback. All of these things are things that we might see that indicate one type of communication error or another, right? So these are connectivity issues by NetCPA to the controller cluster. So that takes us to a lab, right? Lab number 7, we are going to connect into the vSphere web client. We're going to then poke around and make sure that all of my hosts are prepared, right? So we're going to kind of get through all of the host preparation, infrastructure preparation stuff. We're going to look at the central CLI and kind of look at some of the data plane configuration, and then we're going to make sure that the data plane does indeed work. So that is lab number 7. We should at this point be able to talk about host preparation and all of the bits involved, EAM and the VIBs and NSX Manager and what we're doing. We should know a little bit more about troubleshooting VSFWD and troubleshooting and analyzing NetCPA, and we should have a good idea of what logs we actually have. Wrapping up Module 4, the key points that we have gone through, the overall NSX architecture, the management, the control, the data plane, certificates. We've got, we self-sign certificates for our use out of the box, but you may want to use your own. So have at it. DNS server, or DNS configuration and time configuration are critical components in making sure that NSX Manager and vCenter Server and my ESXi hosts are all kind of synchronized and able to do their things. We always need 3 controller nodes in the controller cluster. No matter what, always 3. And that's where my runtime lives, right? That's my entire control plane, or almost my entire control plane. We have a VIB that we will install on each of our ESXi hosts, ESX-NSXV. That's going to give us all of the stuff we need to run NSX on our hypervisors. And the message bus agent and control plane agent are both very critical local parts of the management and control plane, respectively. Welcome to NSX 6.4, Troubleshooting and Operations. Module 5, Troubleshooting and Operating NSX Logical Switches. So, why is this important? Well, logical switching is a key piece of the whole NSX experience. A lot of functionality kind of hinges on us having this logical switching capability, or you having it in your infrastructure. So we've got to understand what's going on with logical switching, how they're deployed, what happens when they're deployed. What are the tools we're going to use to gather information while we're doing our troubleshooting in order to really to make sure that your environment's going to be solid and will keep running as you continue to work inside your infrastructure. We've got 3 lessons in this module. The first lesson, an overview of VXLAN and logical switching. So it's going to be a quick a quick review of what logical switching is and how it works and what we're doing with it. Then we're going to get into lesson 2, where we verify the configuration. So this is going to be a lot of command line detail, where we're going through and pulling this information or pulling that information, or on and on and on. Just lots of command line stuff here. And then lesson 3, troubleshooting logical switching problems. So we're gonna kind of put the tooling and the process together, and we're gonna kind of talk about how we go about troubleshooting some of these things. Lesson 1, an overview of VXLAN and logical switching. What are we going to do here? We're going to talk about the logical switching components and how VXLAN fits into this. We're going to talk about how, or not so much how, but what happens when we attach virtual machines to logical switches. So logical switching, what is it? What does it do? Why is it important? Gives us logically abstracted layer 2 network segments. Right? Plain and simple. Lets me create a switch that provides me an isolated layer 2 network, all in software. Right? That's all it does. We use VXLAN as the encapsulation tooling here, standardized in RFC 7348. If you're really curious, RFCs can kind of be challenging to read at times. And this logical switch exists across my infrastructure, right? Across the entirety of my NSX domain, or more specifically, more accurately, across the entirety of a transport zone in my NSX domain. Now, what all pieces are involved in logical switching? Well, NSX Manager holds the intended state configuration. The NSX controller cluster holds the VTEP, MAC, and ARP tables for the given logical switch and the runtime configuration. The user world agents, the NetCPA in particular, is heavily involved with logical switching, as are my vSphere distributed switches, because we're leveraging the core switching capabilities of the distributed switch, the vSphere distributed switch. The VXLAN pieces wrap around the distributed switch to make up an NSX virtual switch. Now, we've got a couple of different replication modes that we can configure. Typically, these are going to be configured on a transport zone basis. We could override them at the logical switch level, but typically we just leave the logical switch with whatever replication mode is set at the transport zone. We've got a unicast mode, a hybrid mode, and a multicast mode replication modes that we can operate in. Multicast mode is kind of the RFC is the RFC defined operational mode for VXLAN, where we have a multicast flood and learn control plane, where unicast and hybrid mode rely 100% on having the controller cluster and use that external controller cluster to work with. Got a couple of different options when I configure a logical switch. The big one being enable IP discovery, which is what allows for ARP suppression. Right, it allows us to learn the ARP mapping of virtual machines, virtual machine IP addresses, virtual NIC IP addresses, I guess to be precise, and associating those with the MAC address and sending those up to the controller cluster. So what do the controllers do for logical switching? Well, they maintain the MAC, the ARP, the VTEP tables. The VTEP table is what gives us that list of VXLAN tunnel endpoints that are participating in this logical switch. The MAC table, just that, right? It's a MAC address table. VTEP table is what enables our ARP suppression. It keeps the mapping of MAC to IP addresses as they run through. Now, the controllers do also have a role to play in logical routing. They maintain routing and forwarding tables for the distributed logical router and lift configurations and so on. But we're not here talking about logical routing at the immediate moment. User world agents for logical switching. What do we use? What do we do? Well, we use both VSFWD, the vSphere stateful firewall daemon service, which is our message bus agent, along with other things, including firewall service user world capabilities, and the net CPA control plane agent. The control plane agent makes sure we can communicate with the controller cluster, but some things still do ultimately come from NSX Manager. So, NSX virtual switch. Sometimes you'll hear this term bandied about, the NSX virtual switch. Well, what is the NSX virtual switch? The NSX virtual switch is a lot of pieces kind of brought together, right? We have our vSphere distributed switch. That's a key piece of this puzzle. We have the VXLAN kernel module, known as VDL2, Virtual Distributed Layer 2. We have the switch security module. The switch security module is the piece of the puzzle that actually does things like ARP interception so that we can query the controllers for it, right, to get the ARP suppression. And then we've got a dedicated TCP/IP stack that comes into play here so that we have a kind of a dedicated network stack sitting in the ESXi host to go with everything else for our NSX virtual switch. What happens when we create create a logical switch, right? Real quick process. We say, hey, I want to make a logical switch. NSX Manager is ultimately going to choose the VNI and, if necessary, a multicast address for this. And we're in hybrid mode, so we need a multicast address. So NSX Manager, we're creating logical switch 1 in a given transport zone. It's VNI 5001. We've got a multicast address that's been chosen of 239.0.0.2. NSX Manager reaches out to vCenter Server and says, I need a port group, right? A distributed port group on my logical switch ready for VXLAN. NSX Manager then provides some opaque configuration options for vCenter to apply to that distributed port group, right? The com.vmware.net.cp or control plane, right? Is that going to be enabled or disabled? com.net.vxlan.id, this is my VNI in hexadecimal. So if you run 5001 through a decimal to hex converter, you get 1389. Right, so that's what we're looking at here. And then com.vmware.net.vxlan.mcast IP, my multicast IP, again in hexadecimal. So 239.0.0.2, ef.0.0.2, as we're showing here on the slide. So we push that configuration information down to the vCenter server, right? But at that same time, NSX Manager is making an API call out to the controller cluster to define a master node for this logical switch and creating the logical switch componentry in the controller. Now, that's great. We've got the logical switch configured or created, but I can't use it. It's not going to do me any good until I attach a virtual machine to it. So what do? Well, I attach a virtual machine to it, either through, changing the virtual NIC association or whatever. That's ultimately an API call to attach the virtual machine to a port group. Now, before we do a whole lot of anything, we need to power on the virtual machine. So we power on the virtual machine, and then vCenter takes those opaque configuration options that were assigned to that port group and pushes them down to the ESXi host. Now we have to wait to get those down to the ESXi host because until the virtual machine is powered on, we don't know what port on the host those options need to be applied to. So we apply those options down to the ESXi host, and there we go. So my virtual machine is powered on. The configuration on the virtual switch port on the ESXi host is done. We know what logical switch we're attached to, what VNI, etc., etc. Now what happens? All right, now what happens? Well, now let's assume through this that that this virtual machine is the first virtual machine on this ESXi host that is a member of this logical switch, right? Let's just make that assumption. Where the VDL2 is going to send a message to netCPA, right? Because VDL2 is a kernel module. It can't reach directly out to anything, right? So it talks to the user space tooling that we have, which is netCPA, and says, I need to join this VNI 5001, if we run with the example that we had in the last slide. So we send the join message. netCPA then figures out which of the three controllers is responsible for VNI 5001 and says, oh, okay, well here, right, controller 2 is responsible for VNI 5001 here. Let's go ahead and send the join request to controller 2. Controller 2 receives the join request and says, oh, okay, this VTEP, VNI 5001, great. And then it sends a join response that says, welcome aboard, welcome to VNI 5001. Once that's done, it sends a full synchronization, right? A full synchronization of the VNI 5001 configuration, including the VTEP list, right? So we get the welcome aboard message, and then we get the full synchronization with all the rest of the information, right? Once we get all that, netCPA will turn around and send a link up message back to the controller, and then back and forth we go. A little bit of chitter chatter happens, right? Our sync, everything is good, and then once the connectivity is hammered out and has settled down just a little bit, and all the chitter chatter has kind of slowed down a little bit, everybody's gotten the synchronizations out of the way, then we can start sending from the ESXi host MAC address reports and IP address reports to help the controller start to understand where certain virtual machines might exist, or populate the ARP tables and things like that. So that's the logical switching. That's how we attach, or not how, but what happens when we attach logical switches virtual machines rather, to logical switches. Lesson 2, verifying the logical switch configuration. So what are we going to do by this point, right? At the end of this lesson, we should know a little bit more about the command line interface related to logical switching for verification, validation, information gathering, looking at MAC tables, looking at ARP tables, and so on. Now, I want you guys to keep in mind in this particular lesson, this is a lot of command line output. So feel free to pause the video and take a look and study it a little more closely. There's a lot of stuff that we have going on in here. So diving in, right, looking at the distributed switch configuration, things we need to verify in the distributed switch configuration might be the MTU, or maximum transmission unit size, where VXLAN really needs us to have at least a 1600 byte MTU size. If I didn't change that, I'm going to have some trouble. I can go through using the ESX CLI command. I can spell out through the network space and look at the distributed switch associated with VXLAN in my particular host and see whether or not that has a 1500 byte or a 1600 byte MTU as well, rather than necessarily looking through the vSphere web client UI. I can use the vmkload mod command to make sure that the VDL2 kernel module is actually loaded, and I can make sure the VIB is installed with the ESX CLI software vib get command. More than likely, I would actually do these in the reverse order that they showed up. Is the kernel module installed? Is the VIB installed? And is the kernel module loaded? In that order. I can look at the kernel module configuration, the VDL2 configuration, what's going on in my host for logical networking with the net-VDL2 command. Here we're showing netvdl2-L for list, which gives us a little bit more output than even we see on the slide here. For example, I can look at all of the different networks that are configured on this particular distributed switch or on this particular ESXi host. I can use the ESX CLI command to do a number of other things as well. So we've talked about in other sections of the course the controller cluster containing MAC, ARP, and VTEP tables for my different logical switches. Well, there is a certain subset of that information cached on each host, right? Subset of that information being what this host has used. So we can use the ESX CLI command to get that information out, and we see some examples of that here. Now, I probably want to make sure if I'm having connectivity troubles that I can get back and forth from VTEP to VTEP, that I can communicate from VTEP to VTEP. We could use the ping command for that, but just ping my destination VTEP IP, that's not very particular, that's not very specific, that's not testing any particular thing, and that's going to, by default, use the management network interface of your ESXi host. If I'm testing VTEP connectivity, I want to make sure my VXLAN TCP stack is good. I want to use that stack, and I want to use my VTEP interface to make sure I'm communicating. Which is where this beautiful, beautiful ping command comes in. Ping ++ net stack equals VXLAN, right? So the VXLAN TCP stack is simply called VXLAN, all lowercase, -I, the interface, so -I VMK1. VMK1 in this case should be my VXLAN tunnel endpoint interface, and then the IP address. That'll see that I'm getting to the destination VTEP on the appropriate, across the appropriate interface using the VXLAN TCP stack. I can additionally add the -D option to do not fragment the ping, and the -S option to define the size at 1572 bytes to make sure that I can get a packet across that 1600 byte MTU window. So I can go one step further on that ping command. ESX CLI lets me look at the routing table for the VXLAN net stack or any other net stack on that ESXi host for that matter. This is useful for validating that my gateway, for example, is correct. And then there's my ARP table, my neighbor table for the VXLAN stack. Again, also with ESX CLI network IP neighbor list. The switch security module gives me a lot of really, really good information, but the first thing I need is the switch port number for a virtual machine. Remember, the switch security module attaches to a virtual NIC, right, or to all of my virtual NICs, really, that are attached to logical switches. So I need to know the switch port number, and I can get the switch port number easily with the net-stats command, -L for list, net stats list, and then you see the left-hand column. Far left-hand column is the port number, far right-hand column is the client name. Should be pretty easy to pick out the switch port ID, the local switch port ID for the virtual machine that I'm looking for. Net-switch security, or SWSEC, is what allows me to work with the switch security module and get information. So here we're showing me listing the IP address that we have discovered and the MAC address that we have discovered using the switch security module. So what does NSX think the IP and MAC address is, or the IP address and the MAC address, what does NSX Manager think those are for this particular virtual machine? And how did we discover that information? I can get into the controller nodes, right? So we saw some examples a little while ago of getting the MAC and ARP and VTEP table from an individual ESXi host, but what if I want to see what the controller has to say? Well, from the controller, I can log into the controller, SSH into it with show control cluster logical switches, and look at the VTEP, MAC, and ARP tables as shown here. I can get into the central CLI, do the same thing. Some cool things about the central CLI, though, is I can query not only the controller, but very quickly and easily can query an individual ESXi host. so that I can make very quick comparisons between what my control plane shows and what my data plane might show, right? Hopefully they show the same thing all the time, but if I'm troubleshooting, being able to quickly look at both is pretty helpful. So here we're showing getting the VTEP table from the controller and then from a specific ESXi host from the central CLI in the NSX manager. Here we're showing getting the MAC address table from the controller as well as from a single ESXi host, again through the central CLI. This is the ARP table. This is from the controller and then from host 16 again. Looking at various and sundry pieces of my ESX CLI commands, I can get a list of my distributed switch, I can get the information about the distributed switch that I'm using for VXLAN. I can take the VDS name information there and plug that into my VXLAN network port list set of arguments in the ESX CLI network vSwitch DVS VMware namespace and look for a particular VXLAN ID and see the specific switch port IDs that are associated with a given logical switch. I can use ESX CLI to make sure that, what are we looking at? The ARP entries on a given logical switch. So I hope my ARP entries locally map out to the same things that my controller has, the same things that my virtual machines are associating with. I can also see the control plane status, right? Is my control plane up? ESX CLI allows me to do that as well. And we're showing that highlighted at the top screen. I can also kind of start diving into which VTEPs I have, right? And we can see the VM kernel port, which VM kernel port is associated with which IP address. If I've got more than one VTEP on a host, we can quickly and easily identify that again using this ESX CLI command. Right? NetCPA can be started and stopped with the etc init.d/netcpa command, right? Status, start, stop. Most of the time we shouldn't have a whole lot of problem with that. So that's just a good one to keep in your back pocket, but typically we don't need it. And I can look at the netcpa logs in /var/log/netcpa.log. Here we show and are highlighting that we can't connect to a controller, so there's something going on that I need to troubleshoot. I can look at ESX CLI network IP connection list, and in this particular case here is an example where I'm stuck in SYN sent to my controller node. There's a problem here. I'm not getting a response from my controller. Now I need to start looking, am I having a problem at netcpa here, or is it a problem with my controller? etc init.d/vshield stateful firewall is the initialization script that we would use to manage the running state of VSFWD of the message bus agent. Here we're showing that I can't connect to my NSX manager for some reason or another. We can use ESX CLI network IP connection list again to validate whether or not I have a good or bad connection. And I should have one or more established connections, ideally. If I don't have connections in the established state, then there's something going on. I can look at the VTEPs, the VXLAN tunnel endpoints, in my logical switch. Right here, we're on the NSX manager. We're looking at the VTEP table for logical switch 5001, VNI 5001. And what we're calling out here is that, we see the VTEPs, and each VTEP has a connection ID associated with it. Well, what does that connection ID mean? Well, if we look at show logical switch at the connection table, right, for the logical switch, we see the host IPs are entirely different than my VTEP IPs, but we have the same connection IDs. They're showing up in a little bit different order, but the same connection IDs. What we can do here is map the VTEP IP in the first command output to the management interface IP, the host IP, in the second command output, so that I can tell which host is which. This is especially useful if, say, you're using DHCP for your VTEPs, so that your VTEPs aren't always the same IP address on a given host. Packet capture. Packet capture is useful. Packet capture is flexible. Packet capture does a lot of good things for us. Packet capture on the ESXi host, if you're using it through the command line, uses the packetcap UW command, which we will see in a second. But we need the switch port number for the virtual machine, again, that can be gathered by net-stats-l. So, let's go play with packet capture. Let's go play with all of this stuff in the lab. You'll get to see all of these commands way, way, way more in depth. We have 2 labs that we're going to go through here. Verifying the proper functioning of logical switching. Get your fingers ready. Lots of typing in this one. We're gonna verify the management plane. We're gonna verify the control plane. We're gonna play around with CDO mode. Actually, we're gonna change the timer for CDO mode on a single ESXi host. Right? Not a good idea for your production environment, but it's good to know that it can be done. We are going to validate that virtual machine connectivity is good and that the data plane functions. And we're going to play with TraceFlow for a minute just to make sure connectivity works. Lab number 9 is where we get our packet capture chops ready. So again, way more typing. We're going to collect the information we need about our virtual machines. We'll start some traffic flowing, right? Minimal traffic, just a ping between web server 1 and 2. Nothing fancy. And then we're going to start capturing traffic across the data path at various points in the data path so that you can see what traffic looks like at the distributed switch when it is received there, what it looks like when it's being forwarded, what it looks like as it's being received at the uplink before we encapsulate it, or what it looks like after we encapsulate it, and we're going to see what it looks like on the destination host as we receive the encapsulated VXLAN packets, and on and on and on. Lots of good stuff going on here. We're going to tweak some log levels and look at, watch NetCPA make some VTEP and MAC and ARP ARP updates to the controllers. All kinds of really, really cool things going on here in Lab 9. So, what did we get through in Lesson 2 here? We talked about a lot of command line verification of a lot of things. ARP tables, MAC tables, VTEP. Can I talk to other things? We played with TraceFlow. We played with packet capture, right? We just covered a whole lot of ground. So I think this gives you a lot of tools that we're going to continue to use throughout the remainder of this class and throughout the remainder of your time working with NSX. Lesson 3, troubleshooting logical switching problems. So what are we going to do here? We're going to talk about some of the failure scenarios that we might see for creating logical switches, or getting logical switches going, or things like that. So we're going to talk about the different troubleshooting, whether it's troubleshooting control plane, troubleshooting management plane, troubleshooting data plane issues, etc. So let's start with a quick flow chart. We're actually going to start with a couple of quick flow charts. What happens, failed VXLAN installation. Failed VXLAN installation. What we're really talking about here is I went to configure my ESXi host for VXLAN, and it failed, right? So it just didn't work. It failed. Assuming you're just being told about the problem, you didn't get to see any of the failure scenarios or failure conditions or whatnot. First things first, can you get from anywhere to the management VMware kernel port or VM kernel port? Can you ping the host? Can you get there from here? If there's something blocking connectivity to the ESXi host, we may have a problem. DNS resolution could be a thing, right? So don't just ping by IP address, ping it by name as well. Make sure the name resolves to the right IP address. I've seen challenges from time to time where folks have re-IP'd their ESXi hosts and then forgot to update DNS. Next thing I want to think about is my distributed switch. Is the distributed switch version 5.5 or newer? So the distributed switch was introduced a long time ago, actually, and we versioned the distributed switch, right? Every new version of the distributed switch gave us new and cool and fun and exciting features. Well, some of those features are required for use by NSX, including some of the features that were introduced in vSphere 5.5 and the distributed switch version 5.5. So NSX 6.4 will not work with anything prior to vSphere 6 or vSphere 5.5. So if you've got a distributed switch and you've been upgrading your vSphere infrastructure, but not realizing maybe that you needed to upgrade your distributed switch, now's the time to do so. It needs to be upgraded to at least version 5.5. Right? There's just no way around that. NSX will not work with an older version distributed switch. Then, what's the distributed switch MTU? Right? Is it 1600 or larger? You'd better configure it that way. Most people I know just turn it up to 9,000 and call it good. Right? It is just a maximum. But work with the folks who manage your physical network to understand whether or not you just crank that up, right? So if that's you, awesome. Have a chat with yourself. If you're the vSphere guy managing the distributed switch, go have a chat with your network team. If the MTU is already 1600 bytes and the physical NIC supports that and everything, end to end is fine there, then start digging into the logs on NSX Manager. Maybe call support and see what they have to say about it. I mean, I know you're taking a troubleshooting class to try to avoid calling support, but sometimes that's where we end up. We talk about this as resolve the management plane issues. What about an error message that pops up that says unable to allocate a resource when you're creating a logical switch? Well, here's what that means, right? Unable to allocate a resource. We can kind of follow the flow chart here. To summarize it all, unable to allocate a resource means that I either don't have a multicast segment configured, so I can't allocate a multicast address to a multicast using logical switch, or I don't have any VNIs left in my segment ID pool if I'm trying to create a new logical switch. I mean, it's very literally, I cannot allocate a resource. That resource is either a multicast IP address or a segment ID pool most of the time. So, if I'm in a multicast configuration, if my transport zone is configured for multicast replication, did I remember to configure a multicast pool and a pool of multicast IP addresses that we can use? If not, I better go do that. Is my control plane set up for multicast or unicast or hybrid? Well, chances are my controller cluster is already there. I'll get a different error if I recall if my controller cluster is not there, but better safe than sorry. Let's check that. If my controller cluster is there, then let's go look at the segment ID pool. Make sure I have enough segments in, right? Each logical switch will consume one segment out of the pool. So if I set up a segment ID pool originally at 5,000 to 5010, that gives me 11 logical switches. If I've deployed 11 logical switches and I try to deploy number 12, we're going to see this error message. So expand your segment ID pool. There are plenty of segments available. Go ahead and let them rip. How about another one? Ping fails between two VMs on different hosts across a logical switch. So two VMs are on VNI 5001, right? Same logical switch. I ping from one to the other and it fails. Well, first things first, let's check layer one. Are the virtual machines plugged into the right spot? Did I remember to move both virtual machines to that one logical switch? Worth checking, right? Can my VTEPs communicate, right? This is where I start thinking about having different conversations happening, right? My services conversation ping from VM1 to VM2, and my transport conversation from VTEP1 to VTEP2. So I need to make sure my VTEPs can communicate. That's very much the second step I would take here. And then if that does work, then I need to look at the control plane on the source and destination host, right? Because what I've probably got is I can't find the other VTEP. I don't know what VTEP is servicing the other side. So I have probably a control plane issue that I need to troubleshoot at that point. So we can think about this and look at this, and you know, as we start to think about the control plane, I need to remember that you know, we talk to a lot of the control plane through NetCPA, right? When NSX Manager has to deal with NetCPA, we have to communicate through the message bus. Don't forget that we have that proxy. And then NetCPA for anything that we need to configure directly into the kernel. NetCPA can do that for us. We can see a number of different log messages. These are actually not all of these. Nope, sorry, I'm incorrect. All of these messages that we're showing on this particular screen are going to be in netcpa.log. So, you know, connected to VSFWD, my proxy is good, right? You know, received registration ACK, right? My proxy is acknowledged. Received host credential message. So, you know, we're talking back and forth from NetCPA to the proxy to NSX Manager and back, and on and on. So what are some of the things we might run into? VM kernel port missing. Have you ever had a case where the VM kernel port was missing? Sometimes it happens, right? Maybe you have an admin that inadvertently deletes a VM kernel port or something like that. A force sync of services, VXLAN services in particular, will actually cause us to go out and resync and realize, oh, hey, look, there's no VTEP here anymore. Let me rebuild that, and we'll make sure we'll orchestrate the rebuilding of that. So that's a pretty easy thing to take care of. If my VTEPs don't have the right IP address, maybe I set them for DHCP and there's no DHCP server on that segment. That could be a thing. Maybe it's just a case of I misconfigured them or, you know, something along those lines. Then I can just go and fix that directly through vCenter server, right? I can just log in and manually manipulate the VM kernel port. Here we're showing the config by VSM XML file, but what we're showing here is the output of that file as gathered by the central CLI. So elsewhere in the class, we have seen that the etc netcpa config by VSM file is pretty important, contains a ton of great information, but I don't need ESXi host access to get to that file. I can look at it right here through the central CLI on my NSX Manager, show logical switch host ID config-by-vsm, and I can get the same file. Central CLI, how do I manage or how do I collect everything? I need my host IDs, right? We've seen the host ID over and over and over again as we continue to look at the central CLI. Well, what's the easy way to get it? If I know what logical switch I'm looking for, or logical switch, I know a logical switch, I can do a show logical switch list, which shows me a list of all the ESXi hosts attached to that logical switch and their host IDs. Then I can do things like show logical switch host ID verbose, which gives us the same basic output, actually I think it's identical output, to the net-vdl2-l list command that we have seen elsewhere. netcpa log shows me when I'm not connecting to my controllers, and using ESX CLI, I can look at the connections list and see if netcpa TCP1234 is establishing connections. Maybe it's not. Maybe they're in a sin-sent state like this. We've talked earlier in other places in this class about the ping command, ping ++ netstack, and on and on and on. You've used that in a couple of the labs as well. If you don't have access to the ESXi host, that ping command is kind of useless. But we have similar functionality through the networking and security plugin. So if you're the NSX administrator, you can log into the networking and security UI, go to logical switches and drill into one, and there's a ping test that you can run. It's the same exact test, we just have a web UI front end for it. I select the source and destination hosts, the size, and I click Start, right? That's that. Which brings us to a handful of labs, right? Not just one, not just two, 4 total labs, 10, 11, 12, and 13. These are all troubleshooting labs. Right? These are all break-fix labs. So we're going to do the same thing over and over and over again. We're going to right-click on the troubleshooting menu and select Run with PowerShell. We're going to run Lab 10 or Lab 11 or Lab 12 or Lab 13. Here in Lab 10, however, this is another Log Insight lab, right, where we break, we validate that things aren't working right, then Log Insight, we walk you through finding the break in Log Insight so that you can then turn around and fix the problem, right? Again, run the repair script just in case. Lab 11, no Log Insight here, just another break fix lab. Lab 12, just a break fix lab. Lab 13, just a third or a fourth break fix lab. So a lot of lab time coming up here. So what did we get through? We talked about logical switching problems, VXLAN problems, some troubleshooting methods and troubleshooting ideas for some of them, talking about some of the different troubleshooting tools we might use. And in this module, we've covered a great many things, right? Logical switching components. We've touched on the replication modes. We talked about all kinds of command line stuff for validation. The controller cluster has logical routing functions that we talk about. We've talked about the user world agents and the VIBs and on and on and on. We've covered these things in relatively great depth by this point. So, I hope we're doing well with logical switching and the user world agents. Welcome to VMware NSX Troubleshooting and Operations, version 6.4. This is Module 6, Troubleshooting and Operating NSX Logical Routers. We're almost there. Not a lot to go through yet. What's important about this? Well, the distributed logical router is sort of a fundamental component of your software-defined network infrastructure. We build logical switches, which are isolated layer 2 segments that we can attach virtual machines to, but those virtual machines likely need to talk to one another. Just like in any other network architecture, if I want to communicate from one layer 2 segment to another layer 2 segment, I have to have a router. We put a distributed logical router in place so that router exists pretty much everywhere. So we kind of need to know what all's going on with that routing device so that we can make sure traffic flows freely and appropriately throughout our networks. We've broken this module up into 2 lessons. Lesson 1 is a brief overview of the infrastructure, and Lesson 2 is all about how we make the distributed logical router go. It's all about the command line aspects and UI aspects of working with a distributed logical router. Lesson 1, an overview of NSX logical routing. What are we going to talk about here? Well, logical routing is made up of a number of different moving parts. Partly because we're distributing the functionality, right? Partly because we've got the control plane involved and the management plane involved and so on. So we're going to talk about all of that a bit. We're going to talk about what the process is as we deploy distributed router instances or edge services gateway instances, and what the process is as we update these things, right? And then eventually we will get into a complete packet flow. We've got an entire packet walk in another part of this lesson that we'll walk through and kind of show you what's going on with the distributed router in very, very much depth. So, logical routing, what do we have? What's going on? What's happening here? Well, we've got the NSX Manager. The NSX Manager is our configuration engine, right? It's our core configuration engine for logical routing. Either the distributed logical router, which is our east-west routing solution, right, inside the software-defined data center, or our edge services gateway, which is our north-south routing solution, or into and out of the software-defined data center. So we deploy these things, and then the logical router control VM and the edge will form their neighbor relationships, assuming, of course, we're using OSPF or BGP for dynamic routing. The distributed logical router will process its routing table, and we have to forward it on, right? The edge will do the same thing, but the edge doesn't propagate that newly built routing table necessarily. The distributed logical router, on the other hand, the distributed logical router control VM specifically, is the piece that's doing this work. And the distributed logical router control VM builds the routing table based on what it's learned through its static and dynamic routing protocols, and then passes that routing information down to the controller responsible for this distributed logical router instance. Well, why does it distribute that information to the controller? Well, here's why. Distributes that information to the controller cluster so that the controller can then populate the distributed router kernel module on each of the ESXi hosts. Because the distributed logical router is very much, as its name implies, distributed across my transport zone. So the routing, the packet forwarding, actually happens inside the ESXi kernel. It does not happen on the logical router control VM. The logical router control VM is there really for dynamic routing, right? To have one central point for the router to peer with its upstream counterparts, right? Instead of having to peer with however many ESXi hosts you have, right? We have a distributed logical router, but that may be distributed across many, many, many ESXi hosts. So what happens when we deploy this thing? Well, here I've got a couple of ESXi hosts. I've got my NSX manager. I have a controller, right? We're not showing the entire controller cluster, just the controller that we've chosen as the master for this logical router instance. And we deploy, right? We create the distributed logical router. So we go in through the networking and security UI, we go to edges, we hit add, and we walk through the wizard to create a new distributed logical router. We get to the end of that wizard, we hit OK. First thing that happens after we hit OK, after we make that API call, is the NSX manager will work with, ultimately, vCenter server to deploy the distributed logical router control VM. This is just another virtual appliance. We're using the same OVA, OVF deployment mechanism that we've used for the controller clusters, for for the NSX manager, and so on, right? This is just a virtual appliance. So we'll deploy that. Once that's done, the NSX manager over the message bus will communicate information about the new instance, about the new distributed logical router instance to the ESXi hosts in the transport zone, right? This gets to the VSFWD kernel module. That kernel module then not kernel module, sorry, VSFWD lives in user space. Let's make sure we're clear. So we get to the VSFWD user space agent on the host. The VSFWD agent on the host then hands that configuration information to the NetCPA user world agent. And the NetCPA user world agent then hands off to the routing, the distributed routing kernel module, VDRB. Virtual Distributed Routing and Bridging is what that stands for. So we pass all that information down to the hosts. What happens next? Next, we make a REST API call from the NSX manager to the controller instance that we've chosen to be master here, and we create the distributed logical router instance on the controller, right? So we've got all the instance stuff set up. We've got the logical router control VM. We have the basic skeleton of the distributed logical router configure, but there's still obviously more work to do. Either we've created lifts in the configuration or we've gone back after the deployment and created lifts. NSX Manager sends that information to the distributed logical router control VM, right? This gets sent to the distributed logical router control VM, but not directly, right? This is not a communication directly from the NSX Manager to the distributed logical router control VM. This is a payload that's put on the message bus destined for ESXi host B in this case. And host B, VSFWD on host B picks up that payload, that configuration payload, and sends it by way of VMCI, a virtual machine communication interface, into the logical router control VM. So wherever my logical router control VM exists, that has to be configured or prepared for NSX, right? Same thing for the NSX Edge Services Gateway. So we're passing that information, we're building the lifts in the control virtual machine. Now, the logical interfaces don't actually exist in the control VM, but the control VM has to have stubs for these kind of abstractions, if you will, for the lifts that we're going to use on all the hosts, right? So we've got kind of a centralized configuration, if you will. Once the logical router control VM has the LIF information, then we send that LIF information down to the controller instance as well. And at this point, the logical router control VM will calculate its routing table, right? Whether it's simply the connected routes for the logical interfaces, we'll add in any static routes that have been configured out of the box, anything like that. But at this point in the game, remember, we've just created this logical router. At this point, we'll have our connected routes table, probably what we'll actually see. That will be sent from the control VM through a VMCI channel to NetCPA, right? The control plane agent on the ESXi host, and NetCPA will pass those routes onto the appropriate controller instance. So there's a lot of stuff going on here, right? There are a lot of moving pieces in what we're doing with the distributed logical router creation, right? Once we've got the routes to the controller, then what's going to happen? The controller, through NetCPA, is going to populate the logical interfaces and the routes to the VDRB module in the VDRB kernel module by way of NetCPA on each of the ESXi hosts. Now that the ESXi hosts have their logical interface and routing configurations all kind of cemented in for the moment, then we can actually start forwarding traffic. Right? Then we can actually start doing stuff. So this kind of gives us a diagram of all the different communication channels that are in play here. NSX Manager uses, we get a lot of REST stuff to NSX Manager or from NSX Manager to the controller, message bus to VSFWD. There's a TCP socket between VSFWD and NetCPA. NetCPA is responsible for actually configuring the kernel modules. VMCI and NetCPA can both use a VMCI channel to communicate with the logical router control VM. There's just a whole lot of communication, a number of communication paths happening in this particular piece of the infrastructure. Now, I'm probably going to have route updates happening, right? Whether I am configuring dynamic routing or I'm building static route tables, right? I'm going to have route changes. So what are we doing with those routing changes? Well, I make those routing changes. Let's say I'm configuring routing changes in NSX Manager. Let's say I'm updating my logical router instance to use OSPF or BGP. Doesn't even matter which. We configure up the routing protocol, and that information will be published from the NSX Manager to the logical router control VM, where the routing process can then be configured and instantiated. So that kicks off the whole process. Well, once that happens, and the routing process comes up, right? The distributed logical router and the edge will come together, and assuming my edge is configured, and we'll start exchanging routes. And once we have exchanged routes, we'll build the routing table based on what we've learned in the distributed logical router. We will forward those new routes to the controller instance. The controller instance then forwards those routes down to the individual hypervisors, right? Whenever I have a routing change, a routing topology change, my dynamic routing, table kind of updates, we'll kind of repeat steps 3, 4, and 5 over and over and over again, right? That'll just run in a circle, just constantly cycle anytime I get new routing updates, right? Now I can have multiple distributed logical router instances on any given ESXi host. And I may do that, right? Maybe I have instance A and instance B for tenant A and tenant B. But they're completely separate from one another, right? Distributed logical router instance A and distributed logical router instance B might as well be router 1 in a rack and router 2 in a different rack, right? They're entirely separate entities. The only thing ultimately shared is a specially configured distributed switch port called VDR port that acts as effectively a trunk interface that I can use to connect the distributed logical router to whatever logical networks that I need connectivity to, right? The distributed logical router has a couple of different MAC addresses that we will continue to talk about over the course of this. It's important to know what they are, why they are, when they are. We can use either the net-vdr command on the ESXi host or the show logical router host connections command on the central CLI, as shown here on the slide. And that will show us for a given distributed logical router instance, it'll show me the what we call the VDR MAC or the virtual MAC or the VMAC, which will always be 025056564452, right? Always, every time. It's the same MAC address everywhere. And when it comes down to it, that's actually okay. Before you start freaking out that all of my different ESXi hosts are going to see this same MAC address, it's okay, right? It's kind of localized to each ESXi host, so it's not gonna cause MAC address duplicates. And then we're going to create what we call a PMAC or physical MAC for each uplink on the distributed switch. Now, one uplink will be active. The rest of them will kind of be, let's just call them standby, if you will. That's perhaps a poor choice of words, but only one will really be active at any one time. And the VDR port will use one uplink. It'll be associated with one physical uplink. And we're going to generate this PMAC address for use, and this is going to be unique per ESXi host, by the way, right? Each ESXi host will have its own unique PMAC. And it'll be a 005056 OUI, which is one of VMware's OUIs. So we have this unique MAC address, this unique PMAC address, so that when we make an ARP request from the distributed logical router, we'll talk in depth about this in a different segment in this lesson, later on in this lesson. But when we make an ARP request, we have to know which kernel module, which VDRB kernel module on which host actually made that request. And so that's where the PMAC actually comes in handy. We'll get in depth with that later on, so hang tight. Other things to think about, distributed switches with VXLAN need at least one uplink and VDR port, right? This is just going to be part of our configuration. It's almost a guarantee, right? But we need to think about that. I'm going to have at least one VTEP, right? One tunnel endpoint. We're going to need to know about that, right? Because that's where we're ultimately going to be doing our encapsulation, de-encapsulation of logical switching. The virtual machines source MAC or source port is used to determine the DV uplink. So, the teaming policy applies to the virtual machine as well as the distributed logical router, as well as the VTEPs, and on and on and on, right? So we kind of keep that all mapped out. And if you paid attention to the command line output on the last screen, it talked about packets dropped and packets replaced and packets skipped, and those might look a little scary. Ignore those. Those are internal counters. Those are not actual useful counters for real life troubleshooting. So don't worry about those. So let's talk labs. Real quick, let's talk labs. We will dive into lab 14 here. We are going to verify what the distributed logical router is doing, how it's doing it, right? Nothing crazy, nothing fancy. We're just going to make sure we understand where everything is. In this lesson, we talked through the logical routing components, functions, etc., the creation process of the distributed logical router, and later on we will get into the packet flow. Lesson 2, verifying and troubleshooting the NSX logical router configuration. Here comes the command line. So we're going to go into a bunch of stuff in this lesson. We're going to talk about the command line. We're going to talk about the GUI. We're going to talk about how to validate configuration settings, from a number of different perspectives. We're going to look at some logs. We're going to look at the management plane and control plane and data plane again, and just make sure that those are all functional. We're going to look at packet capture. Right? Where do we capture packets for some of these points, right? So we've got virtual machines that attach to distributed switches or logical switches, and then the logical switches attached to a distributed logical router, and then we have to, how many different packet capture points do we have? We'll show you. There are quite a few. So we'll talk about that. And then we'll talk a little bit about backup and restore tasks for edges. So we'll kind of get into that as we go through. When we talk about troubleshooting routing, right? When we worry about troubleshooting routing, I am going to stress right here, right now, that documentation is your friend. Pictures are your friend. Diagrams are your friend. You need to know what the topology is supposed to look like, ideally, logically, and physically, so that you can kind of figure out where things might be going right and where things might be going wrong. So we can gather all that information if we don't have it, but I hope you have it ahead of time. There are tools out there to help you go and pull information together. Since all of this software-defined stuff is all centralized in NSX Manager, right? You could write an API script to go pull your topology information. So there's a lot of cool stuff we can do. Documentation is important when we're trying to figure out a routing issue. What are my prerequisites? Well, host preparation, right? VXLAN configuration, transport zone configuration. When we look at this, particular picture, and we start and this slide, and we start talking about what are my logical routing configuration prerequisites, it can really be summarized as I need NSX logical switching to work before logical routing is going to even be useful, much less functional. Because we do rely on a bunch of the same stuff, right? The host preparation, for example. The logical switching relies on a different kernel module than distributed logical routing, but they're all packaged in the same VIB. So if I get one, I get them all. Transport zone. The transport zone is going to define the clusters on which my distributed logical router will be configured. So that's going to be an important thing, right? Because we're using logical switching, MTU needs to be configured, et cetera, et cetera, et cetera. I need my controller cluster, all of these things, right? I need logical switching to work, and then we can get into logical routing. Right? One step at a time here, guys. One step at a time. So here's my transport zone, right? I can go in and look at my transport zone. And here we've drilled into it a little bit, and we've gone to the Manage tab, and we see that I have two clusters, Compute Cluster A and my Management and Edge Cluster. And if that's all I've got in my environment, this is great. right? But this tells me which clusters my distributed logical router will be configured into once I've attached it to a logical network, right? So I need to think about that. And when we start thinking about transport zones and which clusters are attached, we also need to think about my distributed switch configuration. Right? So we have what we call distributed switch to transport zone alignment. And what we're doing with this alignment is ultimately making sure that, just like it says, my transport zones and my distributed switches align. So, if we look at this example, this is a well-aligned transport zone. So I have two distributed switches in my environment, one for my management and edge cluster, a separate for my compute cluster, and the transport zone encapsulates all of the clusters that are attached to both distributed switches. This is what we want. What we don't want is what we see here, where my transport zone does not entirely encapsulate my distributed switches. If we look at this, I have my management and edge cluster. That's fine. I have my distributed switch for that. That exists. That cluster is attached to the local transport zone. But then I've got my compute distributed switch, to which I have hypervisors in compute cluster A and compute cluster B attached. Well, only compute cluster B has been included in the transport zone, which is a problem, right? It's a problem on a number of different levels, right? This has logical switching impacts and logical routing impacts. So since compute cluster A is not in the transport zone, the VTEPs will not join the logical switches, right? We've got the two logical switches going on here, red and green, three of them, right? Red, blue, and green, 5001, 5002, 5003. The VTEPs on ESX Comp 1A and ESX Comp 2A will not join the logical switch, the VXLAN, right? It won't join the VNI. So layer 2 connectivity is shot unless I'm on a common hypervisor. And then the distributed logical router, when we attach it to one of those logical switches, will populate that configuration across the transport zone. The logical router configuration will not be propagated to ESX Comp 1A or 2A. So logical routing will also not work. So we want to make sure that we have everything configured properly. Now, it may not be a big deal. You may not see a big deal yet because the cluster's not part of the transport zone, so it's not it's not going to have those things configured. Well, of course it's not. But we also have to think about the fact that when I configure a logical switch that deploys into vSphere, that's configured into vSphere as a distributed port group, and that distributed port group will be configured on compute VDS. Therefore, since the hosts in compute cluster A are attached to compute DVS, they will be able to see the port group. They will be able to attach virtual machines to that port group, but we won't have all the configuration necessary to make those work, right? So this is actually ultimately a big problem. So we would need to change the transport zone or change the distributed switch. You'll have to figure out what the right solution is for your environment. So there's just our big red note. Notice we don't use big bright red text very often to note something. This is something to think about. Now, we need to think about logging, right? We always need to think about logging when we're trying to figure out whether or not things are working. So when I deploy a distributed logical router, it's going to log some things locally. And when I say some things, I mean core router operations. It's not going to log things like my dynamic routing process information. So I would have to go in and enable logging specifically on that. We'll see that over and over and over again throughout the distributed firewall and the edge services gateway, is that services that we enable, we will need to enable logging manually for those. Something else we will do, that's very much worth noting is when I deploy a distributed logical router, when I deploy an edge services gateway, syslog receivers are not configured, right? So all of the logging that does happen on my NSX logical routers is only happening locally in the virtual appliance. If I want that traffic or that log information to be forwarded over to, say, vRealize Log Insight, then I will need to go in and configure that. Now, it's easy to configure, but I do need to take the minute to do that, to go into the basic configuration and change the syslog configuration to point to at least one syslog server. I can also, for my edges, download tech support logs. Right through the NSX UI, right? I can select my NSX edges in networking and security, and I can right-click, and I can download tech support logs. If I happen to be in the command line interface, I've SSH'd into the logical router control VM or the edge services gateway virtual machine. I can do a show log to watch the logs. I can also do an export tech support, which is the same as what we're doing here in the UI with download tech support logs, right? It's doing the same exact thing, except that through the browser, I can do an HTTPS download to my desktop, where through export tech support, I have to have an SCP or an FTP destination, right? So a couple of things to think about. When I'm using dynamic routing, I may want to use route redistribution to control what routes are propagated into one routing protocol or another. Distributed logical router will automatically enable route redistribution. If you're using OSPF, it'll enable that, and it will redistribute connected routes into the OSPF routing protocol. The Edge Services Gateway does not. If you change routing protocols, the route redistribution on the distributed logical router does not magically change for you. So keep in mind. So we've talked about transport zones. We've talked about how important they are. Logical switching is important. We've also covered how logging is not enabled by default, but can be quickly and easily enabled, and probably should be. So we rely on NSX Manager and the NSX controllers and ESXi hosts and all these things for distributed logical routing. Well, let's go through and look and see what happens in various failure scenarios so you can be prepared or at least understand what's going to happen when you see one thing break or another. What happens when NSX Manager fails? Well, we've got a couple of different scenarios here. A complete network outage of NSX Manager. And then we've also got the loss of connectivity just to a host, right? A message bus down. So this would be VSFWD failing. Let's start with the first one, right? Network outage, complete outage of NSX Manager means that I just can't change anything. I'm not losing any configuration. I'm not losing any control plane stuff. My dynamic routing updates will continue to propagate to all of my ESXi hosts, right? Everything that I have will continue to work. I can't add logical interfaces. I can't delete a distributed logical router or just delete an interface, right? Because there's no NSX Manager there to handle those operations. But everything else is just fine. So if NSX Manager goes away for a couple of minutes, it's not the end of the world. We're okay. What about if the message bus on an ESXi host fails? Well, if it's not the ESXi host that the logical router control VM or edge services gateway runs on, we're not going to notice anything. Well, we're not going to notice much. How about that? The host that has the message bus failure will not receive logical interface configuration, right? So any new logical interfaces that I create, any logical interfaces I delete, will not be updated on the host where VSFWD has failed. Outside of that, everything's going to continue to work. Now, if the host that has lost its message bus is the ESXi host on which the edge or the distributed logical router runs, then I won't be able to change anything on those particular edges or distributed logical routers, right? No other configuration changes will be able to happen either. So management, creation, right? Basically what we call CRUD, create, read, update, delete operations, management of the object is gone. But it still works. What if the NSX manager can't communicate with the NSX controller clusters? Well, again, everything continues to work. This is NSX manager and the controller clusters. Everything continues to work. Everything's happy. Everything keeps running. It's all good. Most of my management, I can still look at information. So I just lose create, update, delete. I can still read information about the distributed logical router or the edge services gateway. I just can't change anything, right? That's what I lose there. If the NSX manager virtual machine is destroyed, for example, a data store failure, right? My data store fails and the LUN backing my data store on which I'm running my NSX manager, that just goes away, right? I hope you have good backups. But again, this is simply going to be a management failure, meaning that my control and data planes will continue to operate. So long as NSX manager doesn't exist, then I can't change anything. But everything that's running will continue to run. All right, my control plane will continue to operate, and so on. Now, we mentioned here there is a risk of a subset of routing or bridging instances becoming orphaned if we end up restoring to an older configuration, which is very much true. Right? We may require some manual cleanup after I restore my NSX manager, but that's a small price to pay for things continuing to work while NSX manager is not running, I think, or non-existent. What about when we move to the controllers? How about a control plane failure or a variety of control plane failure scenarios? Let's take a look at that. If the controller cluster loses connectivity with the hosts, right? So this is the entire controller cluster. I've lost connectivity to my entire controller cluster from all of my ESXi hosts, or with any given host, right? Let's just say with any given host. My create, update, delete for my routing no longer works. For the host where NetCPA, the control plane channel is down. I can't manipulate my logical interfaces, and we don't get routing updates. Right? This is a little bigger one. This has a little bit bigger impact. We're not going to get routing updates if my control plane is offline, right? If we're using dynamic routing. Now, that's not completely catastrophic. The data plane will continue to work based on what it currently knows. So everything's going to continue to go as we know, but we need to watch this. We're not going to get those routing updates if the network topology changes. If one controller loses connectivity with the other controllers, it's a single controller failure, basically. It's okay. It's okay. All of that controller's responsibilities will be transferred over to the other two controllers, distributed between them, and the controller cluster will run just fine until that third controller has come back to life. Right? Routing updates will happen. Everything will be good. Right? We're okay. We're okay. We're gonna see no functional impact. We'll see an availability impact. We're now in a jeopardy state, but there's no actual other mechanical impact to one controller failing. Two controllers failing becomes a bad day. A very bad day. When two clusters fail or lose connectivity with each other, the cluster majority is lost. The controllers will all see that they're isolated. Here we're talking specifically about a network configuration or network isolation. If my controller nodes cannot talk to one another, each of them will assume that they have lost cluster majority and the cluster no longer exists. Each controller will go into a read-only state. It will drop all of its existing connections, meaning all of my NetCPA connections, my host connections, done. and they'll just sit there. This is more or less an entire, a complete controller cluster outage at this point. No control plane stuff happens, right? Anything that requires the control plane, done, right? We're not gonna do anything with it until the control plane returns to service. Now, the data plane continues to operate, right? We continue to function on the last known good state, so we're okay there. But I need to recover my controllers. If that means deleting all of the controllers and redeploying them, and then synchronizing them with the manager, or fixing whatever network connectivity problem we're seeing, or whatever that might be, we need to repair our controller cluster. What about the distributed logical router control VM, right? The control plane part of the distributed logical router. If that's lost or powered off, right? If that's essentially not in existence for the moment, well, I can't manipulate my distributed logical router. Right? I can't change anything. Dynamic routing, right? This is where things start to get a little dangerous. Dynamic routing, my upstream devices will lose their adjacencies with the distributed logical router. But the data plane is still going to function, so I'll be able to go northbound, but traffic will not be able to come back southbound because it won't know where my logical networks are. So I really want my distributed logical router control VM to stay online if at all possible. Now, we can use vSphere HA to protect it. We can use Edge HA to protect it, right? So we've got a couple of different availability options. But I do need to protect my logical router control VM. If my DLR control VM loses connection with NSX Manager, well, what does that mean? That means that the host on which the distributed logical router control VM is running has lost message bus connectivity, right, with NSX Manager. So we've got an ESXi host level message bus failure at this point. That's what's happening if the DLR control VM loses the connectivity with NSX Manager. So we can't change anything, right? We can't change anything at all. If the control VM loses connectivity with the controllers, my data plane still functions, right? But this is in effect a control plane outage at this point. We'll maintain our adjacency upstream because the control VM hasn't gone offline. We simply can't talk to the controllers for one reason or another. So we can't pass any updates to the controllers. So I can't change things. We'll still work. Everything will still work on last known configuration. If the DLR control VM loses connectivity with NSX Manager and the controllers, and the DLR control VM and its routing adjacencies are still up. So the DLR control VM is isolated from the network somehow, right? The ESXi host on which it's running has lost VSFWD connectivity. We have lost NetCPA connectivity. The ESXi host's management interface basically is isolated on the network. We're still okay. We lose, obviously, all the management stuff, but the data plane is still going to function based on what we know. We're not going to lose adjacencies because we'll be able to talk back and forth over between the control VM and its upstream, and we'll be all right. So not to completely freak out here, but I do need to repair that ESXi host. What are some of my common problems? Configuration. Holy smokes, configuration. Routing protocol configuration is huge. Making sure that my routing protocol configuration of my DLR matches upstream, whether that's an edge or something else, right? Those things are critical. Transport zone misalignment. We talked about that. Things like that. We've got the distributed logical router is a little interesting in that we have a protocol address that we have to configure as well as a forwarding address, right? The protocol address is the routing protocol peering address. That's going to be an IP address on the logical router control VM and only on the logical router control VM. And then I've got a forwarding address, which is the logical interface, the uplink logical interface IP address that's distributed across all of my ESXi hosts. It's really easy. I've done it myself more than once when I'm configuring up my distributed logical router to flip-flop those, right? To put the forwarding address in the protocol address field and the forwarding address in the protocol address field. That's a big thing, right? If I've got those backwards, my adjacencies aren't going to come up. What do we recommend for routing configuration problems? Make sure the configuration is right. Plain and simple. Watch the logs if you need to, and you're absolutely convinced your configuration is right. We have at the Edge command line, the distributed logical router control VM command line, debug IP OSPF and debug IP BGP to actually get deep insights into the routing protocols and what they're doing. Common problems on the control plane. We've kind of gone through all those scenarios, right? NetCPA can't talk to NSX Manager. We didn't really talk about that, but that tells me that something's wrong with NetCPA or VSFWD. VSFWD to NSX Manager, right? That's used for a lot of things. Controller cluster, rare occasion, right? Very rare occasion we see a controller cluster kind of go a little bit haywire. Here what we state here, the controller cluster has problems with handling the master role. Sometimes that happens. Again, it's rare. It's rare. I've seen it, I think, twice, but I have seen it. If something like that happens, you bounce a controller, right? Just reboot a controller that kind of resets the cluster, redistributes the slices, and everything's okay. Invalid next hop. When I set static routes, I need to make sure that the next hop IP address is in a local subnet to one of my logical interfaces. Right? Has to be local to one of my interfaces. If I don't have, here I've got, invalid next hop shown on the screen, right? Next hop must belong to a given VNex subnet. Well, what that's saying is I don't have any interfaces, any logical interfaces on this router attached to the 192.168.100 network, right? I just have to have a locally accessible IP address from some interface on my network to have a valid next hop in a static route. So, look at all those failure scenarios. Holy cow. Lots of detailed failure scenarios. Most of them are just not going to be common, but we need to understand what all the different things are going to do. Lots of different things that can fail here. We'll talk about fixing them in the rest of this lesson. So, we have logical routers. We need to troubleshoot them. We maybe are lacking connectivity. We need to figure out what's going on, who's going on, where are we going. We've got maybe our documentation, but let's go and validate some things. Right? This is all about how do we validate that in the infrastructure itself. So I can go in and look at my distributed logical router. I can go into the NSX Edges UI, I can drill into my distributed logical router and look at the interfaces, and I can figure out which interfaces are connected to which logical networks. It's a good thing. What I would like to do at that point is take that network connection and go over to my logical switches UI and make sure I understand which VNI we're looking at, which network segment, right? Just so I have all of the information I need, right? All of the information I might need. Now, we can go in and look on the command line to see the general health of my logical switches in that, I can see what's configured, I can see whether I'm connected to the control plane, I can see a count of how many ports are attached to a given logical switch using the ESX CLI command as shown here. We do make a note when I attach my distributed logical router to a logical switch that does increase the port count naturally, right? I'm plugging something else into the logical switch. I can use the ESX CLI command with the network port list argument in the VXLAN namespace to kind of get an idea of what switch ports are configured. I can see the local switch port ID and the distributed switch port ID. The logical router ID is always going to be VDR port. I can see the VMKNIC ID associated with the VDS port. This tells me the uplink, or not the uplink, but the VM kernel port association, right? This gives me my VM kernel port or my VTEP association for this particular port. I can map that VMKNIC ID to the endpoint ID in the ESX CLI network vSwitch VXLAN VMKNIC list command that we're showing here, right? So this can tell me if I've got multiple VTEPs, this will tell me which VTEP we're going to use. Show logical switch host. We use this command an awful lot. This is the same output as net-VDL2 on the ESXi host, or net-VDL2-L for list, which gives me information about the ports. Here again, we see the VXLAN port for VDR port. We get the local switch port ID number and the VMKNIC ID, etc. So we get a bunch of the same kind of information, just formatted a little differently, gathered from a little bit different spot. Show logical router host verbose gives me information about a distributed logical router instance, very much like the net-VDR-I-L command, right? I for instance, L for list, gives me information at the command line about a given distributed logical router ID. I can look at my distributed logical router from the command line, from the central CLI, more specifically, show logical router list all, and that will give me an edge ID and a VDR name. So I can use show logical router host and then the host ID I'm looking for, right? Because we're looking at information on a particular host, DLR, and then the DLR name or VDR name, verbose. We see this output yet again. All right, so another different way to get that. Net-VDR capital L lowercase l default edge brief gives me a brief summary of my interfaces. We see the show logical router host ID command, the central CLI command equivalent right below that. Gives me a brief output of the logical interface configuration. To get a verbose output, I simply don't put the -brief argument on the net-VDR command we just saw, right, where I just get more detailed information about the logical interfaces. I can look at the routing table with the net-VDR -R command, or I can do the same thing with show logical router route, right, and have all the host and distributed logical router information we're showing on the screen there. Show IP route, well, that shows me the routing table on the edge itself. So I've SSH'd, I'm not on the ESXi host, I'm not in the central CLI, I have SSH'd into a distributed logical router control VM, or I've SSH'd into an edge services gateway, or I've opened the console and logged in locally, right? So show IP route shows me the routing table as far as the edge device locally sees it, right? And we can see there's not a lot of difference between the edge services gateway and the distributed logical router command output. I can also look at the forwarding table with show IP forwarding. Net-VDR, here we are back on an ESXi host. I can look at the ARP table or neighbor list for the distributed logical router instance with the net-VDR-N argument, right? So this gives me the ARP table, what we've got going on, what neighbors we know on this distributed logical router instance. Show control cluster logical routers instance all. This command is being run from the NSX controller clusters. So one more place to look for information. Not the ESXi host, not the central CLI, not the edge device itself, but the controller node that's running this. So I can look at all of my logical router instances. I need the logical router ID to move forward from here. So we can do things like show control cluster logical routers, interface summary, and then the router ID, right? Notice we just passed the logical router ID. This gives us kind of a similar output to my brief interface view from the central CLI or from NetVDR. Show control cluster logical routers routes gives me the routing table. But if we notice, there are no local or connected routes listed here, right? This only shows the non-connected routes. So static routes, dynamic routes, that's what we should see. Or that's what we will see here. But on the controller node itself, we will not see the connected routes provided by the connected logical interfaces. This is a really neat diagram, a really good reference. This gives us an idea of which net-VDR or net-DVS or net-VDL2 command, whatever, what ESXi host command gets us information about which component that we might be looking at, right? Whether we're looking at a logical router instance or VDR port or logical interfaces or what have you, right? So this is a good reference to kind of come back and look at. Now, I can also do packet capture on the DLR or the ESG with the debug packet command. Debug packet capture captures the data to a PCAP file. Debug packet display just shows to screen. I specify the interface and my filters and what have you. And then I can capture the data, and then I can copy the data off to look at it if I say captured to a PCAP file. But what about on my ESXi host? Look at all these places that we can capture traffic. Look at all these places. I can capture traffic as it leaves the virtual machine. I can capture traffic as it enters the distributed switch port. I can capture traffic as it enters the distributed logical router, as it exits the distributed logical router, as it gets to the uplink before we've encapsulated it, at the physical NIC after we have encapsulated it. I can capture traffic almost anywhere in the, actually not almost anywhere in the life cycle of traffic, from the virtual NIC all the way to the physical NIC as we're exiting the ESXi host. So this slide gives us a nice reference of what I would use, right? I would have to identify things like switch port ID numbers in my ESXi host, yeah, we can capture traffic almost anywhere. It's pretty fantastic. We have a lot of flexibility here, to gather information. So packet capture is great. We can do it from the command line. We provided a really neat reference right there. We can do it through the packet capture utility in the networking and security plugin now, and then NetVDR. Is great for pulling information if I have access to an ESXi host, but I also have lots of equivalent central CLI tools that we can look at for that as well. But what happens to a packet when we're using the distributed logical router? Where does it go? How does it flow through the ESXi host and then across the network to the destination ESXi host? Well, that's what we're looking at here. And we're starting here with an ARP request from the distributed logical router, right? That's the scenario we're looking at here. We want VM1 to communicate with VM2. Right? VM1 is on host A, VM2 is on host B. Those are who we want to communicate with. VM1 is attached to VXLAN 5000, VM2 attached to VXLAN 6000. So we need the distributed logical router, which is attached to both logical switches. VM1 is going to send its packet, right? We're just going to use an ICMP here. We're just doing a ping, nothing fancy. We're just showing the flow of the traffic. And so, in this packet, the source MAC address is VM1's MAC address. The destination MAC address is the VMAC, and then we've got the ICMP payload. So VM1 forwards this frame, right? I'm trying to get to this other IP address. It's on a foreign network, so I need to send this to my gateway. And that gets forwarded up to the logical switch. Right? The logical switch then turns around and forwards that to the VMAC address, to VDR port, where the frame with its VNI metadata gets published to the correct logical interface, or picked up by the correct logical interface on the distributed logical router. Now, in receiving that, right, the distributed logical router then does its processing to say, well, I need to get to virtual machine 2's IP address. I have a route connected that matches that IP address, so I can forward that destination out or forward a packet out that interface to the destination network. However, I don't know what VM2's MAC address is. Right? That's where this conversation really begins. That's what the title of this slide starts getting us to, is the distributed logical router needs to forward this ping to VM2, but it doesn't know how to get there. Right? It knows the IP address, but we need to get the MAC address because we're forwarding out onto a layer 2 network. Right? We've done our layer 3 processing now. So distributed logical router instance A on host A. Right? So the VDRB kernel module on host A packages up an ARP request and sends it out the destination interface onto VXLAN 6000. So the frame looks kind of like what we have here, right? The source MAC address is my VMAC, my VDR port. The destination MAC address is broadcast, and the payload is an ARP request for VM2. We've got some metadata that we tack onto that so that the distributed switch knows where to forward this frame. Now, if we notice, once we get through the uplink, right, because we're sending a broadcast, we forward this to the uplink, the DV uplink port on the distributed switch. Once we get there, we have to go through a series of I/O chains or I/O filters, one of which is a distributed logical router filter. The distributed logical router filter says, wait a minute. We need to do something with this. The VMAC is not what we need to keep, right? Because the VMAC exists on host A and on host B. So we'll get the ARP request on host B, but we won't know where to send that. We won't know where to populate that, who needed that ARP request. So what we're going to do in the DV uplink I/O chain before we encapsulate this to forward across the VXLAN transport network is we are going to change the payload, right? The encapsulated payload now. So if we look at the encapsulated packet, what we're sending to the destination MAC address is the VMAC. The VMAC over on the secondary host on ESXi host B, but the source MAC address has been changed from the VMAC to the PMAC, right? From the VMAC to the PMAC. And we did that so that we know where to send the response, the ARP response. And then we add in the outer payload, the encapsulated headers for VXLAN, right? We forward the frame across the network, across our VXLAN transport network from VTEP A to VTEP B. VTEP B receives the frame. In receiving the frame, VTEP B then de-encapsulates, right? The VXLAN I/O chain de-encapsulates the payload. The payload looks like this, right? We attach some VNI metadata to that says this is on VNI 6000. And my destination is the VMAC. My source MAC address is the PMAC address. So we forward that up. That gets to the logical interface on ESXi host B. Now this is an ARP request. The distributed logical router instance here on host B then says, okay, I need to ARP for VM2, for IP2. Right? I need to ARP for this VM's IP address, and then I need to return this ARP request to the source, the source DLR instance, the source VDRB module that was requesting this in the first place. So it turns around and sends an ARP request out through a broadcast back onto VNI 6000. And if we look at this, the source is the VMAC, the destination is a broadcast. We will filter that. This is not going to be flooded across the physical network. This is going to broadcast only in this ESXi host because of the filters we have, the natural filters we have to prevent loops and broadcast storms and things like that in the distributed switch. But we will send that, and that broadcast will ultimately get to virtual machine 2. Stay tuned. In another segment, we are going to look at the ARP reply. In another section, we saw the ARP reply or ARP request process using the distributed logical router. So, when a virtual machine wanted to talk to another virtual machine and the logical router was involved, how did the logical router actually pass the ARP from one host to another host so that we could update the routing, or the ARP table rather, on the LIF? Well, we saw the ARP request. What happens on the return path? Right? That's what this is all about. What happens on the return path? So if you remember, VM1 wanted to talk to VM2. So VM1 sent its ping to its gateway, the logical interface on the distributed logical router, and the DLR said, I need to figure out what the MAC address for VM2 is. So we sent the ARP request out. Well, VM2 finally got the ARP request. And so it processed it, and it's replying. It's replying to the ARP request. It says, hey, I'm VM2, I'm IP2, I'm MAC address 2. So let me tell you about that, right? Now, unlike an ARP request, which is a broadcast, an ARP reply is a unicast. So we've got a little bit more simple track here, right? So we send the ARP reply. The destination is the VMAC because that's where the request came from. So as that flows through the DV port filters, one of the things we're going to do is tack on some metadata that says, hey, this is on VNI 6000. So that MAC, that ARP reply will get to the distributed logical router to LIF, LIF A on VNI 6000, right? We'll get to VDR port and forward that up to LIF A thanks to the VNI metadata. So now what's going to happen, right? Now my distributed logical router technically has this ARP response. Technically, we've got this ARP response. Technically, LIF A knows where VM2 lives, right? Knows the IP to MAC mapping for VM2. But over here on host B, that's not who asked for that information. We have to get this information back where it came from, which happens to be the VDRB module, the DLR code on ESXi host A. So what are we going to do? We're going to take that ARP response, that ARP reply, and we're going to forward it out. Now the destination is not the VMAC. The destination will be replaced now with the PMAC, right, that we received from the source, so that we know where to forward this particular traffic, right? So we send that out to the logical switch. The logical switch picks up that the PMAC is not a local thing, so we forward to the uplink, right? All the while, the VNI metadata says this is on VNI 6000, and then we take that ARP response frame and we bundle it up into a VXLAN packet, right? So my VTEP packages up the ARP response. We've lost the VNI metadata. I don't know if lost is the right word. It gets moved into the VXLAN header, the VNI field there, and we forward this packet along to the destination uplink, or the destination VTEP rather. So the destination receives the VXLAN encapsulated packet. The VXLAN I/O chain filter de-encapsulates. The distributed logical router filter, right? Notice what happened here. Right? Notice what happened here. Look, the packet, the ARP response came into the ESXi host with the PMAC as my destination. The distributed logical router filter in the uplink I/O chain changed that DLR or that PMAC to the VMAC. Because the VMAC is how we're communicating with the distributed logical router. It's the MAC address of the DLR on this host, right? The PMAC is just an abstraction of that, if you will. Something we have if and when we need to send data or identify the source of data when it goes across the physical network. We attach to this the VNI 6000 metadata. at which point we forward the ARP reply up to LIF A on DLR instance A. So now both ESXi host A and ESXi host B know where MAC address 2 or VM2's MAC address exists, right? So we're updating all of the ARP tables all along the way where it's appropriate and necessary. So now, now the logical router can forward the traffic from LIF A over to VM2. So we've finally gotten our ARP request from LIF A propagated around, and then we got the response from that propagated back. So let's look at the overall packet walk now. What does it actually look like now that we're doing this? So VM1 sends its ping to VM2, right? That's destined for the VMAC address. The frame is destined for the VMAC address because we're on different subnets. We have to get to our gateway, so we're going to a non-local address. That gets forwarded up through the I/O chain to the DV port, where we tag in the VNI metadata that we're on VNI 5000. So we're going for, our destination is LIF B. So the traffic gets to LIF B. LIF B looks at the metadata, says, "Yep, that's what I'm expecting," and says, "Well, I'm looking for VM2, right? I'm trying to send this to IP2." We process the routing table, find that we have a destination for IP2 or a destination network for IP2, and then we look up in our neighbor table, our ARP table, to say yes, IP2, right? VM2's IP maps out to MAC address 2. So that's pretty awesome. So let's go ahead and forward this packet out, right? We'll rewrite the IP header, or rewrite the layer 2 header rather, and forward away, right? Off we go. So my source MAC address for the frame I'm forwarding is the VMAC address of the DLR. Destination MAC address is VM2's MAC address. And then we tack on the VXLAN 6000 metadata so that we know which logical switch we're on. The traffic gets to the logical switch. We forward it to the uplink because the logical switch realizes that MAC2 is over on a different ESXi host. So that traffic gets handed to the uplink and then handed to, the DLR filter doesn't actually do anything at this point. We simply pass on to the VXLAN filter in the I/O chain, which encapsulates the traffic and forwards out the VTAP. Right, so we are sending traffic destined to yet a different ESXi host, a different VTEP. The destination VTEP receives the ESXi frame, and as it's de-encapsulating, it looks at the VXLAN header so that it knows what metadata to attach to the frame, the internal frame, as it's forwarding onto the distributed switch. So we forward up through the uplink port to the distributed switch, an Ethernet frame destined for VM2's MAC address, and then the distributed switch simply forwards that MAC address to the appropriate distributed switch port, where VM2 then receives the ICMP, right? The response to that ICMP packet goes in precisely the reverse path. It does exactly the same things, except it's sourced from VM2 on ESXi host B. What about equal cost multipathing? We support ECMP both at the distributed logical router as well as at the edge services gateway. How do we monitor that? How do we validate that? How do we look at that? Well, here we're showing our OSPF neighbor tables on the distributed logical router and on the edge services gateway. We could kind of look at the same thing with BGP, but it's not going to be, BGP configures a little differently, right? Where I'm specifically calling out and configuring my neighbors, where OSPF is a more broadcast-centric kind of thing, right? And so we want to think about that. If I'm using OSPF, my distributed logical router is going to show all of my edge services gateways as neighbors. The edge services gateways are going to show far more neighbors, however, especially if I'm using equal cost multipathing upstream, because I'm going to show neighbor relationships on both the uplink networks of the edge services gateways as well as on the internal networks of the edge services gateways. So we're going to see, for many things, two neighbor relationships when we look at our neighbors in OSPF. We can look at the routing tables, right? The routing tables are going to be fairly telling for equal cost multipathing scenarios where we see lots of routes going one place, right? So in our distributed logical router, we have a bunch of zero routes, a bunch of next hop, default routes, if you will. On my edge services gateways, we will have a different set of equal cost multipathing routes, right? Heading further north still. I can look at the net VDR configuration of my interface on an ESXi host to get my VDR name, and then in my using net VDR, I can look at the routing table on an ESXi host to see that yes, equal cost multipathing is there. Most importantly, not because I have the multiple routes, but if we look at the flags, there is an E flag specifically to note that this is indeed an ECMP or equal cost multipathing route. So if I'm dealing with ECMP and equal cost, if I've got ECMP set up, how do I deal with failure? Well, the failure kind of automatically resolves itself. I get a little bit of a hiccup in traffic, but once my adjacencies fail for, in this case, edge 1, once my adjacencies fail, we'll be all right. We're going to redistribute those flows, rehash those flows that were being forwarded to edge 1 to other edges. So there will be an impact. Depending on your timers, your dynamic routing timers, will depend on how much of an impact that's going to be. Now, we've got some other failure scenarios to think about within the context of equal cost multipathing. If my distributed logical router control VM fails, my DLR control VM fails, what else fails? My neighbor relationship, my dynamic routing, my adjacency. When the edge says, oh, look, there's no more distributed logical router control VM, my neighbor is no longer there, then what's it going to do? It's going to flush those dynamic routes. It's going to flush those southbound routes to, in this example, my web app and database networks. So southbound traffic's not going to be able to get back in, right? Something upstream may still have a route that says, oh, well, to get there I need to go through my edges, but the edge will receive the traffic and will just drop the packets because it doesn't know how to get there. Traffic going northbound, on the other hand, traffic going northbound from a web server or an app server or a database server will still go because we still have all of those routes, even though we've lost the adjacency. Because remember, the data plane won't be updated if the control VM is not available. Right? So this is kind of a challenge. Now, once the standby distributed logical router control VM turns back up, we'll reestablish relationships and everything will come back to life. We'll get our routes and everything will be good again. But that could take a few seconds. How can we deal with this? How can we fix this? Well, one way to fix it might be to build a summary route of some kind. And this is naturally going to assume that you've got your logical network set up in such a way that you can summarize them. But if we create a static summary route, we could advertise that upstream or configure that static route summary upstream on your edges, on your physical routers and so on. So that if your dynamic routing goes away, then we'll be okay, right? Your static route will naturally need a larger administrative distance, so it's kind of a backup, a floating route rather than an active, normally used route. Now, what happens if the distributed logical router control VM and one of its peered ESGs, edge services gateways, are on the same ESXi host, for example, and that host fails? This is kind of a bad day. Due to the timing events of bringing these things back to life and resetting everything and rebuilding adjacencies and things like that, we have seen outages of as long as 120 seconds in this. So how do we avoid this, right? Because I don't want a 2-minute routing outage, and I'm pretty confident that you don't want a 120-second routing outage, right? 2 minutes. So how do we do this? Well, we want to make sure that in the edge cluster, right, wherever I'm hosting my edge services gateways, that I have enough hosts that I can keep the edges on one subset of the cluster and my distributed logical routers on a different subset of the cluster. So that if a host with an edge services gateway fails, it's not also going to have one of my distributed logical router control VMs. And that's going to mean judicious use of DRS anti-affinity rules or VM to host group rules to keep those workloads on separate pieces of your edge cluster. Restoring the edge appliance, when we talk about restoring the edge appliance in context here, we're really talking about somebody deleted the appliance and I need to recover it. That's really what's going on. I can simply, in the edge UI, right-click on the edge line entry and say, redeploy. The configuration for the edge is stored in the NSX Manager, in the NSX Manager database. And if I'm doing NSX Manager backups, the configuration is backed up on whatever cadence my NSX Manager backups happen. So backups are not really a big thing. Now, I can back up configuration elements of the Edge Services Gateway through the NSX APIs as well if I really want. But my configuration is really held in the context of NSX Manager, and that's where it's going to stay. If something happens to my Edge Services Gateway virtual appliance, then I can redeploy it here through the UI. Which wraps up the lecture more or less and brings us to a bunch of labs, right? Bunch of labs. Lab 15 is a data path lab. This is another lab where we're doing sort of like the logical switching data path, except now we're adding in distributed logical router packet capture to the mix so that we can see traffic as it enters and leaves the distributed logical router as well. Right? So this is kind of a long lab. There's just a lot going on here. The rest of the labs here are troubleshooting scenarios, right? Lab 16 will run the break script and then go through and we'll repair it when we're done. Lab 17, another troubleshooting scenario. Run the break script for Lab 17. We'll go ahead and validate the symptom. We will then, once we've validated the symptom, we'll start going through our troubleshooting, narrow down the problem, resolve the problem, validate that we have indeed fixed the problem, then run the repair script, just to be sure, right? Just to give us a clean slate, just like we have for every other troubleshooting lab we've done so far. Lab 18, another troubleshooting scenario. Lab 19, another troubleshooting scenario. And finally, Lab 20, one more troubleshooting scenario. Same thing for all of these, right? We run the break script, we verify that the symptom is actually happening, we then troubleshoot the problem, fix it, and then verify that it's fixed. So what have we covered so far in this lesson, right? We've talked about the Edge UI, we've talked about the Edge command line, the central CLI, all of the different command line interfaces we might look at. We've talked about what information we need when we're troubleshooting routing. We've talked about the interplay between the management and control and data planes. We have talked about packet capture. We have gone through packet walks of what happens. We've done some backup and restore stuff, right? Lots of good things. So distributed logical routing, big deal. It's important in context of your virtual network. We can deploy the edge for north-south traffic and the distributed logical router for east-west. We can deploy an edge in different sizes, but we need to know how to manage, how to troubleshoot, how to dig through all of these things so that we can effectively troubleshoot issues in our environment. Welcome back to the VMware NSX Troubleshooting and Operations course. This is Module 7, Troubleshooting and Operating NSX Security Services. So, security tooling and microsegmentation are a really, really big piece of the NSX puzzle. A lot of people are using security, or NSX rather, for security as a primary use case, and logical switching and logical routing and such may come later on. So it's kind of important to understand how to work with and monitor all of the security tooling, the distributed firewall and the edge firewall and guest introspection tooling and so on, so that we can have a good grasp of what's going on in our data centers. We've got this broken up into a couple of different lessons here. Lesson 1 is all about the distributed firewall. Lesson 2 is a lesson all about Service Composer and the identity-aware firewall. Lesson 3 is an edge firewall-based lesson, and then we'll wrap all that up at the end with lesson number 4, all about guest introspection. Lesson 1, the NSX Distributed Firewall. This is good stuff. So we're going to talk about the architecture, right? What are all the moving pieces in the distributed firewall? How do we deploy it? What are the different command line tools we can use to start looking at things like rule sets and whether or not the firewall is functional and all that kind of stuff. We're gonna do some operational stuff. We're gonna do some basic troubleshooting with firewalling. And eventually we'll get into a whole bunch of labs around the distributed firewall. So what do we have in NSX? Well, we've got a layer 3-4 firewall. That's the distributed firewall that we have had for ages, right? We work on a traditional 5-tuple, sort of ruling, right? Source IP, destination IP, source protocol, port, and action. But NSX 6.4 introduced something new. In NSX 6.4, now we have a layer 7 firewall where we can actually look at the signature of the application signature, more or less, that is in the packets, so that we could protect against, or not necessarily protect against, but say allow SSH traffic, no matter what port you're actually using for SSH, right? You could be using port 22 over here and 2222 over there and 2244 here, whatever, right? Because you may have lots of different ports in different cases, right? HTTP or HTTPS is another common example of where I'm using HTTP or HTTPS traffic across many different ports for many different things. We can actually do some very flexible things with the capability to look and inspect for an application instead of a port and protocol. So we've got that. Now, the layer 7 firewall is only intended for protection against east-west traffic, so workload to workload traffic. This is not not necessarily a replacement for fancier firewall devices, but it is here as an option. So what is the architecture? What do we have going on here? Well, I've got my web browser, my vCenter server, my NSX manager. These are the pieces I'm using to do my management of NSX. And we're going to have those everywhere. What else do we have? Well, on my ESXi host, I've got my user space agent, VSFWD. How many other times have we mentioned VSFWD in the context of this class? I've got some other stuff in the user space. We've got a VDPI, or a vSphere, a VMware Deep Packet Inspection Engine, where our layer 7 stuff comes in. that's installed now. I have a command tool set called V6.4 that allows me to kind of interact with the kernel module. The kernel module is called VSIP, right? VMware Internetworking Services Insertion Protocol. Say that 5 times fast. So I've got the VSIP kernel module in the hypervisor that's actually doing the core management of the distributed firewall. But the cool thing about the distributed firewall is that it's distributed, and not only does it live on each ESXi host, we have a filter called the VNIC firewall filter that VSIP manages. And that VNIC firewall filter is where the actual filtering happens, where the actual firewalling happens. And we have one of those attached to each virtual NIC. Right? We use the message bus to pass traffic, not traffic, but configuration information and statistics back and forth between the ESXi host and NSX manager. And there's our note about the VSIP kernel module. And I've said all of the things that we just called out up here, so that's all good. So what do we have to think about here? Well, what we're talking about here in Distributed Firewall Architecture 2 is the tables that we look at. So each VNIC firewall filter has a rule table, right, that has all of the rules enumerated for the distributed firewall. And then we also have a connection tracker table. The connection tracker table maintains a list of all of the allowed connections. So when a new packet comes into the distributed firewall, the connection tracker table is actually the first table that's looked at. So we look at the connection tracker table to see if that flow has already been allowed. We claimed this a net new packet, so there's nothing in the connection tracker table. So we move on to look and evaluate the rule table, and then we evaluate that packet against every rule in the list until we find a match. The match then, depending on the action, if we block the traffic, right? If we match on a block, we'll simply drop the packet and move on. If we allow the traffic, if it's an accept or a forward rule, then we will forward the traffic and update the connection tracker table with that new flow. So I've got one of these table sets, right? Rule and connection tracker table. One set for each VNIC firewall for each virtual machine. So here we just have a little bit bigger or a little bit more detailed view about the layer 7 firewall componentry. So we work with NSX Manager works with vCenter Server to make sure we've got inventory for my virtual machines and all that stuff. The NSX Manager makes sure that my rules are applied, and VSIP will program anything in the VNIC firewall. And VSFWD will also pass information to the VDPI engine, right? Remember, VDPI lives in user space, not in the kernel. So there's information passed between kernel and the VNIC firewall, so between kernel and user space. And so all the signatures are stored in VDPI, and that's where they're evaluated. And so once we understand the flow and the context, then that gives us an awful lot to work with as far as protection is concerned for our context-aware firewalling. Now, I can validate that my hosts are prepared and ready for the distributed firewall by making sure that one VIB is installed on the host, ESX-NSXV. Right? When I prepare the hosts, I get all of the kernel modules, all of the user space stuff for NSX. So I prepare my clusters and I get VSIP and I get logical routing and I get logical switching and I get all of these tooling and toolkits installed. We can look to see if the kernel module is installed with the vmk load _mod command. And naturally, we just look for VSIP and that'll tell us that VSIP is there. I can look to see if VSFWD is running, right, with the PS command. I can look to see if the VDPI services are running by using, again, the PS command and grepping for VDPI instead. Now, both of these services, VSFWD and VDPI, are both multi-threaded. So we'll see many well, maybe not many, but one or more entries in the process list, we're seeing the process and the subthreads. And then in the Etsy initd, I can look at vShield stateful firewall, or I can look at vShield protocol inspection, right? vShield stateful firewall is it's VSFWD. We've seen that before in this class. We have not previously seen vShield protocol inspection, which is my VDPI engine. So that's how I can start and stop and check the status of that service. But what if I don't want the distributed firewall installed on a given virtual machine, on one virtual machine or another? Well, we have an exclusion list to do just that. The exclusion list, right? So I go right to the firewall UI and there's an exclusion list tab. The exclusion list gives NSX a list of virtual machines to not even install that VNIC firewall filter on, is what we're doing, right? We're excluding them from the protection of the distributed firewall. There are very few virtual machines that really meet the criteria to be put in the exclusion list. Things like your vCenter server, right? Limit the things you put in your exclusion list to absolutely critical workloads, right? And when I say critical workloads, I mean critical to the function of your infrastructure, not say business critical, right? That's a different kind of critical. Things like vCenter server. Your NSX virtual machines are automatically excluded, right? They don't even show up here, but they're excluded. So be careful with your exclusion list. There should be very few virtual machines in this list. So what are we talking about? We talked about the VDPI architecture. We talked about the distributed firewall architecture. We've talked a little bit about the exclusion list here in this first segment. I might want to look at my distributed firewall through the command line. Maybe even through the central CLI, right? The central CLI is a good place to kind of start everything. However, I need to get some information before I can actually start looking at information in central CLI. First thing I need to do is suss out some ESXi host IDs. So how do I do that? Well, the easy way to do that, the way I always do it, is a couple of commands. It takes an extra minute, but it's quicker and easier perhaps. Is from the central CLI, if you type show cluster all, that enumerates out all of the clusters in your infrastructure. That's important because we need the domain ID, the cluster ID for the cluster to enumerate the ESXi hosts in that cluster with the show cluster command again. So show cluster all lists out all of the clusters, and then show cluster ID enumerates out the ESXi hosts in a given cluster. And then I can look at the ESXi hosts and find the host ID. Once I have the host ID, I can go in and look at what virtual machines are on that host and get the virtual machine ID. So show host, then the host ID gives me the host and all of the virtual machines and the virtual machine identifier. And then I can type show VM, and then my virtual machine ID. Show VM gives me a list of information about the virtual machine, including the VNIC name and ID, and more importantly, in context here, the filter name for the VNIC firewall filter, right? The VNIC firewall filter. The VNIC firewall filter name is always going to end in -VMware-SFW.2. Right? What comes before that may vary a little bit, but it's always going to be the -VMware-SFW2. Write this filter name now down, copy it off to a notepad, something, right? Make note of this. We also need the host ID. Now, I can get the filter name from the ESXi host as well. I can use the summarize dvfilter command. Here's the trick with summarize dvfilter. We see on the screen a whole bunch of output, and that's going to go on and on and on because summarize dvfilter will list out for you all of the filters for the ESXi host, for all of the virtual NICs built on this ESXi host, instantiated on this hypervisor. So we do give you here an orange kind of a filter that you can look at. You can, a grep command that you can pipe your summarized DV filter to kind of minimize what you're actually going to be flooded with on screen. But summarized DV filter is your command to get the VNIC firewall filter name if you happen to be connected to an ESXi host. If you're on the ESXi host, you can take that information and use the vsip ioctl command to do things like get rules, right? So vsip ioctl is the command we would run, and then there's a sub command, and then -f filter name, right? We need to use that over and over again. And get rules gives me the active list of firewall rules applied to a given VNIC firewall filter. Right? From a practical perspective, we're generally looking at this and saying this is the list of firewall rules applied to a given virtual machine. Right? So I can look to see what the active rule set is, what we're actually filtering against, compared to what you might think you're filtering against. Right? This is a good thing to understand. Right? vsip ioctl get rules. Here we're just showing an additional example. Not only do I have accept rules, I have a reject rule. So we're showing the reject action here. Instead of just accept and deny, we also see reject. And we should see what happens when we have a reject action. What you might see on your client. Now, the distributed firewall is really, really cool. We build all our firewall rules in the UI using security groups or virtual machine objects or logical switch objects or whatever other vCenter objects we might use. But when it comes down to it, ultimately, my distributed firewall is just a layer 3-4, layer 7 firewall. My sources and destinations still need to be IP addresses. Right? My source and destination addresses still need to be IP addresses. There's no magical metadata that says this virtual machine belongs to that cluster or this packet is being sourced from a virtual machine in this resource pool. There's nothing that fancy going on here, right? It's a game of abstraction. So we can actually see, if we look at this rule set, there it is, right? Rule 1009 at the top, right? From any to address set IP security group 13, right? That's a security group object in my destination. Well, what's in that security group object? That's what this command is all about. That's what vsip ioctl get address sets is all about. This will tell us what the address set object translates to, right? So what IP addresses are included in a given address set object. Or in all of the given address set objects calculated for this particular VNIC firewall filter, right? So very useful. I can take this and I can go one step further in populating the active rules associated with this virtual machine. I can look at log files to get message bus information. Why is this important? Because I get my rule set changes at the ESXi host over the message bus, from the NSX manager over the message bus. So VSFWD, very important thing. I can look at my VSFWD logs to make sure I don't have any connectivity problems. I can look at my RMQ variables. I can look at the RabbitMQ, the RMQ IP address variable specifically. I can get that to make sure that my NSX manager IP address is that variable. I can look at my ESX CLI network IP connection list to validate that I have TCP 5671 connections established to that IP address. Those are things that tell me I have my message bus configured and ready to go. Now, what happens if the message bus is down? Right? What happens if VSFWD is down? Well, to the distributed firewall at large, nothing happens. To this specific host, though, I can no longer get rule changes, right? We can't publish anything new. I don't get any distributed firewall rule set changes. Anything that's already there is still fine, right? The data plane functions at last known configuration. If VSFWD goes down, it's not like we're going to flush all of the vSIP configuration because the message bus has gone away. We're going to leave all of the vSIP configuration as is until we receive something new. So anything we already have programmed is good. Anything new is not going to be published, right? If VSFWD just crashes, it's not a big deal. We've got a watchdog, right? We've got a watchdog paying attention to VSFWD. We'll just kick VSFWD back into gear, and off we go, right? You won't notice it. I won't notice it. If you're watching the logs, then you might see it. But every time VSFWD gets restarted, NSX Manager will be called to give me a full sync of all of my distributed firewall stuff and everything else for that matter. So if I've got VSFWD constantly bouncing on a host, then maybe I'm going to see some resource utilization go up, but I'm not going to see a functional issue with my ESXi host. If you stop the firewall manually, the watchdog's going to stop too. What if NSX Manager is unavailable? Well, if NSX Manager is unavailable, that's kind of like my message bus is unavailable, except my message bus is unavailable for everybody. Nobody gets any updates to distributed firewall stuff, whether it's distributed firewall rule updates or address set or IP object or vCenter object updates. So all these cool dynamic objects we have, they'll stop updating. So if I add a new virtual machine to a resource pool and I'm using that resource pool in a firewall rule, that's not going to be updated until NSX Manager comes back to life. So keeping NSX Manager online, not a big deal, or it is a big deal. Let me rephrase that. It is a big deal. It's not the end of the world if NSX Manager goes offline for a couple of minutes, but you probably want to bring it back fairly quick, right? Hopefully it's just an ESXi host failure that took the VM down. It'll come back in a second and everything will be good. So we talked about how to deal with ESX or VSIP iOctal. Something that we really didn't mention after talking about how to get the host IDs and the filter names and such is the show DFW command. So show DFW gives you the central CLI equivalent to VSIP iOctal. And that's kind of what we have, right? What happens when NSX Manager fails and so on. So that kind of wraps this one up. So what if I want to monitor the utilization, the resourcing in my distributed firewall? How much CPU am I consuming? How much memory is my firewall consuming? Things like that. We do have some event thresholds that can be configured in the distributed firewall. Now these are configured actually through the APIs, so we can look at them. We can configure them through the NSX APIs, and what they give us is a way to monitor the amount of CPU utilization consumed by the distributed firewall, the memory heap sizing consumed by the distributed firewall, and the connections per second that are flowing through the distributed firewall. Now, by default, out of the box, by default, these values are 100% CPU, 100% memory, and I forget some crazy number of connections per second that more than likely our environments are not going to hit. So it's effectively disabled. But we can tune those numbers, right, to whatever threshold you need. The polling interval. How do we get events out of this? How do we get threshold warnings out of this? Well, it takes some time. VSFWD will poll every 10 seconds for these threshold numbers, right? CPU utilization, memory heap utilization, connections per second. We'll look every 10 seconds, and we will generate a system event starting on this host. We'll generate a system event after 20 polling cycles have been exceeded. So what we're looking at is an event will be triggered just over 3 minutes if I have a sustained condition, right? It'll be just over 3 minutes that'll be triggered. So just be aware of that. And these events are logged to syslog on the ESXi host to syslog on the NSX manager and to the events, the system events on NSX that we can look at through the UI. What's also nice about this is in NSX Manager, my system events can be configured to trigger SNMP traps as well. So there are a number of different things a number of different ways we can be alerted of these performance thresholds being broken. So in the VSFWD log, we see something like what's on the screen, where we get the DFW CPU usage exceeds threshold message. Right below that, we see the system event message in NSX Manager's syslog. There will also be an NSX system event in the UI with all of this exact same information. And we can kind of, we would come in and find that here in under events and then system events. Looks like there's not a utilization event, a threshold event here, but we can see, all the different kinds of system events, a number of different kinds of system events that we might run across. Now, what about flow statistics? Right, flow statistics are very useful when we are looking at firewall rules. Right, how heavily used is this firewall rule? We can turn that on. I look at that through the UI here. I can use the drop-down menu over here that we're pointing out and click the stats button, right, the show hide columns. That gives me a little chart-looking column called statistics or stats in my UI. And I can click that, and that brings me out a call-out box, a dialog box that shows me the flow statistics for the last 24 hours. So this flow monitoring is only what's happened in the last day. This also requires that I have flow monitoring enabled on my NSX infrastructure. I can also look at statistics using vSIP ioctl or show DFW if I'm looking at the central CLI. So I can use the vSIP ioctl get rules -s command, S for statistics, and I can see how many times we've evaluated a given rule, how many times have been inbound, how many times have been outbound, how many packets inbound and outbound, how many bytes have we seen through this rule. So we can get some pretty solid statistics there. I can also get some additional filters or some additional statistics with the vSIP ioctl get filters command, right, which is going to give me a list of all of the filters with the -s for statistics, and that'll give me additional statistics for this filter, right? So it should be kind of an aggregate. So it'll show me timing for this VNIC firewall filter. How much latency is this adding? How much latency per packet? How many packets per second? Right? All that kind of stuff. I can do vSIP ioctl get flows to see flow data for this given VNIC firewall filter as well. But again, I have to have flow monitoring enabled. If I see something like this where I do a vSIP ioctl get flows and have a no records found, flow monitoring is not enabled. What if I want to capture packets? I can do that, right? Packet capture, packet cap UW on my command line, packet cap UW --dv filter, right? --dv filter, and then my NIC, or my filter name rather, that'll tell packet cap UW to capture traffic going into that filter. Now, what if I want to capture traffic coming out of that filter? That's the --stage argument, right? Stage 0 is before the filter. Stage 1 is after the filter. So we could look and see what's going into my distributed firewall and compare that to what's going out. We can save this file like we're doing here with the --out file, and then just pull that file down to, say, a machine, and open it and say Wireshark. So we've got some different monitoring thresholds that we can look at. We've got system events that we can look at. We could capture traffic coming into or leaving the distributed firewall filter. Lots of cool stuff we can do for monitoring traffic in our distributed firewall. The distributed firewall has a spoof guard component to it I can enable spoof guard. I can trust IP addresses on first use. I can manually approve IP addresses. Depends on my use case. Whether or not how much control I want over the IP address that we associate with a virtual NIC. I can use VSIP by Octal to get my spoof guard information. What information has or does the distributed firewall have for me for a given virtual NIC? So that's kind of a cool thing to look at. Now, we have more than one IP discovery mechanism in NSX these days. Once upon a time, the only mechanism we had was this VMware tools mechanism. And what happens is, because we've got to be able to associate an IP address with the virtual NIC of a virtual machine. And VMware Tools is a very easy way to do that, because VMware Tools gets this information, or gives this information to vCenter Server, right? If you've ever looked at a virtual machine summary page in the vSphere web client, there's a little section up near the thumbnail of the virtual machine console that says, what are my IP addresses? What are the IP addresses associated with this virtual machine? That information is delivered to vCenter by VMware Tools. So we already have that information. So NSX Manager requests that information from vCenter. That's great until VMware Tools isn't there, right? How many guests do you have that don't have VMware Tools for one reason or another? It may be more than one. Maybe it's a guest operating system for which we don't have VMware Tools. Maybe it's, maybe there are other reasons. Who knows? But not everything has VMware Tools, right? Plain and simple. VMware Tools does not exist everywhere. It's as ubiquitous as we can make it, but the data center is far and wide. So there are a lot of things that are going to slip through the cracks. So VMware Tools is not always the right answer. And let's face it, VMware Tools is software. VMware Tools could fail. If VMware Tools is stopped by an administrator, or the services crash and they can't report things to vCenter Server, well, all of a sudden these virtual NICs don't have IP addresses as far as NSX is concerned. So how do we work this otherwise? What kind of workarounds do we have? Well, I can manipulate the IP discovery mechanism to do either DHCP snooping or ARP snooping, or both, where now at the distributed firewall, we're going to watch for DHCP requests and offers and replies and all that. We'll watch for ARP entry or ARP requests from the virtual machine, right? All kinds of common traffic coming from a virtual machine that will have its source IP address. So we'll watch for that. The vSIP kernel module will then hand the information that we learn to VSFWD, which will then be passed up to NSX Manager. And this is great because this is going to happen whether we've got VMware Tools running or not. We'll be able to identify IP addresses for virtual machines, and it also would provide us a safeguard against somebody stopping VMware Tools or VMware Tools crashing in a virtual machine. I can change this on a cluster-by-cluster basis in the host preparation UI. We could also change this on a global basis through the SpoofGuard UI. There's a change IP detection button. And what we're looking at with IP detection is I can enable either DHCP snooping or ARP snooping, or both. If I choose ARP snooping, I can define what is the maximum number of IP addresses that I will learn for any given virtual NIC, right? The maximum number of IP addresses that we can learn for a NIC, for a single VNIC, from ARP is 128. So we want to think about that. For most of us, one IP address learned through ARP is probably enough. But if I have applications where I have more than one IP address assigned to a given virtual NIC, then I probably want to crank this number up at least incrementally to meet that requirement. So, in SpoofGuard, here we see the SpoofGuard UI, and if we looked up near the top of this UI, there's the IP detection type that I can change. But what we're also showing here is where we tell you, as NSX tells you and as an administrator, where we learned a given IP address. So I can go look at my virtual NICs, and I can see in the source column where my IP addresses came from, right? In this particular example, we're seeing IP addresses, the same IP address from both VMware tools and ARP snooping. So I can go look at that. Now, this drop-down menu, this view drop-down menu, is where most of my management of SpoofGuard actually happens, where I can look at my active NICs or unpublished virtual NIC IP addresses, where these are the things I've learned that I still need to approve, and so on. So this is a good drop-down menu to be familiar with. The distributed firewall can log rule matches. It can log its packet logs to the ESXi host. But since the distributed firewall is just that, it's distributed, we may not want them to stay local to the ESXi host. I can change the syslog server on an ESXi host by selecting the host in the vSphere client, going to the Configure tab, going to Advanced System Settings, and looking for the syslog global log host variable, where I can plug in the URI to one or more syslog servers. Right, and that's a good idea because then I can have all of my packet logs forwarded to a single syslog server that I can then use to make sure that my distributed firewall is doing its thing, no matter what host my virtual machines are on. If you're using vRealize Log Insight, there are integrations where Log Insight can actually reach out to your vCenter server and to your ESXi hosts to automatically set this variable to go and point to the Log Insight server. If I want to look at the logs, var/log/dfw packetlogs.log, this is where my log or my rule matches and session terminations and things like that are matched. So the top part of this screen, we show the rule matches. Bottom part of the screen, we see that when a session is terminated, we tell you, and we show you how it was terminated and how many, what the statistics were for that flow and so on. So we can get a lot of information out of the dfw packetlogs.log file. The distributed firewall also maintains an audit log for my distributed firewall. Under events, instead of going to system events, I can go to the audit logs button and I can see all of the audit events for NSX, whether it's a simple login or a configuration change for the firewall or what have you. And I can hit the little I, the information icon, to actually see the pre and post change configuration. So we can actually we're not only going to tell you that something did change, we'll give you the information to identify precisely what it was that changed. So we've talked about the architecture of the distributed firewall, VSIP and VSIP iOctal and VDPI and VSFWD and all these different moving pieces, the NSX manager, etc. We've talked about configuration of the components, looking at status, digging through VSIP iOctal and show DFW and all these different things. We've talked about threshold monitoring. We've talked about some basic troubleshooting tooling. A lot of good stuff here and a lot of good security stuff yet to come. NSX 6.4 Troubleshooting and Operations, Module 7, Lesson 2, NSX Distributed Firewall, Service Composer, and Identity Firewall. Two big, neat pieces of security. So we're going to talk about Service Composer a little bit, and we're going to talk about security groups and security policies and configuration backups, and we're going to talk about the Identity Firewall just a little bit here. So what is Service Composer? Service Composer is a security policy application orchestration tool. Right? Really what it is. It has two main pieces. Right? Two main pieces. A security group. The security group is going to be some kind of grouping of virtual machines. These are the things that you want to protect. Then you've got a security profile, or a security policy rather. The security policy is a collection of distributed firewall rules, or guest introspection policies, or network introspection policies, or a combination thereof, that ultimately defines how you want to protect a security group, right? So you've got what you want to protect in your security group and how you want to protect it in your security policy. So I can go in through the Service Composer UI and create security groups and create security policies, and these things will all be synchronized as I create them, right? Synchronized through the message bus to all of my ESXi hosts from NSX Manager. If there is a problem, we'll tell you. And if there is a problem, we'll tell you what the problem was. Guest introspection policy in this case didn't synchronize properly. But we can automatically try to resolve that. So I can just hit the resolve all link and we're going to try again. Right? Maybe there was some network contention or something happened, or there's some host level contention that means the guest introspection service virtual machine wasn't responding properly. Who knows what it was? Maybe if I try and resolve it, it'll be all right. I have another option in Service Composer about how the firewall rules are applied. By default, the firewall rules in Service Composer, just like the firewall rules in the firewall UI, are applied to this object called the distributed firewall. This distributed firewall object is, well, it's just like it says, the entire distributed firewall. So I can create security policies and apply them to security groups, and then the firewall rules in those security policies, instead of just being applied to those security groups where I intend them to be, they're applied to the entire distributed firewall. That's probably not what we want all the time. I'm not going to tell you how is best in your specific environment to do this, but we can edit the applied to value for my distributed firewall rules and change it from the distributed firewall to the policies security groups object, so that the distributed firewall rules in a security policy are applied only to the workloads in the security groups to which that particular security policy is applied. Now I can export my Service Composer configuration. This could be useful as an ad hoc backup, or maybe as an export of my Service Composer configuration. In this case, we're doing our policies. My policy configuration to import in maybe to a secondary site where I want to make sure my policies are synchronized, right? That could be a thing. I can export my configuration here, and then I can turn around and import my configuration to another NSX manager. All right, so there's our import configuration button on the screen. Then we have an identity firewall. The identity firewall allows me to create firewall rules that say, if a member of this Active Directory security group tries to access that destination IP address on this service, allow or deny, right? So my source of my firewall rule can be an Active Directory user or group. My client, my source can be either a physical machine or a virtual machine. We're not concerned. If it is virtual, we do need a complete VMware tools installation deployed, not just the typical, but I need the complete installation. And this is only going to work with Windows guests, right? Windows guests. We're leveraging the guest introspection framework. If we can, that's a much cleaner way to do things, but if that's not available for any number of reasons, we can actually also watch Active Directory event logs. Right? So NSX Manager can actually tie into Active Directory and event logging, assuming you provided access, and we can watch Active Directory log scraping. So if I have problems with this, what are some of the things I need to worry about? Well, I need to worry about my Active Directory sync is working. So I need to make sure that my security groups are up to date, right? Do I know all of the current things with NSX Manager or in NSX Manager, right? Do I know all of the current things about Active Directory that I need to know? Can I get to log scraping? Do I have guest introspection deployed? Is guest introspection healthy in my infrastructure? Is VMware Tools installed? Is VMware Tools running in the guests? Things like that. We do have a gotcha down here at the bottom of this slide that I want to make sure I call out. Multiple user identity firewall cannot be used with context-aware firewall. So let's break that down just a little bit. My identity firewall was enhanced in NSX 6.4. Now we can do things like identity-based firewalling on RDSH servers. The cool thing about that is that I can have 4 or 5 different people logged into an RDSH server and have different firewall policies associated with each of them, right? Different policies associated with each user at some level, right? But right now, that would also mean that for that RDSH server, I can only use traditional layer 3-4 rules. I cannot use layer 7 rules in that context. That's what that means, right? So I'm going to have to pick one or the other right now. Well, how's this for a list of labs? You ready to spend some time in the lab? What is that? 11 labs ahead of us, 9 of which are troubleshooting scenarios, right? 9 of which are troubleshooting scenarios. So first things first, lab 21, we're going to kind of look at the configuration. We're going to make sure that the management plane and the data plane are functioning for the distributed firewall. Lab 22, we're going to start getting into some packet capture to watch the behavior of the distributed firewall, watch the data path, watch the data flow. We're going to watch distributed firewall logging, some kind of cool stuff here. And then we get into troubleshooting scenarios. Now, lab 23 is another login site specific lab. So we're going to run our break script. We're going to validate that the system's not working. We're going to look at the symptom. And then task 3 will guide you through. Guide you right through running or detecting the problem in Login Site. And then we'll troubleshoot and fix the problem. Should be fairly easy at that point. Verify that it's fixed. Remove the configured firewall rule. Very important. And so, if you've paid attention to what I've been saying about the rest of the troubleshooting labs, right? Break the lab, verify that it doesn't work, fix it. Verify that it's fixed, run the repair script. This is where running the repair script becomes critical because for many of the labs that we might run into here, maybe we're creating new firewall rules or we're manipulating firewall rules, and we might be able to fix things a couple of different ways. Running the repair script will reset the firewall rule set back to the default rule set that we've started with the rest of the time. So let's just stress that here. Lab 23, 24, 25, 26, 27, 28, 29, 30, and 31 are all troubleshooting exercises. So at the end of each of these, run the appropriate repair script, please. Your life will be much easier, I promise. I promise it'll be easier. So what have we learned so far? We've talked about Service Composer. We know what makes up Service Composer. We know how to back up Service Composer and import data into Service Composer. We've talked a little bit about the identity firewall. Lesson 3, the NSX Edge Firewall. So the NSX Edge Firewall is not distributed. This is part of the Edge Services Gateway. So this is the firewall on our north-south ingress-egress point to our software-defined data center. So we're going to be protecting against different things or allowing or denying different things here than we do at our distributed firewall. So we'll talk about the Edge firewall a little bit. We'll talk about the command line to investigate and to look at the Edge firewall. Remember, almost all of the command line stuff that we're doing here in all of NSX is to gather information, not to actually make any changes. So the edge firewall, the NSX edge firewall monitors north-south traffic, right? This is on my ingress-egress point to the software-defined data center, right? And the edge gives me all kinds of capabilities in that north-south context, everything from NAT to VPNs to firewalling, etc. We have a firewall in the edge that will protect the edge and things that hang out behind the edge. And we've got a couple of different rule types that we might want to look at in the edge. We have pre-rules, which we're not actually showing here. So I can build my rules in the global firewall UI. So the same place I build distributed firewall rules, I can just change my applied to value to specify an edge or all edges. Those rules will show up as what we call pre-rules, and they will show up at the very top of my firewall list if I'm looking in the edge firewall UI, kind of like we're looking at the bottom part of the screenshot here. So above and beyond pre-rules, I've got my default rule, right? The rule at the bottom. What am I going to do if nothing else matches? Am I going to allow or deny? I have user rules, which are the rules that I'm going to create as an administrator. And then I've got internal rules. There's an option when I deploy an edge services gateway, and then I can manipulate it later. But when I deploy an edge services gateway, there is an option that says, do you want to enable automatic rule generation? And one of the things that does is it will automatically generate rules for network services related, or for services related to things that I've enabled on my edge services gateway. So if we look at the screenshot here, we actually have a routing routing firewall rule, not distributed, a routing edge firewall rule that's internal that was created when I enabled, what are we running here? OSPF. Right, so when I enabled OSPF, the automatic rule generation created a firewall rule on the edge that said, I will accept OSPF traffic, so that I can do things like share LSAs and spout my hellos and all that kind of stuff. Now, from the edge command line, we have a bunch of stuff that we can look at, right? I can do a show configuration, I can show IP sets, I can show logs, I can show tech support, I can show firewall, all kinds of things, right? Show firewall flows, show firewall rule IDs. So I can look at my flows, I can look at my rules, I can look at my flow table, show flow table, and I can look at different flow specs, and I can top talkers and so on, just like I can with my rules. So we've got a relatively, I would argue, a relatively familiar command line structure for all of this, naturally depending on what things have been managed, what things you've managed in the past. So here's show configuration firewall, which gives us some information about how the firewall is configured. So this gives us the firewall stanzas in the edge configuration. Show configuration global that we're showing here. This gives me things like, is FIPS enabled? What's the edge ID? What's the tenant ID? Is logging enabled? So this is kind of part of my global configuration, but it's still important in the context of my firewall. Show IP set, very much like vSIP ioctl get address sets for the distributed firewall. I probably want a way to look at different IP sets so that I can see what IP addresses are mapped to what abstracted objects. So that's the edge. The edge firewall is actually pretty straightforward when it comes down to it. It's very simple. It's easier. There are fewer moving components because it's all self-contained. It's not distributed, but it's still a stateful firewall, and it still has a nice UI and CLI command set that we can use to manage it. Lesson 4, NSX, guest introspection. So we're going to talk about our side of the guest introspection tooling. This is a little bit of a challenge for us here in education because guest introspection in NSX is almost entirely reliant, as far as functionality, on partner solutions, right? That's That's its sole, really its sole purpose, right? Is to give partner solutions a way to deal with guest introspection and look inside the guest. So we really don't talk about partner stuff here, but we will talk about all of the VMware stuff, the NSX specific stuff that enables all of the partners to do what all of the partners do, right? To enhance NSX so very, very well. So what do we have? What are some of the components that we might think about, right? We have a guest introspection security virtual machine or service virtual machine, right? A dedicated service virtual machine that is deployed to each ESXi host. The service virtual machine is there to provide offloaded processing, centralized processing in a distributed fashion, if that makes sense. So, we're going to have our guest introspection service virtual machine, and then our partners will have their own service virtual machine. So if I have an antivirus solution, for example, the antivirus service virtual machine will be doing all of the antivirus scanning, even though we're scanning the different guests through the guest introspection workload, right? So it's a very flexible infrastructure, but I need one of those service virtual machines on each of the ESXi hosts. So what else is involved here? Well, NSX Manager is obviously involved. I have a partner management solution, a third-party management console of some kind, and that management console will be registered with NSX. There's our guest introspection service virtual machine, as well as the NSX services, the hosts being prepared by NSX. And then we've got our partner service virtual machines that are the ones actually doing the really cool work. And then we've got our local guest introspection tooling on the ESXi host that we'll talk about in a little more depth coming in here soon, right? There may also be some network introspection going on, right? So when we talk about partner in security service insertion, we could be talking about guest introspection. We could be talking about network introspection or traffic redirection, right? If we're doing guest introspection, then we've got a multiplexer that we're going to install, and we'll talk about that a little bit as well. So, how's this? Is there enough going on this slide? This is talking about all of the different things that are happening during a guest introspection file scan. So antivirus, vulnerability management, those types of things where we have to be able to read the files inside the guest OS. So NSX Manager and the guest introspection service virtual machine are talking to one another. The identity firewall and endpoint monitoring perhaps are talking to the EPSEC lib library, the endpoint security library that we've written in the and put into the guest introspection service virtual machine. My partner management console, NSX Manager, are talking to vCenter by way of APIs. My partner management console and NSX are communicating by way of the REST APIs, the NSX Manager APIs. And then Service Composer and NSX Manager, my third-party management console, they're all kind of talking to the partner service virtual machine through the network and kind of implementing how these scans are going to take place, leveraging EPSEC lib again, just like in our guest introspection service virtual machine. Those guest introspection requests, right? The file scanning requests are going through an internal VNIC to the multiplexer, where the multiplexer can then, through a VMCI channel into the virtual machine, act on those file scan requests to a thin agent, which is why we need the complete VMware tools install. Communication goes to that VMCI or that thin agent over VMCI, where we can then read the file, and the third-party service virtual machine can scan for whatever it's scanning. Now, That's guest introspection. What about traffic redirection or network introspection? Well, this is a little different. This works in a similar fashion to the distributed firewall in that my redirection module is a DV filter slot, much like the distributed firewall, the VNIC firewall. Right? The VNIC firewall is always going to load into DV filter slot 2. All right, that was what we were looking at in the command line previously. But we also have DV filters slots 3, 4, 5, 6, 7, 8, 9, 10. There are 16 slots total indexed at 0. So slots 0 through 15. Slot 4 is the first slot where we might install a guest or a partner network introspection solution. So what happens is when I have that network introspection solution in play, maybe through the Partner Security Services tab or through a Service Composer security policy, we will have redirection rules applied to the VNIC firewall filter and to the partner introspection DV filter, so that as traffic passes, rules are evaluated just the same. And if we are told to redirect the traffic, we redirect the traffic. The partner services virtual machine processes based on whatever policies are set up in its management console. And if traffic is to be forwarded, it's simply returned to the DV filter to be forwarded on. Now, I can look at NSX Manager as I'm registering a partner solution, and you'll see we've got highlighted here a number of log messages that are kind of showcasing that, yes, a partner security solution is being registered, and it's being registered successfully. I can also look in my service definitions in my networking and security UI to see whether or not the solution has been successfully registered, right? Here Trend Micro Deep Security is being highlighted, but it could be any number of other partner solutions. From there, I can go into installation and upgrade and go to the Service Deployments tab, where I can then deploy the VMware guest introspection infrastructure, right? So our service virtual machine and all of the stuff associated with that. Or the partner service virtual machines. So let's look at the guest introspection architecture. Let's kind of dig in just a little bit. We saw a very high-level version of this a little while ago, but let's take another brief look. I've got my guest virtual machine that's running whatever applications it's running. We also have the VMware tools drivers installed, right? The vsep.flt.sys is the guest introspection filter. vsoc.sys is my VMCI socket that we use to communicate back and forth with the multiplexer, and then we have a couple of different tools in the partner service virtual machine, right? Antivirus is what we're looking at here, but it could be, say, vulnerability management or other stuff. And then a specific security library that we've provided the partner so that we can make this guest introspection work happen. We can validate that the thin agent is installed in the guest operating system. We just look at files. This is all going to be Windows only. But we can look at that. We can look for vsep.flt.sys or vnet.flt or vnet.wfp.sys. The vsep.flt.sys is the file or data introspection, where vnet.flt or vnet.wfp.sys is the network introspection device driver. The difference between the network introspection device drivers, vnet.wfp.sys will be installed on Windows 10 or newer systems, where older systems will use the vnet.flt. I can check my VMware tools installation to see if these are here. I can look at the file system. I can also look at the cluster, for example, in my vSphere client, in my vSphere web client. I can select the cluster and go to monitor. There's a guest introspection tab once that's all set up, and I can see my different virtual machines and what versions their device drivers are, their thin agents are. So we've got a multiplexer that we have to install for guest introspection to function. This is a multiplexer that exists inside the ESXi host that all of the service virtual machines attach to provide a common point by which we can access the VMCI channel of my virtual machines. We've talked about the architecture of guest introspection. We've mentioned the multiplexer a number of times. We've talked about network introspection. We kind of have an idea now of what's going on, at least at an overview level. So we'll come back and see some more detail in another segment. Guest introspection. We've got a multiplexer. We've got bits that need to be installed. When we prepare our ESXi hosts for guest introspection, what are some of the things that happen? Well, we have a VIB that gets installed through the same processes that we use for host preparation, right? We use ESX Agent Manager, and so we can track all that in esxupdate.log on the ESXi host. I can use ESX CLI software VIB list to see the EPSEC MUX VIB once it gets installed. I can use the process list, PS -C in grep for MUX, and find the vShield endpoint MUX or multiplexer running, right? So there are services that are running as well as other infrastructure in place. So I can see all of this stuff. We will also create a firewall rule set in the ESXi firewall, right? Not the distributed firewall. This is not the distributed firewall. This is the internal ESXi firewall that protects access to and from VM kernel ports. This is important because there is a VM kernel port attached to the multiplexer. So we've got a multiplexer rule set that will open up to allow the guest introspection traffic on our inside our ESXi host. ESX CLI network IP connection list will show us our connections to the multiplexer. We should have at minimum one connection from the multiplexer to our guest introspection service virtual machine. We may have more. And then we should also be able to look at the VM kernel interfaces and see our VM kernel multiplexer interface. Now that interface, that VM kernel port is always going to have the IP address of 169.254.1.1. Always, right? Always. That's my multiplexer IP address. So it's a link local address. Now, remember, this set of configuration things is going to be repeated ESXi host by ESXi host by ESXi host, right? All of the ESXi hosts in the cluster that the EAM agency is associated with. I can look at the multiplexer virtual switch, right? So there's a certain level of network exposure that the multiplexer has to have. That's all exposed through a standard virtual switch that we automatically create called VM service-vSwitch. I can see things that are attached to that vSwitch through the ESXi host command line using net-stats-l. I can also look at my VM kernel port, right? In addition to using ESX CLI to list my VM kernel ports, I can look at my VM kernel ports right through the vSphere web client, right? I can identify the multiplexer VM kernel port by the switch that it's attached to, right? It'll be attached to VM service-vSwitch. And then I can also use ESX CFG-VMKNIC-L to look at that through the ESXi host command line again. Common multiplexer problems. Things aren't working right. It's kind of a vague way of putting it, right? Virtual machines on a host won't work with a specific endpoint, with the endpoint on that host. Alarms are shown about endpoint communication, service virtual machine communication. Very, very often, these things are actually caused by a host being kind of ripped out of one cluster that had guest introspection deployed into it and dropped into another one, and done either quickly enough or with little enough care that the guest introspection tooling didn't get removed as the host was removed from the first cluster, so that it could be gracefully reinstalled. So what we really recommend there is going in and removing the multiplexer. Let's start peeling stuff out, reboot the host, and re-prepare for guest introspection. Right? That's really the solution we're thinking about here. Here's a guest introspection agency in EAM. So we can go and look through our agent manager and see the introspection. A status of normal is always a good thing. What kind of things, once we deploy, should we look at? Well, the VIB, right? We talked a little earlier about looking at the VIB. We talked about the rule set for the ESXi VM kernel firewall. We talked about the standard switch, the port group, the agency. What did we not talk about on this slide? We didn't talk about the muxconfig.xml file. We have a multiplexer configuration file that will be created that tells us all about the installed solutions. So, deployed service virtual machine. Here we're just looking at the guest introspection service virtual machine. Through our service deployments, we can just look and see, is it there? Is it up? Are we communicating? What's the status, right? Things are good. Things are good. I can see the service virtual machines in my virtual machines and templates view or my hosts and clusters view in vCenter, and I can see information about them just like they were any other virtual machines. We can look at the muxconfig, the multiplexer config file, right, under /var/run on the ESXi hosts. And here we see the host ID and the list of installed solutions, right? So this is just a quick XML file. I have installed solutions, the installed solutions tag, and then a solution underneath that, and that'll give me my guest introspection. And then we'll close that solution tag. If there are other solutions installed, we'll open up another solution tag. We'll define that service virtual machine and close that tag, and so on and so on and so on. So what about troubleshooting all this stuff? There's only so much we can look at, right? And we've kind of talked about most of that here already. So what things might we be looking at? Well, from the VMware perspective, we're going to look at NSX. We're going to look at vSphere. Where are we going to look at things in NSX? Well, the NSX Manager logs, maybe the UI. What are we going to look at, in the UI? Well, my service deployments. Are my service definitions good? What are my security groups and security policies look like? Am I talking to the right services? In vSphere from the UI, I'm going to look at the guest introspection versioning. Right, that's easier than looking at every single guest individually. On the ESXi host, I can validate my muxconfig XML file just to make sure that my solutions are defined properly. I'm going to check logs in syslog. I can look at my multiplexer service status. Right, so those are all the things in vSphere and NSX we might look at. Now, I also have things in the guest operating system to look at, specifically my drivers, right? Do I have VMware tools installed in this guest? Is it a complete install? Do I have the VMCI driver, the vsep-FLT driver, the vnet FLT or vnet WFP.sys driver? Are those there? And then I'm going to look to my partner tooling, and some things we might suggest here is in my partner management console, can I see my synchronization status with NSX and vCenter server? In my partner service virtual machine, can I look at the logs? Things like that, right? A lot of the troubleshooting from here is going to be completely dependent on what your partner solution recommends, right? So we can make sure that our side is working. We need to be able to work with the partner solution to make sure their side is working. Which brings us into a couple of labs, right? Lab 32, we're going to use endpoint monitoring. We're going to actually deploy the guest introspection services so that we can use endpoint monitoring. And we're going to kind of see the traffic and the applications that are driving traffic from a Windows virtual machine in your lab environment. It's pretty slick. Lab 13, we're going to go in and validate and verify all of the things that we deployed in Lab 32 for guest introspection. So we're going to look at the multiplexer and the service virtual machines and that kind of stuff. So what all have we gone through? What all have we seen? What all have we talked about here? Well, we talked about the components and the architecture of guest introspection from a VMware perspective, from an NSX perspective. We've talked about things that we can look at on our side of things to validate and troubleshoot guest introspection and partner integration solutions. So we've covered a goodly amount of ground with all of this. How about this module, right? The whole module, the distributed firewall. Really cool stuff. This is where the microsegmentation starts. Service Composer is how we start to automate that microsegmentation game. The identity firewall allows us to use all kinds of Active Directory groups for firewall rules, right? Good stuff. We've got an edge firewall, our north-south, our perimeter. So we've got not only a firewall inside the software-defined data center, but we can define our software perimeter around the software-defined data center. And then we've got guest introspection for all of the things that we need to do inside the guest for security as well.